Welcome to day 4 and good morning to everybody. So far we had 3 days of policy discussions. We had day 1, of course, with the policy on where the EU should position themselves in the world on hydrogen. We had inspiring speeches from the president of the European Commission, but also the executive vice president, Mr. Timmermans from the European Commission. And on day 2, we have talked on the research policy, looking a little bit ahead for the next 10 years, what we will do, what should be our research priorities. And then yesterday on day 3, we talked about the policies on energy and also the policies on transport, and a little bit at the end on the standards that we have to do. I think we have learned a lot. We know what the expectations are from the European Commission, from the policymakers, but also we heard firm commitments from the industry in the past 3 days. So today we will zoom in on our core job, on what we are actually doing every single day here. And these are the projects. We are funding projects, and basically the hydrogen projects we will show today are the projects that have advanced a lot since the past year. But also we will show projects not only from the FCH-JU funding, but also projects that are funded by SINEA, by CEF, and by this I would like to use the opportunity to say thank you to our colleagues in the other funding instruments for helping us and for cooperating with us to have also those projects presented during today and tomorrow. But what is most important, of course, and what I always say, is the projects and the people behind the projects. Because for me, the people behind the projects are really the real hydrogen stars, to use a quote from Mr. Timmermans. Without them, for sure, it would be impossible to advance on hydrogen, but also impossible to have at the end a hydrogen economy in Europe, and we would not be the leaders without the people. So the next speaker will be Mirella Attanasiou. She is, of course, my head of a unit for all the projects, but also for the communication. And I already mentioned it, she is doing really with her team for this week a fantastic job. She will present a little bit the FCH-JU program status, and that will be then followed by the project officers who will explain the results we achieved in each of their pillar or portfolio, how we call it, and also how we progressed towards the technical KPIs. So I'm sure you will all enjoy this very interesting day. Again, thanks for being with us here today. Thank you. And now over to Mirella.
Good morning. Good morning, everybody, and happy to be with you today. I hope we have many of you looking at us online, and we hope for these 2 full days to have a full agenda with a lot of presentation of our flagship or most representative projects. Thank you very much, Bart, for the nice introduction. Indeed, let's start with the program status. And if I can have my presentation, thank you very much for that. You heard from Bart already. The first 3 days were full of messages. I think there is a very important moment for the hydrogen, and I think the fuel cell and hydrogen trend undertaking has contributed substantially to where we are when we talk about hydrogen. Of course, you also heard that we have launched the logo of the Clean Hydrogen Partnership on Monday. And of course, as of Tuesday, the Fuel Cell and Hydrogen Joint Undertaking, in fact, it's called Clean Hydrogen Partnership. So still, for today and tomorrow, we will talk about the achievements, of course, of the Fuel Cell and Hydrogen Joint Undertaking program. Let's see if that works. Yes. Here a bit, I will start with a bit of a context and why we do what we do, if I can say that. So we know that last year we had launched the hydrogen strategy for a climate neutral Europe. And we know very well what our president have said at that time, that clean hydrogen demonstrates that we can reconcile our economy with the health of our planet. And this is precisely the spirit of the Green Deal. So at that time, when she launched the strategy, she put it very well in the context. And I dare myself to even take a quote from this Monday, saying that clean hydrogen is the energy of the next generation. So we cannot agree more with our president. And as we said, with our program, with research and innovation activities, we will try to contribute to the ambitious targets of the hydrogen strategy in order to contribute with renewable hydrogen technologies to the 6 gigawatts of electrolyzer by 2024. Why not to the 40 by 2030, and on a longer scale by 2050 with a large deployment at scale. In particular, and I again wanted to underline there, with the Hydrogen Valleys initiative of us. Who we are, for those that do not know by now, we are a strong public-private partnership with a very focused objective, a partnership between, on the public side, European Commission, and on the private side, Hydrogen Europe and Hydrogen Europe Research. And our mandate by, if I can say this week, was to bring the technologies into the market by 2020, which we managed to do with both programs, FCH1 and FCH2, the way we call it. And of course, with a new mandate, and I'll come to that later, we will even push the technologies further. What we have as objectives in the past more than 7 years was to work on the different technologies of hydrogen technologies, of course, for the different application on the transport side, to provide fuel cell and hydrogen technologies for road transport vehicles, road vehicles, but also non-road vehicles, and for the refueling infrastructure, of course, by working on reducing the cost and improving the performance. Similarly, on the energy side, when we talk about stationary application, in the same time, using reducing the use of the critical raw materials, but also looking at the technologies to be used and feasibility to be used for storage, for energy storage, with services to the grid, grid balancing. And of course, when talking about hydrogen production, mainly 287 precisely, for a bit more than 1 billion euro, 1 billion euro combined between FCH1 and FCH2, so as of 2008. And on the right side, you can see with a balanced support between transport and energy applications, almost half and half, with about 6-7% to cross-cutting activities like standards, safety, education, but also activities like cross-cutting, like overarching, supporting activities like bringing different sectors together, sectoral integration, or like, you know, the hydrogen valleys. Furthermore, when we talk about our projects, you can see projects with a well spread support over the whole Europe, over the whole member states, and I can tell that all the member states are involved in our projects. and with a balanced also funding between research-oriented projects like Research and Innovation Actions, RIA, and innovation actions, more demonstration, validation into the field actions, and a small portion of support action, like I mentioned, on, for example, education or training type of activities. In complementing all this portfolio of projects from which you will hear later, we have also some other activities, and I will go quickly through them. And the first kind of horizontal activities that we have is the European Hydrogen Safety Panel. You will also, again, during these 2 days here, a dedicated presentation about what the safety panel is doing. The safety panel is a panel of 15 experts. They help us with support on both program side, but also project side. Again, in addition to the portfolio of projects and to the grants, in particular last year, we have worked with external consultants and did three particular studies on trucks, and we have published the end of last year the study on fuel cell hydrogen trucks, the valleys, hydrogen valleys, and in the summer we have published a report on under the mission innovation activities on hydrogen valleys, and you may remember the Hydrogen Valley platform. And the project development assistance, which we launched about a month ago, a month and a half ago, which is also supporting regions with their projects. We have also, and we are continuously working on a system that maps not only the hydrogen refueling stations, but also their availabilities. On the left side, you have the link. It provides free access to real-time information system on the availability of the refueling stations. We will continue to do that, and we will try to provide such free information on the availability of the stations. We are also working, and we will continue to work on the guarantees of origin in supporting especially the requirements of the Renewable Directive. And as you know, we worked on that for almost 5-6 years. We are in the third phase of the Certify initiative, and right now we are working on harmonization of the guarantees of origin schemes among member states, and we would like to extend the work and to go beyond the guarantees of origins with this initiative. On the regions, I mentioned already the 2 reports that we have published this year, the one on project development assistance and the one on the valleys. You know, we have worked as of 2017, and that's why we have the different streams in which we work with the regions. We will continue working on that. We will continue working on the valleys, and here just to show the 3 most famous, if I can say that, valleys which we have supported. On one hand, the Big Head, in the middle, the Heaven, the Northern Netherlands Valley, and on the right side, the project in Mallorca, the hydrogen island. Again, I mentioned the international initiative that we have done and worked with under the Mission Innovation. We have created the Hydrogen Valley platform, and we will continue to support this platform and to support our public member, European Commission, in their commitment under the Mission Innovation to reach 100 valleys by 2030. And we will next year also work with, again, continue to work with a consultant to further develop this Hydrogen Valley platform, where currently we have more than 30 valleys already mapped there, with an overall investment more than 32 billion. in doing all these type of activities, we are working, as we said, with the regions, and we are working also with some other funding opportunities in supporting the regions. And in that respect, we have on our website, and I would kindly recommend that you are aware of that and refer to it, or even go there and look at it. A fuel cell and hydrogen regions hub. In that hub, you can go and find not only all these initiatives that I talked about, but also some tools that we have developed to support regions. And next to it, you also look at funding and financing support services, and the funding and financing navigation tool that we have on our website. As an overarching, if you want, activities, and in preparing the whole Hydrogen Week, but in particular today and tomorrow, we have the so-called knowledge management team, which we would like to evolve into a hydrogen knowledge hub. This team helps with this annual program review. It helps with the data collection exercise. It follows the Fuel Cell and Hydrogen Observatory. It also brings to the policy all the necessary feedback from our projects, monitors, of course, all the KPIs, and all the knowledge management tools that we need. I'm happy to announce that today we have published the program review for 2020-2021. So following the exercise of last year and this year, we have published today, this morning, the program review report. Please refer to it. In annexes, it has all the 97 project posters. The posters have been also featured on the event, on the Hydrogen Week webpage, and is based on an annual survey questionnaire to all our projects and a data collection in our trust database. The data collection I mentioned, it's also done, and the analysis is done with our colleagues in the Joint Research Center. And again, in a moment, you will, towards the end of this introductory session, you will hear also from our colleagues in the Joint Research Center how they support with this knowledge management activities. In doing this annual program review exercise, we have also, like every year, done an extensive work to collect the success stories. And for this year, we have identified 13 new success stories and 6 new best innovations. You may have watched us already Monday, when we have, based on these nominations, we have awarded the best success story, best innovation, and best outreach. Just for recollection, the best innovation went to the project Everywhere, dealing with gensets. The success story on a collection of projects dealing with sustainability and circularity, and the best outreach to the project Refine for their, I could say, outstanding activities of this year when opening the 10 megawatt electrolyzer in Cologne. Many projects this year and last year have done a lot of dissemination and exploitation, despite, if I can say, the situation in which we are with the COVID, with all the delays that some of our projects are experiencing still. I think it was a good year for dissemination, exploitation, and even for publication and patents. I mentioned already the observatory, just for your reference, wanted to again mention it here. Please refer to it. It is a tool with a lot of resources on all aspects on fuel cell and hydrogen areas. It is very user-friendly, and we intend to continue to develop the different modules with a new tender in next year. And with a new clean hydrogen partnership, we will also move towards more public awareness and public opinion, public acceptance, if I can say that. We have started working on this, and you will hear more and more from us with not only the status of the public acceptance, but also which activities we need to do on that. And now I'm coming towards the end of my presentation, which refers to the next partnership. Again, I mentioned it at the beginning, and you heard at the beginning of the week about its launch. It has been voted by the council on the 19th of November and enter into force on the 30th this week. It will provide a financial contribution from the European Union through the Horizon Europe program to the joint undertaking of 1 billion euro. And it will give this support for activities that will contribute, like I mentioned at the beginning, to the hydrogen strategy, and in particular, to develop technologies for hydrogen production, for hydrogen distribution and storage, but also solutions for end uses of hydrogen, like fuel cells, boilers, burners, or even turbines. I have here provided the schematic that I also showed on Tuesday when introducing the R&I activities, the research and innovation activities. You see that on the production side, we will mainly look at electrolysis, but also to some other low TRL routes. On the distribution and storage, on the storage side, we will look at both above ground, but also underground storage. On the distribution, we will look at liquid hydrogen. We will look at other carriers, such ammonia or liquid organic carriers. We will look at blending of hydrogen into the natural gas grid, but also repurposing of the existing grids, pipelines. We will continue looking at compressed hydrogen and technologies on compression, and of course the refilling stations for the transport applications. And then when we talk about end uses, of course, the transport and the stationary applications, how we call them. On the transport side, we will focus mainly on the heavy duty transport, starting with the trucks, maritime ships, trains and planes, but we will also, in working in synergies with the other partnerships within Horizon Europe, we will develop the necessary so-called building blocks or the technology necessary for such applications. On the stationary side, I mentioned already, we will continue working on the stationary fuel cells, but also on the boilers, burners, and turbines. And of course, as horizontal activities, we will continue working on the valleys. We will go beyond what we have done on valleys so far. We will, for example, go on cross-border activities for valleys. We will try to move the valleys towards Central and Eastern Europe. We will follow up with the valleys on the project development assistance, for example. We will, of course, continue with the cross-cutting activities like education, training, pre-normative research, safety. We will probably, and already next year, look at, again, at the supply chain, because in doing all these activities, we have to consolidate the supply chain in Europe and to ensure the competitiveness of the EU industry. And of course, we will have to address the strategic research challenges, such as, for example, reducing the dependencies on critical raw materials. And now, really about today and tomorrow, you will have different sessions following the introductory session now. We will have different parallel sessions. I encourage you, I know it's difficult to follow in parallel different sessions. I can tell you all of them are extremely interesting. Please follow them. They are very, very interesting. We have selected few projects. As always, we will try to present every project, every year, different projects. I really hope you will enjoy the presentation of the different projects. Please do not forget, if you would like to put questions, to go into the Bitumatch, into the registration tool. Please use Mentimeter. It's there open for you to put questions and to address the different speakers. Please be interactive. I think everything deserves that. So with that, I thank you very, very much for the attention. I hope I gave it a bit of a flavor of what the program of the joint undertaking does. How or what are you gonna listen to or see today and tomorrow? And with that, I would like to already introduce one of my team members, the first speaker that will go through the portfolio analysis of our project, Mr. Nikos Limperopoulos. He's a project officer in the joint undertaking. He's a senior project officer in the joint undertaking in charge of hydrogen production. And Nikos, the floor is yours to guide us through the portfolio of hydrogen production projects.
Right. Thank you very much, Mirella, for the introduction. Good morning, ladies and gentlemen. A very warm welcome to all hydrogen friends out there. It's a pity we can't meet in person, but today in Brussels, it's rainy, it's cold, it's windy, so you're not missing much. I will be presenting briefly an overview of the portfolio of projects of the FCHJU on hydrogen production. These projects are monitored by myself and my colleagues, Dionysis Tsimis and Claudiu Pavlou. You will be able to follow 14 of these projects presenting during the following 2 days in the context of these 4 sessions. Today it's about electrolyzers, and tomorrow it's alternative routes for hydrogen production. So the FCHJU has supported 56 projects on hydrogen production, providing 177 million, which is 16.5% of our support. The orange circles with the numbers there indicate the number of projects supported per topic, and you can clearly see there that it's only renewable hydrogen production routes that we have been supporting. The majority of our support going to electrolyzers, and we're starting with electrolyzers. We'll see 2 slides with some statistics. On the left-hand side there, you can see our annual support to different electrolyzer type technologies. To the right-hand side is the cumulative support, 150 million, provided mostly to PEM, then solid oxide, and then alkaline electrolyzers and other new technologies. Interesting to observe on the left-hand side the difference between FP7, the early days when electrolyzers were considered a facilitator of fuel cells, and the Horizon 2020 increased support, where the electrolyzer is moving center stage, recognized as a facilitator for the greening of hard-to-abate sectors like industry and heavy transport. When the JU was initially being formed, there was concern that it would be just big industries receiving all the funds. But you can see on the left the number of beneficiaries every year and the type of beneficiaries as well. So it's quite different. And to the right-hand side, it's the support the FCHJU provided. 40% has gone to SMEs, a quarter to industries, and more than a quarter to researchers and universities. Also interesting to look at the left-hand side, year 2018, we had only 2 large demonstration projects. That explains the small number of beneficiaries there, mostly industry. So when we have research topics, then participation is much bigger. Now, this slide shows our large low-temperature electrolyzer demonstration projects. These projects are arranged according to the capacity of the electrolyzer, which is shown in the middle gray arrow. It's not just FCAJU projects. Bottom right is the Green Deal 100 megawatt projects of the European Commission. But if we look at the complete picture, over 11 years, we saw an increase of around 500 times of electrolyzer capacity, while our support per megawatt of electrolyzer installed reduced 100 times. So clearly economies of scale, but also improvements in the industry. We'll be hearing today from 4 of our projects. I've marked them there with this graduation hats, also from the European Commission's Green Deal projects. Now, something that very interesting that we observed is that electrolyzer OEMs really had to up their game when moving inside industrial courtyards in terms of the technical stringent specifications, safety regulations that had to be followed for these devices to be installed in industrial courtyards. Similarly, industries had the opportunity to assess these new types of electrolyzers, and this created a very interesting and useful feedback loop that eventually enabled electrolyzers to move center stage in the EU hydrogen strategy. Also, very important is our support to the European value chain. And I like to use this schematic from the REFINE project. Maybe you can make out these little flags that show that the different components come from 5 different countries. The heart of the system is these 5 white boxes is the electrolyzer stacks. And then all around, you can see the balance of plant. And I had the privilege of looking at the cost statements. And I can tell you that the cost of the balance of plant is very significant. It's an issue that was also raised yesterday during the gigawatts of electrolyzer session. Now, these large demonstration projects have been supported by research projects. You can see here that most of our key performance indicators have been met in terms of energy efficiencies at system level, but also at stack level for alkaline and PEM. This is on the left-hand side. You can see how efficiency improved over the years. And on the right-hand side, you can see the current density. This is an average of our projects. The next slide provides some more detail. Bottom right is our support in terms of standardizing testing of electrolyzers that operate in a dynamic fashion. So the QualiGrids project tested on 5 different electrolyzers and came up with protocols for system level testing, while the JRC provided this very important document covering single cell and stack testing. We'll be hearing from the JRC today on their work as well. Now, recently, 2018, we supported 2 projects. We call them game changer low temperature electrolyzer projects. These projects, Neptune and Pretzel, will be developing 25 kilowatt, 100 bar PEM electrolyzers. So these projects are in their final year. There have been some delays, but the stacks are ready. Pretzel has already tested the stack. Neptune finished testing the MEAs. They operated at 4 amps and 80 degrees, but also at 8 amps per square centimeter at 90 degrees C over 2,000 hours. Pretzel has already the electrolyzer there, and it's now moving into the endurance testing. The more recent projects are 2020, our COVID projects now. They are on anion exchange membrane electrolyzers. These electrolyzers have the potential to combine the advantages of both alkaline and PEM in terms of using no critical raw materials in their catalysts and also using pure water or very diluted potassium solution. There are 3 projects, Anione, Chanel, and New Eli. All 3 will be presenting today. They will be developing a 2 kilowatt stack each. They are currently working on the hydrogen and oxygen highly active evolution catalysts. And they have also jointly developed anion exchange membrane electrolyzers testing protocols at the start of these projects. They also established an anion exchange membrane electrolyzer hub on the web. Similarly, very bright picture for the high temperature electrolysis demonstration projects, where in the context of 5 years, we saw an increase of 10 times in terms of capacity and a reduction of our support 5 times per megawatt installed, going from green high 150 kilowatt all the way to Multiply, which is 2.4 megawatt electrolyzer. We'll be hearing today from Green High 2 and the Multiply projects. And these demo projects have been supported by research projects in the field, projects like Gamer, Proton Ceramic Electrolyzer, or Reflex, both at the stage of completing and demonstrating the final electrolysis units. Green High 2 achieved very good durability, and a recent project is Switch, which is a reversible 75 kilowatt electrolyzer, 25 kilowatt fuel cell system for refueling stations. The last 3 slides are now the alternative hydrogen production routes. So we've supported the production of hydrogen from the dissociation of water using concentrated sunlight. It's mostly based on redox thermochemical cycles, the Hydrosol family of projects. Hydrosol plant demonstrated they developed technology in the field, 750 kilowatt thermal, a number of issues. Basically, the efficiency was very low. Hydrosol Beyond is currently trying to address these with materials improvements, but also system improvements like advanced heat exchangers like the one shown bottom right. We'll be hearing tomorrow afternoon from the Hydrosol Beyond coordinator. At low temperatures, we have photoelectrochemical devices going from artifiction to PEC demo to PEXIS, improved efficiencies, larger sizes. PEXIS will be presenting again tomorrow, established these 10 square meter panels, operated for 9 months, producing a total of 22 kilograms of hydrogen. Still work needs to be done there. It's an area to be supported in the future, Clean Hydrogen Partnership for such systems, but also for standalone renewable electrolyzer systems, either PV electrolyzer or wind turbine electrolyzer. The last slide is on biomass gasifiers or biogas reformers. On the left-hand side is biogas, dry or wet biogas. Unfortunately, only 1 project each, and quite some time ago. Dry biomass gasification was successful, Project Unify, and Project High Time was wet biomass waste, a small laboratory unit. And to the right-hand side, it's the reformers. We focus on small distributed reformers that reform raw biogas, meaning including CO2. Project Bionico and Biorobur Plus. Biorobur Plus will be presenting tomorrow. They are reforming biogas, which is less than 60% methane, the rest being CO2, and they're producing 99.9% pure hydrogen. With this, I would like to conclude saying that through our research projects, we saw that the best-in-class electrolyzers have met the 2020 key performance indicators. Our large demonstration projects have shown that electrolyzers can play an important role in the EU energy policy. In the future, there will be more targets for further improving electrolyzers and ensuring EU leadership. and alternative routes have received support till now, but there is still some time to go until they can make an impact to the real world market. Thank you for your attention. Mirella, over to you.
Thank you very much, Nikos, for your insightful presentation on the production side, on the electrolysis part. Don't put your mask yet and don't leave us yet, because we got an interesting question here, and I would like to take them as we go, because then it's going to be very difficult to have a full panel with all of you. So it would be good to take the question. So somebody in the audience, it says that for the 100 bar electrolyzer project, will it cover only cell performance or also cost penalty for the design at higher pressure?
This is indeed something, thank you for this question. This is indeed something that the project eventually need to assess, whether one should go for atmospheric or 30 bar or 100 bar. The aim here is that if you have an electrolyzer 100 bar, you can, without the need of a compressor, inject directly to transmission natural gas grid lines. So eventually we will have to assess the additional cost, any efficiency penalties, with the cost of an electrolyzer plus compressor.
Thank you very much, Nikos, for answering this question.
Thank you, Mirella.
Good. We received also several questions, more of a general nature. I would just like to answer to quickly just to the first one, saying that indeed all the presentations will be made available, and also the recording of all the week of the recording on the YouTube, of course, on our YouTube channel, and the presentations will be made available on the page of the event on our website. Ultimately, we hope to make that available as of next week. Now, without looking too much at the other questions, because and thank you for sending questions to us. I'm really happy to take them. We will make sure we take them all. I would like to introduce my next team member, another senior project officer in charge of distribution and storage lately. I mean, portfolio of projects that he's managing, it's also looking at production, hydrogen production, at stationary application. But I think towards the next GU, Dionysis Tsimis will probably start looking more and more also at distribution and storage. And I have the pleasure to have him with me today to introduce you to the portfolio of projects in that respect. Dionysis.
Thank you very much, Mirella, for the kind introduction. Hello, everyone from my side as well. I'll be today briefly going over the portfolio of projects that we have on hydrogen storage and distribution, which are now monitored mostly by my colleagues, Claudiu Pavel, Nikos Limperopoulos, and Alberto Garcia Hombrados. Next slide, please. As with the other panels as well, we will have dedicated sessions, dedicated parallel sessions on this topic. As this is a newborn panel, we only have one this year, but we expect that this panel will grow in the coming years, and with Okay, hello everyone. Welcome back. Sorry for that interruption. As I was mentioning, we will have also a dedicated parallel session on this topic on hydrogen distribution and storage and carriers at 4 o'clock today. So if you're interested to hear more about the topic, about the 4 projects that we have on this section, please tune in and make your questions online. Next slide, please. So back in July 2020, the European Commission released their hydrogen strategy, where they outlined the need for an EU-wide logistical infrastructure for hydrogen. And in line with this, we have within our program 4 groups of areas that are dealing with this topic, trying to support this endeavor. On storage, we have we're dealing with bulk underground storage and above ground storage. And then on the distribution side of things, we are starting our first demonstration on hydrogen injection into the natural gas grid and the separation from the gas grid. Staying on the distribution, we're also dealing with hydrogen carriers in order to enable the transport of hydrogen across vast distances. And I will walk you through in a bit more detail on each one of these 4 application areas. Next slide, please. So it is clear that in order to enable the seasonal storage of electricity and to be able to provide the industry and the mobility sectors the massive amounts of hydrogen that they will need in a reliable and cost-effective method, that we will need some form of underground storage. And this work has started within our program with Project High Under, which has been completed since some time now, which identified some of the most prominent sites for hydrogen storage and indicated that there is a small additional cost projected of about €0.5 per kilogram when we're dealing with such form of storage. Now, recently in 2021, actually, we funded 3 new projects on underground storage, and we're seeing the surge of interest on the topic. On the one side, you can see on the left Project Hipster, which is dealing with salt caverns, and it will be an actual demonstration doing a cyclic testing of the storage facility. And on the right side, you can see the 2 projects, High Stories and High Esprit, that are dealing with a different media, porous media, depleted reservoirs, and aquifers, and are looking at technical feasibility and risk assessments and how to mitigate them. Apart from these 4 dedicated projects, we also have a demo planned in our Hydrogen Valley in the Netherlands, Project Heaven, where although it's not a dedicated project to underground storage, it will have an element there, a storage facility planned in a salt cavern with a pressure of 40 to 80 bar. Next slide, please. Now, apart from the underground storage, it is clear that we will also need some form of decentralized storage as well. And for us, in our program, we have focused on a novel technology on metal hydrates. We've had a series of 3 projects, SSH2S, Eden, and Bor4Stor, that have led to HyCare, which is the most recent project we have on this topic. It's the biggest capacity that we have seen in our program, and it foresees a system capable of storing 50 kilograms of hydrogen. It is also very innovative in terms of the efficiency that is aimed. So we're aiming at 70% round trip efficiency. And a very innovative element of it is that it is planning to integrate phase change materials in order to store the heat that will be necessary to release the hydrogen from the storage facility. And you'll be hearing about it more later today in the parallel session. Next slide, please. Now, moving on into the distribution side of things, it is clear that one of the most cost-effective ways of distributing hydrogen will be by utilizing the existing natural gas grid. And with this in mind, we have a dedicated project on this looking at how to focusing on the high pressure natural gas grid and the ability to inject there. The project will be developing an R&D platform that will be testing admixtures, 20% and up to 100% hydrogen. And it will be looking at innovations necessary to make the high pressure network compatible with admixtures. Apart from this dedicated project, we also have some other demonstrations happening in our big demo projects, like Heaven, the Hydrogen Valley in the Netherlands that I mentioned before. Also Green Island in Mallorca, where the project plans to inject into the local gas distribution grid of Mallorca hydrogen of up to 2% by volume. And also we had a modest demo of the project HyPem2Gas, where it injected in the distribution network of Germany. Next slide, please. And as we are going to be injecting hydrogen into the natural gas grid, it is also important to have key technologies that are able to separate and purify the hydrogen from these admixtures. And here we have two projects, HyGrid and Memphis. HyGrid is focusing on low content of 2 to 10% in the mixture, while Memphis is looking at higher contents of above 50%. And as you can see, the project managed to achieve the cost of purified H2 to be below 1.5 euros per kilogram, while we still need to work on scaling up these prototypes to have capacities up to 25 kilograms per day. And on the bottom right, you can see that with the blue bars, we have the energy consumption, and with the green bars, we have the recovery rates. And as we're going into higher recovery rates, it is tough to keep the energy consumption down, to keep it efficient. And this is something that still needs to be dealt with to have high recovery rates at good efficiencies. Next slide, please. And on the last point, on the distribution side, we move on to hydrogen carriers. And here I would like to point out that the JRC did a policy brief a few months ago, where they compared several ways of distributing hydrogen for a point-to-point route for 1 million tons of hydrogen. And it showed that for very large distances, as you can see on the graph on the right, liquid organic hydrogen carriers present themselves as competitive solutions. And with this in mind, we are supporting two projects, HyStock and Sherlock. HyStock is looking already at a prototype that you can see in the pictures of 24 kilograms of H2 per day, while Sherlock is looking at scaling back down, going into a lower TRL and looking at more innovative catalysts in order to lower the cost of the overall system and the distribution of hydrogen. Next slide, please. Yeah, to conclude, I think it's quite clear that there is no silver bullet in terms of the distribution and storage of hydrogen. And it will depend very much on the amount of hydrogen, on the distance, on whether there is existing infrastructure available, etc. And with this in mind, we have, as I have clearly shown in my presentation, we support technologies really across the board. Looking at underground storage, we have the first demo starting now, a surge of interest from the industry and research, really on the topic. On above ground storage, our focus has been mostly on metal hydrates, with the most innovative project being presented later on today. And then on the distribution side of things, we are looking at the first demonstrations of hydrogen in the natural gas grid, as well as the prototypes needed to separate and purify the hydrogen from the admixtures. Lastly, on the liquid organic hydrogen carriers, as I said, we have the first prototype already being tested, and it is a solution that we're looking at closely in order to enable the import and export of hydrogen across very large distances. With this, I'd like to thank you for your attention, and we can move back to you, Mirella.
Thank you very much. Thank you very much, Dionysius, for your insightful presentation too. So also very happy to see how reactive the audience is, I have to say. And to thank you for sending us questions. I have to say even that the hiccup we had, the Dionysus, the audience was telling us. So I'm really happy to see so many people looking at us and telling us that we should be aware it's frozen. So thank you for being with us today again. And we got two questions. Let's try to make them quick. So one is of more of a political nature, if I can say. And it's asking with the recent developments on the blending side. Do we think it's opportune to have the blending in our program? I would take that one myself, and I will say that indeed it's a good point, and we will see what the next gas package of the Fit for 55 towards the end of this year will tell us in as regards the blending. As I said at the beginning in my presentation, we will probably have to look more into repurposing than into the blending. And of course, we will adapt our program according again to the policy needs. The second one for you, Dionysus, is the one on injection, still blending. And it's asking if it's necessary, it's a very technical question, if it's necessary to odorizate, it says the question, to odorate, or to introduce some other chemical compounds into the hydrogen before it is injected.
Yes, thank you for the question. Indeed, this is something that we will be looking at in our next partnership. It is one of the topics identified by our research and industrial community, and it is in our next, let's say, multi-annual work plan as a point to do further research on and to see whether it's possible, as it will also affect the end-use applications. It might affect the end-use applications, to see whether it would be possible to odorize hydrogen. This is something that will be of interest in the future, and we will be looking at it.
Thank you, Dionysus. I see more questions, but I think it's time to move on. So thank you very much again. And thank you to you again. I encourage you to put questions. We will do our best to take them, and especially if we have time at the end of this session, we will try to take them all. It is time now to move to the next presentation on another portfolio of projects that we have. And for that, another colleague of mine, part of my team, Lionel Boyot. He is a senior project officer also in charge of transport applications. And Lionel, really looking forward to your presentation this morning.
Thank you very much, Mirella. Let's start a journey within the result from project looking into hydrogen for transport application. We'll start that journey by the road transport, so the buses, the cars, the trucks, then moving on towards ship, rail, train, and aeronautics. Then we'll do our first pause, looking at the research done in fuel cell systems and their manufacturing, ultimately reaching our last point, which will be the infrastructure to refuel hydrogen vehicles. Next slide, please. This overview session is complemented by 3 dedicated sessions. One will be about transport and infrastructure, a second one about heavy duty, and the third one about building technical blocks for heavy duty sector. The last session will be moderated by my colleague Pietro Caloprisco, who, together with Claudiu Pavel, helped me to put together the slides for this presentation. Next slide, please. Let's start with cars. This year, in 2021, we have achieved the milestone of the 1,000 cars being deployed within our project, H2ME, H2ME2, and Zephyr. And collectively, this project have amassed more than 25 million kilometers driven by hydrogen vehicles. This is quite an achievement. If you consider that 5 years ago, in 2017, only 500,000 kilometers were driven. So in a 5-year period, that's 40 times more. Most of the vehicles that were deployed in 2021 were part of fleets of vehicles, specifically hydrogen taxi fleets. So if you fancy a zero emission, silent ride to the Eiffel Tower or to Buckingham Palace or to the Little Mermaid, please do so with one of the hydrogen taxis that are available in Paris, in London, and in Copenhagen. The COVID-19 had an impact on public transport operation, therefore on the taxis. So some of the vehicles within fleets have been put on pause for most of 2020 and the start of 2021. But the operation of the taxi is now resuming, and we've seen the inauguration of the fleet in Copenhagen, 100 hydrogen taxis. Next slide, please. Another interesting business case outside the taxi are the functional fleets of vans. Since May 2018, utility company ENGIE is operating a fleet of 50 hydrogen Kangoo van. These vehicles are used like for like by the technician, meaning that they do not take specific care of these vehicles. They will throw their toolbox inside, so it shows the robustness of these vans. And the hydrogen is used as a range extender to the battery, meaning that with the battery alone, the maximum autonomy is 85 kilometers. That's certainly sufficient for 3/4 of the number of days. So we could imagine the technician refueling with hydrogen only when it is needed for the long distance days. But what we figure out, collecting and analyzing the data, is that there is a like for like a 50-50 share between the electricity and the hydrogen. So it shows clearer an adoption to the hydrogen technology by the drivers, by the technicians. Next slide, please. Now we speak about the buses. There is an increasing demand, an increasing number of buses in operation in Europe. We started from 50 in 2019, and by the first semester of 2022, we will reach 350 buses on the road in Europe. It's 7 times increase over this 2-year period. What we see as well are that the cities involved in the JIVE and JIVE 2, the early adopters, if you want, from the hydrogen buses, are now doing their second follow-up order. That's the case for Aberdeen, for Wuppertal, for Pau, Cologne. And there is a demand for coaches, long-distance coaches, and 18 meters articulated buses. This is the purpose specifically for the coaches of Project Coach Highfield. The technical achievements were there, and we are still collecting data on the performance of the buses, but one key indicator is the consumption of hydrogen per 100 kilometers. And if you look back in the year 2000 to 2010, in that decade, the average consumption was 23 kilograms per 100 kilometer. And today, from the early result of JIVE, we see 8 kilograms per 100 kilometer. That's roughly 70% reduction. Next slide, please. Truck is the next road segment to decarbonize. And it's getting a lot of attention. 28 trucks and bin lorries will hit the road in 2022 in 7 European countries. So we do have project H2Hole that will deploy 2 different configurations of the truck, a 26-ton rigid and a 40-ton tractor truck. These will be used by several end users, from logistics, from the retail, from hydrogen distribution. They will use them in different cases, different mileage, different payload, different types of goods that will be carried. And regarding the urban bin lorries or garbage trucks, 3 of them are already in operation in the Netherlands, and for the benefit of the worker, improving the working condition, and the one from the citizen having a silent collection of the garbage in the morning. Next slide, please. But the preparation for the wide commercialization of the hydrogen truck is not done by only increasing the number of trucks, but as well in making sure that all points of attentions are covered to provide commercial confidence into the product. It means that the durability of the fuel cell must increase, and therefore Project Immortal and More for Life are looking into degradation mechanism so that the state-of-the-art value on a fuel cell, which is 5,000, 6,000 hours for automotive sector, can go to 30,000 hours needed for the truck sector. STASH is looking at standardized fuel cell module. So imagine a shelf that in a plug and play manner could be put in different truck architecture and even beyond, into ships, in trains, in aircraft, you name it. This helps to aggregate the market, lower the cost of development, and have a reduced total cost of ownership of that solution. Finally, the advantage of hydrogen trucks is that they can refuel fast, and therefore Project Pride is looking on the objective to refuel 80 kilograms of hydrogen within 10 minutes, something which is currently not possible due to the limitation of the existing protocol. Pride is as well involving partners from Japan and from the US. Next slide, please. Regarding ships, we started small, went big and quite fast. And due to the variety of ships, depending on their distance or the autonomy they need and the power needed, we've been looking at different fuels and different fuel cells. Historically, we started with hydrogen, gaseous, then moving towards liquid hydrogen in PEM fuel cells. And in 2019, we supported a project, SHIP FC, looking at ammonia in a solid oxide fuel cells. So this is one part of the project. The demonstration will get operational data from these ships later on. But we do have a project called eShips, which looked into pre-normative research, into gathering experimental data so that it can develop guidelines for the safe design of hydrogen vessels. And it is a combination of the operational data and the desk research, if you want, of pre-normative research, that will feed into the regulatory authorities, CESNI for the inland navigation, and IMO for the seagoing ships. Next slide, please. Ports are often located in urban areas and are facing pressure to decarbonize their operation. 3 projects are looking at providing heat and clean power for ferry terminals in the port of Palma, Orkney, and Tenerife. And in the port of Valencia, for the container handling, we do have heavy machineries, yard tractor, a reach stacker, and a mobile HRS that will provide clean service for the handling of containers within the port of Valencia. 3 weeks ago, so quite recently, we've signed for a study that will last 2 years on hydrogen for ports and industrial coastal area to measure the demand at different horizons of time, how hydrogen can be produced, be it locally or imported, how can it be stored, distributed, and find out the economics, define a roadmap on how to implement that vision. It includes as well community building aspect by the establishment of a European hydrogen port network that will feed into an initiative from the Clean Energy Ministerial at the global level. Next slide, please. On trains, Project FCH2 Rail, which started recently, will develop an innovative bi-mode fuel cell hybrid train. It will be tested, it will be validated, and brought to the point of homologation. On aircraft, same trend, started small, going big. We started with auxiliary power units to power a secondary system like the kitchenette within an aircraft or the emergency operation, up until a propulsion using fuel cells and hydrogen of a 4-seater aircraft. That's Project Heaven. Given the importance at the European scale of the aeronautic sector, we are looking into how to scale up the fuel cell to 1.5 megawatts and the handling of liquid hydrogen within airports. Next slide, please. Let's let's have a look into research and investigation for MEAs. Still today, 40% of the stack costs are due to the use of critical raw material, namely the platinum. So the objective of several projects were to increase the power that you could get with the lowest amount possible of platinum. So that in the graph, it will be on the right-hand side at the bottom. The blue areas are our KPIs. Several projects have achieved remarkable results in the sense that in 12 years period, from 2018 to 2020, a 10-time decrease of the platinum loading was noted from 1.5 gram per kilowatt to 0.11 gram of platinum per kilowatt. Non-PGM projects, Crescendo and Pegasus, have achieved technical targets. However, the cost still need to be further reduced. Next slide, please. So when facing an increased demand in Europe for fuel cells, it means as well that we do have the capacity in Europe to produce in high quantity at the right quality and reduce cost all these components, balance of plant, fuel cells, stacks, and so on. That was the purpose of several projects which have been looking into automated assembly line, inline quality control, design for manufacturability, things like that. An interesting result is that the cell assembly has been reduced from 22 seconds to 5 seconds, 4 times less. That's an achievement. Next slide, please. Now we look into the infrastructure, the HRSs. And in a hydrogen refueling station, the most critical component is the compressor. It's energy intensive, and it's the reason or the cause of the downtime. So through a succession of projects having cosmic in their names, we have supported the concept of a hybrid compression system using metal hydride and mechanical compression. It has been then validated, and it's now working in a real hydrogen refueling station, providing hydrogen for a garbage truck. It went even beyond that, because due to its successful exploitation, a company, a small and medium enterprise called HiFiTech, has been created. The succession of the Cosmic project helped to reduce the capex by 55% and halve the energy consumption for the compression. Next slide, please. Out of the a bit less than 100 hydrogen refueling stations supported by the FCH, we've noted a shift from 2015 up until now. Back in the days, operators will have a small number of HRS with a known number and identified customers. And now these operators have to manage a network of HRSs that are facing fleets of vehicles to which the owner are not identified. So that means the customer experience must be improved. And if we look at one indicator being the payment system, back in 2017, the monthly invoice was the accepted or adopted practice. And today what we see are mobile app payments, or you pay with your credit cards. Customers are demanding an increase of back-to-back refueling, multi-dispensers, things like that. Availability of the HRS for the buses has increased up to 98%. Next slide, please. To conclude, for the hydrogen buses, the goal is to get robust data on 3 aspects: the economical part, so the TCO, the environmental benefits, and the operation of both the buses and the infrastructure. For the heavy-duty segment, trucks, ships, heavy machineries, we continue to prepare the commercialization of the product. Regarding manufacturing, the focus is there to increase and scale up the capacity available in Europe and strengthen this European supply chain. And regarding research for the building blocks, investigation on the low platinum catalyst or even non-platinum gold metal catalyst is clearly so something to achieve, together with the improvement of performances and stability of these catalysts. Thank you very much for your attention.
Thank you very much, Lionel. I have to say, the audience is really getting warmed up by your presentation. We receive a lot of questions, which I would like to reverse to the different sessions, where the different projects will be presenting, because I believe it's the right moment then rather to do it now, to get into the details of manufacturing and how we will revisit, for example, the business cases for fuel cell vehicles. Or the TCO of the trucks with fuel cell or with batteries. So that's the type of questions we receive, and I would like the audience to wait a bit for the different sessions to get answer to that, as we are a bit behind schedule. Thank you very much again, Lionel, for that, and it's time now to introduce the next project officer, Antonio Aguilo Rulan. He's the senior project officer in charge of the energy application, in particular stationary fuel cells. And of course, he will present us that portfolio of projects and the achievements, of course, over the past year. Antonio, the floor is yours.
Thank you. Thank you very much, Mirela, for the introduction, and good afternoon, everyone. Today I will be sharing with you, if you can put the slides, I don't think I can see them, but okay. Today I will share with you our update, our progress on a stationary application with fuel cells. And tomorrow you will have the chance, next slide, please. And tomorrow you will have the chance to see the more details presentation of a number of dedicated projects. So if we can have the next slide. Yeah, and the next one, please. So for the last 14 years, we've been providing support to a whole range of activities, starting from research, lifetime performance, material levels. We managed to put together the first generation of products to test them in operational environments through early field trials. We continue parallel research to come up with the second generation of systems, which is now being demonstrated in a number of ongoing projects that we will present later on. So far, within the two joint undertakings that precede the Clean Hydrogen Partnership, 87 projects have been supported with a total funding of 277 million euros. Next slide, please. Starting with domestic applications, we're talking about here heat and power production for residential sector and for the small businesses. The market continues growing, 25% increase since last year. We could conclude that European market is in the order of 20,000, a bit more systems. We do continue our large-scale demonstrations in the PACE project, close to 2,000 units installed, but this is not the only deployment activities that are taking place. In Germany, largely thanks to its national support scheme, the KfW, we have seen 18,000 applications filed in these schemes. It has started some years ago, meaning we have a market, as I mentioned before, of around 22,000 systems. Follow-up countries include Belgium, around 1,000 systems installed, and also important activities in countries like France and Italy. If we move to the next slide, please. We reported already last year that our program targets for 2020 have been achieved, both in terms of performance, but also in terms of cost reduction. And as we accumulate hours of operation, we are now starting to see, for instance, continued operation of a single fuel cell systems for close to 40,000 hours. That means that we are able and starting to be able to validate, if you want, the durability of the stacks, for instance, that manufacturers are reporting. So we will continue monitoring this system. So in the years to come, we should even have longer operational hours. Also availability levels on the 90% range, which is what you would need indeed for commercial operation, for real operation in real households. Nice report that the Joint Research Center has produced, providing a historical analysis of our activity in the stationary sector. You can see the link in the slides if you were interested to read. Next slide, please. In terms of research, we are glad to present the results of some of our projects, looking at the next generation of component designs and manufacturing. Mamma Mia project, working at MEA level, it developed and costed a fully printed catalyst-coated membrane manufacturing process line. managing to reach 3 gigawatts of MEA capacity of production capacity per year, while keeping the equivalent performance of the MEAs than more traditional, if you want, manufacturing processes. At interconnect level, solid oxide fuel cell, low-cost IC project has demonstrated the feasibility of roll-to-roll process, and also low-cost steels have shown to perform similar as high-cost steels in lab. Low TRL level project, Cell3 Editor, very successful. It looked at adapting 3D printers for solid oxide fuel cells printing. It printing single repeating units by different printing techniques. And it's good because it managed to start investigating how you could use 3D printing to print novel surface geometry, like maybe corrugated cells, where you can increase the power density thanks to 3D printing. Similar activities continue in the NewSOC project, helping to keep European leadership on the solid oxide field. This project gathers European solid industry and research communities and is looking again at improved performance, durability, looking at material element and hoping to validate what elements will be at large cell and short stack level. Next slide, please. Looking at the stack, we had the QSOF project. It reduced the conditioning time for the stack, 75%, managed to achieve 10 seconds inline inspection of cells, bringing the cost of the CapEx for solid oxide to 1,100 euros per kilowatt at mass production. Important achievement, or if you want, impact of this project is that it managed to secure new stack production plant in Europe by a leading stack manufacturer. We continue supporting proof of concept projects. We have, for instance, the Empower project that will be presented tomorrow in detail, looking at a 5 kilowatt high temperature PEM fuel cell using methanol. Next slide, please. Last year, now we moved to commercial size systems, application of fuel cells for the commercial and service sectors. Last year, we saw that research have managed to put together the second generation of systems through a number of research projects or lower TRL level projects at the stack level. Then the Innosoft project presented in detail last year put this second generation of units. We are glad to have now data that we can present to you for the first year of operation, system efficiencies over 60%, availability level of 99%. These units are ready for serial manufacturing. They have fewer components. They are simple to manufacture. So now the next step would be to have volumes of manufacturing that would allow to reach the necessary CapEx. Next slide, please. So how we can get there? We do have now an ongoing project, that is the COMSOS project, that is looking actually at deploying a larger number of these next generation of units. You can see that on the right part of this slide. We intend to deploy 450 kilowatt electrical of capacity. 2 OEMs out of the 3 that we have in the project have finalized their design. 160 kilowatt of electrical capacity has been manufactured, 1 system installed, 3 under installations, and we hope to provide results also next year. Next slide, please. Now, solid oxide cells offer versatility, and this is what the 2 projects I will present now are exploiting, if you want, or are looking at. In here, we have the CH2P project, looking at using methane-rich gas, could be natural gas, can be biogas, to simultaneously produce power, heat, and hydrogen. We have done, or the project has done a number of tests at large stack module level, reaching promising degradation, efficiency degradation rates, 0.26% per 1,000 hours. CapEx target, the targets of the hydrogen production being 4.5 euros per kilogram of hydrogen. Bringing it to the next level, the switch projects is operating or can operate in the same fashion, tri-generation, but then it's also able to operate in reversible mode, hence producing hydrogen using electricity. Early tests at large stack module level have shown efficiencies of hydrogen production of 97% when waste heat is used. It targets a 2.8 euros per kilogram of hydrogen. Most immediate application would be hydrogen refilling stations, but it can be used, of course, to any end use that would require hydrogen. Next slide, please. Tomorrow, we will see this set of demonstrations presented in detail. Just to say here that we do have a number of 1 project supporting power-to-power solutions for isolated and off-grid remote areas. We're talking about here to take renewables, to convert it into hydrogen through electrolyzers, storing it, hydrogen storage producing power with fuel cells. These systems present higher CapEx, but lower OpEx, and they do come with zero local air emissions. Hence, they are alternative for diesel generation. 3 demos are planned, 2 of them are ongoing. They are below the 100 kilowatt electrical capacity, and tomorrow we hope to see the results presented. 1 additional system being prepared in Gran Canaria in Spain. Next slide, please. And then we have also the ability to produce power, portable power with hydrogen gensets. We do expect to demonstrate these systems across Europe in festivals, in construction sites, in urban events, even in shore power applications. We hope to get 7 gensets built by the next year. 2 of them have already been validated, and they are ready to be demonstrated already in this winter. If you would like to get involved, please look at this slide, click on the link that I added there, because there is opportunities to get involved if you would like to use one of the gensets for demonstration. Next slide, please. Remote power under harsh condition. This is what RoRePower is attempting to do. We intend to produce 47 units. 20 of them have been already installed or are under installations. They have demonstrated operation under -20, -30 degrees centigrade, a startup, and long-term desulfurization also been achieved. Systems have been certified, and tomorrow we will have detailed presentation. Just to point out here that the demonstration, most of them are now taking place in a broad market, offering actually opportunities, real opportunities for our industry to export European technology abroad. Next slide, please. So my last slide, we already reported last year as well, looking at the early results of our megawatt scale fuel cells. Installations were abroad, driven by the higher power prices. We're talking about the refinery application in Martinique and also a 2 megawatt PEM fuel cell in China. Performances were good, but costs were high. So what happened a few years ago, we started the Grasshopper project, looking at a 100 system prototype, representative of a megawatt scale fuel cell. And we are happy to see that the system is now finalized. Commissioning and first startup has taken place. The plant is now in the south of Spain. It should move to Netherlands soon for real, for starting operation in a real environment. And dynamic operation, load 20 to 100% has already been tested. This comes with an improved stack, and we hope to be able to report on that next year as well. So next slide, please. And final, domestic sector, we have managed to move the market from 100 to 20,000. We do have now a track record of performance of the next generation of products. That's important to point out. And we have achieved our 2020 KPIs. We see a strong and consolidated European supply chain component, but also at system integration level, composed not only by established heating equipment manufacturers, but also with SMEs, which is, I believe, an important achievement. Commercial applications, next generation of fuel cells demonstration has started, and very promising to see the early results for reversible solid oxide regeneration systems. We believe these systems will play a key role when we do have high penetration of renewable. We will require a flexible energy system, and as I mentioned before, solid oxide is able to achieve or to offer that flexibility. Next slide, please. And finally, for the larger applications, we are very happy to see that the prototype of the next generation of low cost and flexible PEM fuel cell has been built, has been validated, and is ready for demonstration. And we are glad to see that the findings we have managed to gather in this segment are now being used as well for other sectors, maritime, and possibly in the years to come in the aviation sector as well. Power-to-power solutions demonstrated or starting to be demonstrated, hydrogen gensets ready to be demonstrated across Europe. And finally, solid oxide fuel cells for remote infrastructure applications seem to be performing as expected and is allowing to open up also overseas market for European industry. So that's it on my side. I hope that was clear for all. And yeah, I will pass the floor to Mirela. Thank you.
Thank you very much, Antonio, also for your very insightful presentation. Again, we are getting a lot of questions from the audience. And same, I would like to recommend everybody to to keep these questions. They will, I hope, be answered during the sessions dedicated to this project. Thank you very much. We are running a bit late because of the hiccup we had at one point for a few minutes, but I'm sure we will recover. And I would like now to introduce the last but not least project officer, senior project officer, Alberto Garcia. He's in charge of the, I will have to say, extremely challenging portfolio of projects, which is dealing with so many issues from the so-called cross-cutting, from education, safety, pre-normative research, standards, input to standards, and managing even the safety panel. So Alberto, the floor is yours.
Thank you, Mirela. Thank you very much. And hello, everyone. And welcome to this last presentation of this session. First of all, I would like to see if the slides come up, if it's possible. First thing I wanted to say is, there we go. I would like to invite everybody to the two parallel sessions that we will be having tomorrow on pre-normative research for standards and safety, but also on education and training in the morning. So I look forward to seeing you there. And the second thing I would like to mention is that, and to remark, is that in addition to the, let's say, challenges and challenges that we have heard in the previous sessions, mass market commercialization of these technologies also present a number of horizontal challenges that also needs to be addressed to effectively kickstart a hydrogen economy in Europe in the next years. And in that sense, traditionally, we have been tackling all these horizontal challenges through cross-cutting projects on different areas. In particular, we have 6 different focus areas on regulation codes and standards, education and training, safety aspects, also on social awareness and public acceptance, on sustainability and databases. And in the last years, as the technologies are approaching to the market, we have increased the number of supporting activities that we have running in the program, such as, for example, the activities performed by the Regulation Codes and Standards Strategic Coordination Group, the set of activities thanks all together with the Joint Research Center of the European Commission. We set up the European Hydrogen Safety Panel, as Mirela mentioned. We have different initiatives concerning regions. We launched the observatory. We have also, we are providing funding and financing support services. We are publishing studies, just to name up a few. So Mirela has already presented some of them in the opening, so I will try to cover those that remain. So let's start and let's have a look. On regulation codes and standards, we are here supporting the development of adequate and enabling regulatory frameworks for the market uptake of these technologies. We have been supporting projects performing pre-normative research activities. We have also supported, like, for example, HiLaw, a project in order to identify the legal and administrative processes around these technologies, but also the challenges and the barriers and how to overcome them. We have also supported the project Certify in order to set up a framework for the guarantees of origin at the European level. And just to mention that the majority of the activities have been conducted or have been focused on pre-normative research, because we believe that being a research and innovation program, this is where we can make really the most impact. And also because pre-normative research is an essential step for advancing regulation codes and standards, because what the pre-normative research does is to bring new knowledge, scientifically sound, hydrogen specific, to improve, update, or further develop, let's say, standards that then can be referred into regulatory documents. We have been supporting pre-normative research activities in a variety of topics of different nature, like for example on indoor use. I cannot really see, but okay. Hydrogen refining stations, hydrogen in the natural gas as well. So in many different topics. Just to give you an idea, in 2021, we have 10 projects performing pre-normative research to support the development of this regulatory framework. We have 3 projects focused on safety aspects. Presley project is dealing with liquid hydrogen. High tunnel project is taking care of the safe use of hydrogen vehicles in tunnels or underground parkings. Multi-high fuels is dealing with the safety aspects of hydrogen into refueling stations where there are different fuels. We also have the Pride projects developing a refueling protocol for heavy duty applications. We have the e-ships projects dealing with waterborne applications and also including the port bunkering, but also Hydro project dealing with hydrogen quality, ID-FAST and ADE Astra dealing with the stack testing, in particular the accelerated stress testing. And lately, as I mentioned, we also have projects performing pre-normative research activities on natural gas and hydrogen blends. In particular, the Higgs project is addressing the high pressure gas grid, let's say the effects of injecting hydrogen in the so-called transmission gas grid, while the Taiga project is really checking the effects of injecting hydrogen in the end user appliances at the domestic and also the commercial scale. All these projects somehow are supporting the development of this regulatory framework, and all of them, they are covering the entire hydrogen chain. And most importantly, they are also targeting specific standards at both European and international level. And just to give you an example, out of the 8 projects running in 2020, 4 of them, 50%, were addressing standards at the European level, while the other 50% were addressing standards at the ISO and IEC level. Also, something that it is worth to mention, and but I will not spend much time because in the next session, Pietro Moretro from the JRC will provide an overview of the different activities that we have with the JRC. But it is worth to mention that thanks to the framework contract that we have with the JRC is supporting the program throughout many different activities concerning regulation codes and standards, concerning safety. Also, they are supporting about the activities concerning related with the program monitoring and assessment, and so on and so forth. And I will not spend much time. I'm pretty sure that Pietro Moretro in the next session will be able to provide a much better overview than me in one slide. The second focus area on cross-cutting, let's say it's education and training. And here, what we try to do is to share. We have in Europe a lot of knowledge and know-how. What we here try to do is to share that knowledge, to keep up the expertise, but also to prepare the European workforce that we need in the years to come for the mass rollout of these technologies. And to do so, we are supporting the development of educational and training programs for different target groups, from young professionals, technical professionals, safety officials, responders, technicians. Also, we are supporting the development of an e-platform to connect all this knowledge. And also we are supporting the development of the setup of a network of university. So there will be a network of universities in charge of teaching hydrogen fuel cells at the university level. Altogether, all these projects are encompassing different levels of education, from primary, secondary, or tertiary education, different types of formats, just like, for example, e-learning, in-class teaching, or blended learning as well, and also different features like virtual reality, serious games, and so on and so forth. In 2021, we have 3 projects running. The first one is FCH Go, who was focused on primary and secondary education. Also, we have the project Teach High, which is developing a master course for blended education at the university level. And we have the Hub Responder project with developing a program, the so-called Train the Trainer program for first responders. So we are sure that the responders, first and second responders, are aware of all the peculiarities of hydrogen when they face an incident or an event related with hydrogen. Over the years, the last year, we are collecting information from the projects. And in that sense, I'm very glad to share with you that just during the lifetime of these projects, more than 4,000 people have been trained within the projects from more than 11 countries and at least in 10 different languages. And indeed, if you see the graph at the bottom, the trend is very positive. And every year, we're increasing the number of people trained and getting trust on these technologies at the same time. Safety for us is paramount. We need to have a safe deployment of these technologies, especially in the next years. And to do so, of course, we are supporting projects dealing with safety aspects on pre-innovative research and also education and training type of projects. They are addressing safety aspects, but we have also supported the specific actions on concrete safety aspects, like in hydrogen sensors. H2Sense project, they developed a guideline how to use sensors, what technology is best for what application, where to place the sensor, and so on and so forth. Susana project developed a model evaluation protocol for CFD, for safety analysis, and also say H2Trust, they built a safety expert group, which indeed was the precursor of the safety panel, among other initiatives. Apart from the projects, as I mentioned, there are many other activities running in the program. And I would like to mention just that thanks to the cooperation with the Joint Research Center, we are increasing the number of incidents and accidents in the hydrogen incidents and accidents database, the so-called HIAT 2.0, but also we have developed a specific research thematic on the team, technology for innovation monitoring, on hydrogen safety. Sorry for this. The sites, as Mirela mentioned, in 2017, if I'm not mistaken, we set up the European Hydrogen Safety Panel, which is a group of experts helping us at the project at the program level to make sure that the hydrogen safety is adequately managed, addressed, but also supporting the promotion and the dissemination of a high-level safety culture on hydrogen safety in Europe. This year, the panel has been very active. We will have a specific presentation tomorrow, so I will not go into the details, but at the project level, they have released a new guidance document, not only for FCHJU projects. This is a guidance document on safety aspects, on safety planning and management, as we call it, for any type of projects involving hydrogen fuel cells from the private sector, from the public sector. They also have organized a workshop. They are performing safety reviews for the safety plans of the projects. At the program level, they are having different contacts with international actors in order to find points of synergies and point for cooperation concerning data collection and the assessment. They have also issued a new report with the lessons learned and the recommendations for different sectors and applications based on the data contained in this hydrogen incidents and accident database that is managed by the JRC. And on public outreach, as I mentioned, they have revamped the website. And for example, this year they have updated, they have developed this research thematic specifically on hydrogen safety in the team, in the tool for innovation monitoring. On sustainability, it's a very important topic because we need to make sure that this sector is sustainable and circular, and we have been supporting different initiatives to this end. For example, FC High Guide projects to develop life cycle assessment methodologies. FC High Tech Cycling, who has paved the way on recycling and dismantling technologies, and certify, as I mentioned, concerning the guarantees of origin. Apart from the projects, we have a lot of different activities also with the Joint Research Center, and thanks to that, now in 2021, we have 3 projects on sustainability and circularity. The SHE project, it's dealing with the life cycle sustainability assessment, which will be update the guidelines from FC High Guide to the current technologies, but also to include the social dimension, let's say, in these assessments. We have also the Best for High project, which is developing technology for recycling, novel and existing technologies for recycling FCH technologies, and the EGOS, which is the first of its kind, which is developing eco-design guidelines for FCH projects to make sure that right from the beginning, from the design, we are taking sustainability and circular aspects into account. Last but not least, on databases, we are developing databases we are supporting the development of databases to concentrate and to facilitate everybody to concentrate and facilitate everybody the access to the information. We have in HiLo, they developed this database on legal and administrative processes. In NetTools, they developed a database of different tools which could be used for the design and also for safety aspects concerning FCH technologies. And Susana project, they developed this databases for the verification and validation of CFD models. Apart from that, we have 2 databases, or I would like to mention at least 2 additional databases that we have in the program. One is the Trust database, which is for technology monitoring, but also we also have, and we launched a couple of years ago, the Observatory, which is a one-stop shop to find reliable information on hydrogen and fusion technologies, like concerning the technology, the market, publications, patents, education and training, and so on and so forth. So, in conclusion, I know we're a bit late. In conclusion, pre-innovative research, safety, education, sustainability are essential aspects for the mass market commercialization. Both projects and supporting activities, we believe, they are contributing to a safe, sustainable, and frictionless deployment of these technologies in Europe. And altogether, they encompass a set of activities which definitely are strengthening the whole FCH sector and supporting the market uptake in Europe and beyond. And with this, I have finished. So thank you so much for your attention, and I look forward to seeing you tomorrow. Mirela, the word.
Thank you very much, Alberto. And yes, I really have to apologize to everybody for being late, and in particular to the next speaker, Pietro. Many apologies for keeping you and being late. I hope we will be able still to have a small break. So yeah, without talking too much in between, also myself, I would like to introduce the last speaker from this opening session, and is our colleague Pietro Moretto, Deputy Head of Unit in charge of energy storage in the Joint Research Center in Patton, working with us and supporting us for many activities. We mentioned them a bit throughout our presentations, ranging from knowledge management, safety, regulation, code, standards. Yes, really happy to have you here with us, Pietro. And yes, the floor is yours.
Thank you very much, Mirela. While waiting for the upload of my presentation, I can tell you that I'm here replacing Evelyn Weidner, that I think all of you is known. So if my name is Pietro Moretto, but you have to imagine that Evelyn is speaking in front of you. Next slide, please. This is the multi-annual, the scope of the JRC activity in support of the joint undertaking along the many years, as Mirela has mentioned. There are 4 pillars sketched here. Don't worry, I'm not going to give any detail on all of them. I just simply selected for you some interesting story that I have not told yet in the past. Next, please. So the first story that I want to tell you is what we have done together with the Program Office and the Hydrogen Europe to prepare the quantitative dimension of the next multi-annual work plan. If you have assisted to the Smart Talk on Knowledge Hub 2 days ago, you have heard Bart and Elaine repeating often the importance of data and the quality of the data. This is linked to what I'm going to tell you today. If you have a good objective, the setting of key performance indicator is a straightforward work. You have to choose indicators that are able to measure, to let you define the progress of a certain technology. And for that, you have also to set some future targets and the baseline that we call a state of the art. If everything is done in the proper way, then the target monitoring, the measurement of how the program is approaching the target is a very simple thing. Next, please. So if for the first part, the setting of the key performance indicator and the setting of the target and identification of state of the art, in 2020, we prepared a methodology that has been at the basis of this process. Next, please. And we are doing already since a lot of time the annual program review of the joint undertaking. This is, and now I'm addressing the project coordinator among you. This is why you are putting quality data in trust, why you are responding to the user survey request every year. Many thanks to those who are doing it in the best of your possibilities, because it's a time-consuming exercise. We hope with this work that we have done in 2021, having set better key performance indicator and better measuring system for a better program performance review. Next, please. So what you are getting for this money? You are getting in the multi-annual work plan, which has not yet been published, but is ongoing work, several tables dedicated to individual technology for individual applications, containing all what I've just mentioned before. Next, please. I hope that you like this style that I've chosen. It's a symbolic representation of what has really happened. It seems a linear and very simple exercise, but it's been a messy and sometimes a muddy exercise. We had to create our way in the jungle by doing it. So a big thank here to the great expertise of the program office and of Hydrogen Europe. And let me single out one thing, the great capacity of diplomacy of Michael Diderich in this particular exercise. One important thing is still to be said. First, well, two. First, that this is work still ongoing, and we may meet again in a couple of years to redefine certain set of parameters for application that could not be defined well now. The second important point is here on the bottom. The indicator must be measurable, and you need a set of tools for doing this. And the JRC is helping the joint undertaking to produce also some tools that can be used for this. A colleague of mine, Alberto Pilenga, will give you an example of this in the frame, under the frame of what we call the harmonization of European testing protocols. The only thing that I wanted to announce here is another tool that we have just terminated, finished to produce now. Next, please. If you are looking for in hardware, a testing device able to test MES in a most neutral way, here you are. This is a design that we have worked through in the last 4 years. Now it's available to be downloaded from this link. You can download the blueprints. You can download the validation work that we've done, the reporting. What we are not doing is manufacturing it. And a big thank you to the project partner of IDFast, because they have been the guinea pig in testing our prototypes and identifying the difficulties of subcontracting and manufacturing in this frame. Next, please. Now, jumping completely on another subject. You have already heard many people in this Hydrogen Week speaking about sustainability as the core, becoming one of the core dimensions of the new partnership. The JRC is not only supporting the joint undertaking in this frame. So the message here is that we are working also on many different fronts. The work is not yet finished, and we are anxiously waiting for the new update of the Renewable Energy Directive. But here there are some elements. You are certainly aware of the so-called EU taxonomy. You can find it online as a taxonomy compass. And if you are looking for hydrogen, you will find that there is already a definition or a criteria to define a low carbon hydrogen according to this approach. We have used this approach, further developed into a first attempt of a methodology to assess innovation funds call. And we are also working now with the colleague of the service of the Commission, DG Comp, for the important project of common European interest. We are still, from a hydrogen perspective point of view, missing a very detailed assessment criteria and the methodology for measurement. Next, please. So this is, I don't want to repeat this, but this is a long path that we have started in 2019 together with the program office. And we have now at JRC been able to mobilize more resources, not only hydrogen expertise, but also pure LCA and sustainability expertise. We will work together with this project. And it's not by chance that 3 of these projects that I just mentioned there received an award on the first day of this Hydrogen Week. Next, please. Okay, you have seen Alberto already speaking about the databases that are supporting this horizontal enabler dimension of safety. I don't want to go too much in detail in this because the European Hydrogen Safety Panel presentation will probably present the success of this year, based on our database. The message here is that at the moment, the public database HIAD is offline. The reason for this is completely independent of the quality of the database, is security, increase the security criteria at the JRC. So we cannot use anymore the platform before. We are working on a new solution together also with the program office. If you want to access the data set inside of the database, you can write to me and I will deliver all of the resources that we are available together with an Excel sheet. I realize now that the address there is wrong. You may imagine that I'm doing it on purpose to avoid overload, but it's not. The right email is the one written at the first slide of this presentation. So this was a kind of incident, not a safety incident. So next one, please. And this is the last message that I wanted to tell you. The quality of the data are essential, not only for scientific progress, but also to measure the scientific progress when you have a funding program. And also in the frame of safety, the statistics that allow to discover, to deduce failure statistics and reliability data are essential. But it's not the whole story. You need still incident narrative and incident specific stories. This is essential, in particular now where we are going to upscale the quantity of hydrogen brought around in the world. So near misses, stories that could have been gone wrong, but they didn't, are extremely important to learn how to improve the future. Okay, this is all the 3 or 4 messages that I wanted to give to you. Mirella, the floor is back to you.
Thank you very much, Pietro, and thank you very much for sticking to the time because we are extremely late. And again, thank you also for staying with us, being so much late. And ultimately, thank you for supporting us. It is an interesting journey that we have to go through. And like you mentioned, especially in the past year, extremely challenging to set up the new KPIs for the next partnership, I have to say. I'm getting continuously questions in the chat especially on the next program. So I would like everybody to bear with us and to tell you that the next program, it's still under discussion what exactly the next program or the next joint undertaking will cover. So it's not everything set in stone. And yes, bear with us, stay with us. These 2 days we will discuss about the achievements so far. And like I said, for the future, we're still talking about it. So with that, I would like to finish. It's only 1 minute left of the break. I hope we can resume in 2-3 minutes. And I would like now to close this session. Thank you, everybody. And let's now split in 2 parallel sessions and hope you will find them interesting. Thank you.
Good morning, ladies and gentlemen, and welcome to the parallel session on electrolyzers for industrial applications, part 1. This first part is on low temperature electrolyzer demonstration projects. After the break, it's going to be high temperature. There are 4 projects. High Balance is a completed project. This was our first lighthouse megawatt scale project. Then Demo for Grid and Aeolus are projects been running for a few years, faced a few challenges, but now have commissioned their electrolyzers. And we will conclude with Project Jules, which is our biggest and most recent 20 megawatt electrolysis project. Without further ado, I would like to invite Guillaume Jarin to present the High Balance project. Each speaker, please try to present within 10-12 minutes so as to have some time for a question or two.
Thank you, Nikos. Thank you for giving me the opportunity to present the High Balance project and open this session with the electrolyzer. Maybe we can have the slide on the screen. Yes, thank you. So I'm Guillaume Jarin, working for Air Liquide, and I will. So I'm also the coordinator of the High Balance program. So if you can go on the next slide, please. Yes. So the High Balance project is started. Let's say we have to go back in 2014. To the annual work plan of the FCIGU. The idea was to demonstrate the potential of central production for energy storage. And also to see how electrolysis and power to hydrogen can provide grid balancing services. And in order to support the development of intermittent renewable energy. So the program ends in 2020, in September 2020, but the facility is still in operation. So the total budget was 15 million euros for the project and 8 million euros funded by the FCHU and 2.6 million euros funded by EUDP. So the Danish organism, national Danish organism. So if you can go on the next slide, please. So, the plant facility is located in the north of Denmark, in Hobro, exactly. We have different partners working on the project. So we have Hydrogen Valley, who is the dissemination partner. We have NEAS, who is now called Centrica, who is the balance responsible party for the trading of electricity. Hydrogenics is the supplier of the electrolyzer, and LBST in Germany is in charge of the life cycle analysis for the environmental assessment on the project. And Air Liquide make the design, the construction, and the operation of the site. So on the next slide, please. So the idea of the project, there are several goals, and let's say so as I explained, one of the first target was to put in operation the first PEM electrolysis at megawatt scale. So at that time, we had only, let's say, demonstration of prototypes in laboratory conditions. So the idea was to evaluate the performance of this technology in industrial environmental condition. So one of the main topic regarding PEM and let's say main advantage that was seen at that time, it was the reactivity and the flexibility of the technology to address the grid services provision topics. So it was not only the only target. So as I explained, one of the major target was also to deliver customers in industrial application and mobility application. And then the last point is also to check how to operate and manage the operation, fulfilling all this production, H2 production, and serve customers while we can also bid on the electricity market and use the storage capacity of the plant for the energy storage. On the next slide, please. So there were many key achievements for this project. So the site was inaugurated in September 2018. Since then, we performed the ramp up of the production, H2 production, with 120 tons of hydrogen produced. So at the end of the program, but now it will be we have more than since the 1 year, one additional year. Regarding the performance of the plant, we meet and sometimes at some point exceed the targets of the call with a high availability and numerous hours of operation. Also, the site deliver on the 24 and 7 days mode an industrial site which is close to the plant, which is delivered by pipeline, and also address other customers with trucked in the transport of the H2. The plant was homologated also by the TSO operator to be able to provide the grid services. And yes, as I explained regarding the nominal flow, H2 purity, and efficiency, we were on the target of the call. So if we can go on the next slide to check a few more in details, a few KPIs that were, let's say, very important to demonstrate for this project. So the first one is the energy efficiency. So the state of the art in 2014 was to demonstrate that we can reach between 60 to 55 kilogram of kilowatt per kilogram of H2. So we reached regarding with the design of the electrolyzer. So here we have to take care also on the boundaries. I include the electrolyzer plus the auxiliaries of the electrolyzer, meaning the water filtration and the transformator from the grid. So we reach 56.5 kilowatt per kilogram of H2. And now we saw that there are some improvement in the technology where we can reach with the state of the art is more around 52 kilowatt per kilogram. Next slide, please. So one important topic, as I mentioned before, is the reactivity of the electrolyzer. So it was demonstrated within the iBalance program, a ramp-up time. So hot idle ramp-up, meaning we have a standby and already functioning electrolyzer at about 5 to 10% of its capacity, and we can reach the full production capacity in 2 seconds. So this is for the testing in operation. In fact, regarding the need of the TSO, we need to reach 50% of the capacity within 15 seconds. And then we have 30 seconds to reach the full capacity of the electrolyzer to let's say, to balance the grid when there is a need on the primary frequency market. So this is a great achievement, and let's say it's validate the fact that PEM technology is can react very quickly and is very dynamic for this purpose. The next slide, please. So also one point regarding the capital cost, which is a major point, obviously. So as it was the first of its kind, there was a, let's say, high cost of construction, design, and for the equipment. But we were within, or let's say, we were a bit up to the target, which was 1,050 euros. per megawatt and per kilowatt, sorry. And we reach 1,800. So now we have also several figures that we can see. Always, we need to always be careful with these figures because the target today is to have around 1,000 euro per kilowatt for the full plant, or let's say including engineering and construction. But we need also to be careful because depending on the project, you will have also the grid connection to take in consideration, and which can be a very, let's say, capex intensive, depending on the site where you are located, and also so the construction, obviously, and the different elements you want to integrate for the compression and storage of the hydrogen. Yeah, so we can go on the next slide, please. So regarding the life cycle assessment, so Denmark was chosen because there was a high potential of renewable and a lot of deployment there, of very ambitious targets to provide more wind power into the grid. So we can see on the left that the reference case was the German, let's say, trucked-in hydrogen from production from SMR. And we can see that already when we start up with the operation, we were below this carbon footprint. And obviously no surprise there, the electricity represent the carbon intensity of the electricity represent the main part of the carbon footprint. And we can see that in the future, we will reach a very low kilogram of CO2 emissions per kilogram of H2 produced. That's still on the scope of the Danish grid content. So on the next slide, please. So this is also an interesting graph to see the correlation between the electricity cost and the production of renewables on a certain time. So we can see that when we have low carbon intensity, we have also cheap price of electricity, which means that it's a good economic business case to produce when we have a lot of renewable in operation. So it was just to mention that, and it's going in the good way for next project. So on the next slide, please. Just checking. Yeah, so just a few words on the risk and lesson learned and the challenge we have in front of us. Maybe I will keep it short, as I think we are running out of time. So there is we had a large amount of technical and on improvement for the futures on the equipment. A lot of lessons learned there on the design, also on the plant, and to then decrease the engineering hours on the future project. And one also not surprise point is that the electricity cost represent a very high share of the H2 costs. So here we have a big challenge to in the future to implement the policies and to find ways to reduce this share with efficiency improvements, and also to have more capacity of renewable available on the market, as we can see that there is a lot of demand on electricity, on low carbon electricity at the time. And next slide was just to mention all the dissemination activities. There were a lot of dissemination activities around the project. And yeah, so in terms of media, you have several videos available on the website, and also some reports, interesting reports that you can, a lot of readings if you want. And next slide, just to conclude. So on the project, that is, so iBalance was a key demonstrator and flagship project. which will enable a further deployment and get experience for larger scale projects in the future. Thank you very much for your attention. If there are any questions.
Thank you very much, Guillaume, for being also on time. Maybe you would like to share with the audience if you had any financial benefits to the provision of electricity balancing grid services?
Yes, so we did several simulations and trials on the plant to check what will be the benefit, how we can take advantage of cheap prices of electricity. So the let's say the global overview is that we can achieve about 20 to 25% reduction on the electricity cost. Looking at this market, and we also see some very at some point we also can profit from almost sometimes it was also negative prices, so to use the renewable electricity. So,
right.
So there is a lot of potential here.
Thank you. And a question from the audience is: are you monitoring hydrogen-oxygen crossover on your electrolyzer?
You mean the production of oxygen? If we are checking,
if indeed you're measuring if there is any hydrogen in oxygen.
You mean okay in terms of quality?
Yes.
So yes, of course we are tracking the quality of the hydrogen produced, not only on the electrolyzer side but also at the end of the process, because we have to deliver industrial quality, and we reach very good quality levels, better than what we can have with production with SMR.
Right, which is also very important if you operate the electrolyzer dynamically. Thank you once more, Guillaume. Let's now quickly move to our next project, Demo4Grid. I would like to invite Ewald Pervok from the industry that is hosting the electrolyzer, Emprise in Austria, to give his presentation. Ewald.
Yes, hello. Thank you very much, Nikos. Hello to the audience. I'm glad to be here and to have the chance to give you some insights on our Demo4Grid project. My name is Ewald Pervok and I am working for Emprise. Emprise is the implementation partner in the Demo4Grid consortium. A few words later on. Next slide, please. Project overview, Demo4Grid. We came up with a proposal to demonstrate a large-scale rapid response electrolyzer to provide grid balancing service and to supply hydrogen markets, very similar to Guillaume and the High Balance project. Our project has started in 2017. It's ongoing, obviously, and apart from the project budgets and the financial contributions, you can see here our partners is our Diadikasia, our Greek coordinators, FEN Systems and Emprise from Austria, the Fundación Hidrogena de Aragon in Spain, and Inicom, our control and command partner, and IHT Sunfire from Switzerland. IHT is based in Switzerland. They are supplying the pressurized alkaline technology. Next slide, please. So here, to some of you who might remember the project review days 2019, that picture might ring familiar, still there. Before we dive into it, let me a few quick remarks to Emprise. Emprise is a local food retail company that is operating 30 supermarkets in the area of Western Austria and Southern Tyrol. We are a family-owned business, and we do not only operate those markets, we also have a fleet of vehicles, heavy-duty vehicles, to supply the markets with our goods, and we also operate a production facility actually 2 production facilities, a meat processing plant and a bakery. And in this setting, we have now implemented our Demo for Grid project, which consists of mainly, obviously, a big electrolyzer. We will see some pictures later on, which you can see here in the middle, this electrolyzer. As I said, pressurized alkaline electrolyzer coupled to the grid. One of the challenges we are going to meet is that also this electrolyzer will supply grid balancing services. If that will be to the extent that the High Balance project is doing that, we don't know yet. Because they are active on the primary, secondary, and obviously on the tertiary also. We are aiming for the secondary balancing power market. And if we are not supplying services to the grid, of course, we also want to produce hydrogen for the 2 business cases mentioned here. After production of hydrogen at the 30 bar level, you see here the 2 symbolic 2 containers. In reality, they are 3 type 1 vessels that hold the cleaned hydrogen ready for use. And we supply them to our business case number 1. That's what we say. We burn the hydrogen there in a special burner boiler construction. And that boiler is producing industrial process heat at the 300 degrees Celsius level to supply our baking ovens. And business case number 2 is there. HRS will be supplied a 350 bar refueling station, and that will supply our truck fleet, our growing truck fleet of fuel cell vehicles. First 3 vehicles will arrive in February 22. So you can imagine we are really excited. It's not long that we'll be able to start up the entire value chain. Next slide, please. Here I brought along some pictures. Obviously, the objectives of our implementation the objectives are to demonstrate the rapid response capability of the pressurized alkaline electrolysis technology by supplying grid balancing services to produce hydrogen, and that will be done on a scale of 3.2 megawatt, and that will result in a hydrogen production capacity of roughly 1,300 kilograms of hydrogen per day. We are also very proud on the next statement there, integrated plant efficiency beyond 90%. How did we do that? The process, the electrolysis process in our case is running at a temperature level of roughly 90 degrees Celsius. And the heat that is being produced by the ohmic resistance of the stack is recovered, and we transfer that heat to our production facilities to supply also 60 degrees Celsius process heat, or in our case, warm water. Our production facility is using a lot of warm water for various purposes. And by decoupling the process heat and transferring it to our production facilities, we can reach this plant efficiency. And the applications, as said, industrial process heat on those 2 temperature levels, commercial road transport for captive distribution fleets. These are the applications we are serving, we are planning to serve, and we will start operating in February 22. The pictures on the top left, you see a detailed view onto our dual fuel burner. That dual fuel burner is capable of burning hydrogen and natural gas, switching over. That came from the need to decouple the downstream production process from the hydrogen production process. So if we do not have suitable hydrogen in terms of technological availability or pricing, we can switch to natural gas. And the picture below, you see a more integrated view of this new boiler burner configuration that's been now implemented in our facility. Those pictures are 2 weeks old. Top right, you see the 3 type 1 vessels that are holding the cleaned, ready-to-use hydrogen after production. And in the background, you see the electrolyzer hall that we have erected. And on the bottom right picture, you see a close-up of the electrolyzer hall, which has a footprint of roughly 2,000 square meters. Next slide, please. Project progress, site erection. As I said, all the pictures are from 2 weeks ago. Top left, you see our one of the transformers. That is the one producing electricity or producing voltage for our auxiliaries. On top middle, you see the core team of IHT Sunfire and Emprise just finishing the erection of the second head plate to the stack. Top right, you see the 3 vessels. To note here is we have, since we are providing grid balancing services and we are the nominal production pressure from our technology is 30 bars, we also prepared ourselves to produce hydrogen at lower pressures. And in order to handle those without compression, we have decided to have all the 3 containers being governed separate pressure levels. So that means if we decide to produce at lower pressures, we can dedicate one of the vessels on the fly to lower pressure levels so that we can hold even hydrogen that's being produced below 30 bars. That is especially interesting for the burner, for the hydrogen burner, because that hydrogen burner only needs a 5 bar input pressure. Bottom left, you see the cap ends of the 2 gas separators, where the gas produced, the hydrogen and the oxygen, is being transferred from the stack into. And there, the separation of the gaseous phase and the liquid phase, meaning the electrolyte, is separating from the gas. And after that calming procedure, so to say, the gas is further processed, and we have an online gas sampling, obviously, to refer to the question of the high balance project. Of course, we measure hydrogen in oxygen and oxygen in hydrogen constantly. And after that separation, the gas is then sent into the cleaning, and it is dried and cleaned and put into the storage vessels. At the bottom middle, you see the grounding of the stack. You see there is quite some copper. That's a massive installation. Our stack will operate at a nominal DC power of roughly 700 volts, and thereby conveying a maximum of 9,500 amps. So that means copper lines need to be robust. And on the bottom right, you see the stack. Here, one step further, it's pre-assembled and the tie rods are already inserted. That was, as I said, 2 weeks ago. And now we have even took one step ahead. The tie rods are pre-tightened, the stack is pre-tightened and is ready for commissioning. Cold commissioning will take place now before Christmas, and warm commissioning is planned to take place in January 2022. So you can imagine, after such a long time, coping with enormous resistances in various aspects, we are really happy and proud that we have reached this point in time. Next slide, please. Since we are about to commission, I was not in a position yet to bring along a lot of KPIs and compare them. That will be done in the next session when we have commissioned and when we have the experience, and we will see how our stack will behave in real time. But for now, I leave it with site implementation. We have now finalized site implementation around 95%. Some piping is to be finished, and some odd ends are being put together. And as you see, commissioning has already started. We started the loop checks. Everything is brought together in the control and command system. And we're looking forward to, as I said, to the warm commissioning that will take place in January. And the bottom three pictures are something I brought along. The hydrogen refueling station in the middle, you see that. There is one dispenser at the 350 bar level that will serve the trucks. Bottom right picture, you see for the trucks, we partnered with Hyzon, a Dutch company that is supplying the first 3 trucks, 2 pullers and 1 rigid truck. That, as I said, they will arrive in February. And one special part about the refueling station is that the green truck you see there, that is a trailer refueling station. And that serves not only as a backup, so in case our production facility goes offline, we can supply our business cases with hydrogen via a semi-trailer. And also this refueling station or this trailer refuel or filling station actually works in the other direction as well. So we can fill semi-trailers and produce and bring the hydrogen to other business cases in the area. On the left-hand side, you see a MEC, that's a multi-element gas container. We have also chosen to purchase 2 20-foot multi-element gas containers, the ones you see there. These are Type 4 vessels, and they will serve as containers for forwarding hydrogen to other business cases. And they will be pulled by the pullers you see on the right-hand side. Yes, that is the project progress so far. Next slide, please. So what have we learned so far?
Sorry, Ewald, maybe you can try to wrap up within a minute or two?
Yes, thank you. I will. COVID was exceptionally strained to the consortium, but that is nothing new. All the other consortiums have experienced this as well, I believe. The integration of the Demo for Grid project into our facilities was a tremendous effort. Interfaces. So that and the decoupling the production with the business cases was extremely challenging. And also we were suffering from different technology readiness levels along the value chain, boilers, electrolyzers, and so on. And also the lack of standards, which we suffered, especially in the 350 bar refueling station. Yeah, thank you very much. Great more things to tell, but time is running out. Thank you for your attention.
Thank you, Ewald. Indeed, we're running a bit late, but maybe you can tell us, there are some questions. How much hydrogen do you store in the trailers and how much in the 3 stationary tanks?
The 3 stationary tanks now can hold 800 kilograms. One trailer, or the trailer which we have purchased, can hold about 150 kilograms.
Great. Thanks very much for this. And let's then move to the presentation of the Aeolus project, to be given by Elodie Parent, who is one of the members of the consortium. Elodie, the floor is yours.
Thank you, Nikos. So I'm going to present you the progress on the Aeolus project. So my name is Elodie Parent, and I'm the dissemination manager of Aeolus project. So Aeolus stands for Hydrogen Aeolic Energy with Optimized Electrolyzer Upstream of Substation. Next. So about the project overview, so we answered a call in 2017 named Highly Flexible Electrolyzer Balancing the Energy Output Inside the Fence of a Wind Park. And the project starts 1st of January 2018, and it will end at the end of December 2023. The total project budget is about 8 million euros with the FCIG contribution of 5 million euros. And we are 7 partners involved in this project. SINTEF in Norway will coordinate the project. UBFC in France, Tecnalia in Spain, Unisanyo in Italy, Varanger Craft in Norway, which is a end user, KES in Italy, and Hydrogenics in Belgium, which is the electrolyzer supplier. Next. So we are located in Arctic Norway. So you can see it in the red square on the top right figure. In Wagoville Wind Park, we have a power of 45 megawatts built out of 200 megawatts due to the limitation in the grid export capacity. And the total potential is in fact 2 gigawatts that represent 400 tons of hydrogen per day, but with a low local consumption. So we can use hydrogen as solution to export the energy. And so we are located in Bellewaerde Harbor, which is already still virtually inside the fence of the wind park with some dedicated power line and also with access to the road, but also to the sea for the hydrogen export. Next. So we define 5 main objectives. The first one is high wind power penetrations. The second is about the demonstration of multiple use cases. The third one is the demonstration of 2.5 PEM electrolysis technology with a remote operation. And the last objective is dissemination. So what about the global positioning? So we want to produce some green hydrogen based on PEM electrolyzer integrated within a wind farm and with a remote control and monitoring due to the remoteness of first of the locations and the difficult accessibility, especially in winter. So you have a picture on the top right. And we can use the potential for technology transfer to offshore wind. And the market area, as I mentioned before, is hydrogen production for export. Next. So about the different project progress per action, the first one is the electrolyzer efficiency and cost. So you can see in green the target in efficiency. So the efficiency targets are already met by Hydrogenics latest stack with 52 kilowatt hour per kilogram, sorry. And it is the same for the cost. We achieve the target we have inside the project of 3 million euros per ton per day. Next. The next slide is about the electrolyzer performance. So right now the electrolyzer is under commissioning. So we have to test the different operation, the cold start and hot start. So cold start is begin at ambient temperature and hot start at even much temperature. So we have to make some tests to be able to have a cold start in 30 seconds and a hot start in 2 seconds. So this test will start next year. And it is the same for the degradation. So the target is 1.5% of degradation per year. And we have ongoing studies of historical data series provided by Hydrogenics to evaluate the degradation. And we also have a specific task on prognostic approach of the system level. So to see the degradation and to forecast some maintenance, for example. Next. So here you are a slide about control and monitoring systems. So 3 operation cases have been considered. One on energy storage, a second on mini grid cases, and the last one for fuel productions. So what is achieved for now is a dynamic model and control algorithm for all cases are existing. We also design a durability algorithms infrastructure, and we first activated in June this year a remote access and control from Benevento in Italy so to have an access to the systems and control it. And the remaining task is obviously to implement and demonstrate all the control algorithms on the real plants. Next. And last slide about this progress per action. So about green hydrogen integration. So we defined 7 public reports on various aspects of hydrogen wind energy. 5 are already done and published on our website, and 2 are expected in 2022. One about the environmental performance analysis, and the last one dedicated to roadmap to 2023 MLWP targets for electrolyzer. Next. And about risks, challenges, and lessons. So we also have some delays. First delay is due to the loss of the initial electrolyzer supplier. So Hydrogenics entered in April 2018 to the project. And so 2018 year is lost for the construction seasons. The second point is we have some problem in development of 2.5 megawatt single stack. So it is related to double stack solutions. And last but not least is COVID situation and closed borders, so that mainly impact Hydrogenics workshop and actions. But you can see in the top right corner the building, which is specially built in Norway. And we have no accident during construction, so it is a very good point. And the project progressed through pandemic, so you can see to the figure the hydrogen tank, and on the last figure you can see 2 different containers with the electrolyzer and the different ancillaries we have. So now the electrolyzer is ready for commissioning, and the first filling of the tank is scheduled normally this week. And we schedule also a in-presence project meeting on site in January 2022. Next. So now about the exploitation plan. So to produce hydrogen for local consumption, so different solution. First one is a biogas upgrade in neighboring Bastfjord. So it is different cities near to the wind farm. The development of hydrogen fishing boats, and the possible introduction of hydrogen fast passenger ferry between Vadsø and Kirkenes, so 2 specific cities. And about the expected impact, so the first one is the Bellevåg Industrial Park. Another point could be the green ammonia production, because there is an announcement of a large-scale ammonia production from hydrogen with 100 megawatt of electrolyzer scale up by 2025. One of the first application could be the energy supply to the remote Svalbard island, which are currently the last holdout of coal power in Norway. And all these different points are in line with the strategy developed by Troms and Finnmark County Council. And finally, there is also a possibility of using ammonia as a green fuel for ships, for example. Next. So here you can see the different social network where we are very active on. Next. And here I mentioned the different dissemination activities. So 2 workshops were organized by the project. One in 2019 in France about microgrids, and the second one this year, about the control and optimization of renewable and green hydrogen energy systems. So it is organized by both universities in Italy and in France, and it was an online event. 15 conferences and workshops that the project has attended. 3 journal articles you can see here, and we also published 10 public deliverables on our website, hirus.eu. So thank you for your attention.
Thank you, Elodie, for your presentation. I mean, this is really a very challenging location at the very northern tip of Norway. This was a project which is supposed to be inside the fence of a wind park. However, eventually the consortium has moved the electrolyzer closer to the port, but erected also a dedicated power line so as to provide electricity directly from that wind park, aiming to avoid taxes and levies that usually need to be paid. And I saw in your presentation, you're mentioning you're aiming for 4 to 5 euro per kilogram cost of hydrogen.
Yes. Yes, and it is studied also with different use cases we are defined. So for the energy storage, for the islanded operation, in fact, and fuel production. So we try to see the technico-economic aspects of this for these 3 operation cases, in fact. So
Right.
if we have to store hydrogen, or if we have to make the electricity on the grid, what we have to do with the different cases. Yes.
Right. And there is a question on the energy needed for the compression of hydrogen, but this is a high pressure electrolyzer delivering, I think, hydrogen at 30 bar. And it is at this pressure that you are storing the hydrogen in the large tank that you showed. So no energy spent for compression. Right. Thank you once more, Elodie. And now we'll move to the last and 4th presentation on the Joules project. The presentation will be given by the project coordinator, Joost Sandberg. Joost, like in the case of Ewald, is the brain behind the project. He's so enthusiastic about it that he's not using the standard background, but he has a background with the Joules plant. Joost, the floor is yours.
Thank you, Nikos. And indeed, the challenge to keep the presentation short, because there's a lot to discuss. Personal introduction, I'm indeed Joost Sandberg, project leader on behalf of Nobian, who's the coordinator of this project, which is the Delfzijl joint development of green water electrolysis at large scale. Indeed, already elaborating that we're looking at a large scale of 20 megawatts. Project is supported obviously by the Fuels and Hydrogen Joint Undertaking, but also by the Waddenfonds and the Dutch government. Please visit our website at joules.eu. We'll go to the next slide. Overview of the project. So it is part of the demonstration of a large scale minimum 20 megawatts electrolyzer. Obviously, the whole system uses a bit more than 20 megawatts, but 20 megawatts is the capacity of these stacks. We started early last year, and the project will run until the end of 2025, and we're actually contemplating extension of that process. Obviously, having a industrial scale project has many benefits to all the project partners. So the stage of implementation, we're close to publishing the permits and the investment decision next year, and I'll elaborate on that status. But unfortunately, we're still in the design, or we still have these kind of pictures to show, not the picture that the previous presenters have. Total project budget is over 40 million and that is on the investment, and also on the operational side. Obviously, budget will be required, but we'll elaborate that in the presentation. Project partners are Gasunie and Nobian together, developing the whole site factory. McPhee supplying the electrolyzers, De Nora the high current density stacks of the new generation in those electrolyzers. BioMCN is the off-taker of the hydrogen, and Initio is a dissemination partner and supporting on the certification. This facility will produce certified green hydrogen. Next slide, please. It's important to notice that the Joulz project will showcase a complete value chain from renewable power to renewable methanol in industrial setting at a chemical park in Delfzijl, with the right partners to make this happen at this scale. Obviously, it's a bit different in this project that it is we really strive for industrial safety because it is located on a chemical park close to another electrolyzer, chlor-alkali, and close to the BioMCN facility, which is the largest methanol factory in Europe. Going to the next slide. So we've completed design and basic engineering for the 20 megawatt platform, which actually comprises of 5 modules of 4 megawatts, which you see on the top left, or the bottom left. On the bottom right, you see the plant layout, which is minimizing the footprint of the electrolyzers and is also providing a basis for further scalability. So this plant is really designed to think in next step of scale. So how do you design a plant to allow for that scaling? At the same time, how do we design it so that it is as safe as possible with many inherently safe design features? And that's obviously quite important when we think about scale up, that we really think about safe design and as part of the whole design practice. So that's where a lot of our attention has gone as well. Look to the next slide. Here, as you see in my background, but also here, this is now the finalized design, and we are close to having the permits published. Obviously, an important milestone as well when we look at this scale up, and the quite some attention has been in making sure that not only this plant is safe, but that knock-on effects from other chemical plants on this specific plant and vice versa are also well investigated and proven to be safe. The RFI for EPCM contractor, so obviously important that we make sure that this whole plant is built in time and budget, and in a safe way. So thorough vetting process on that side, and we plan for the FID early next year, and after that we can start the construction groundbreaking. Next slide, please. Much of the learnings that we want to achieve from this project will be in the operational phase. So there's 3 years of operational phase planned in the FCH-JU project. We actually expect to expand that with up to 5 years, where we really want to demonstrate the technology, which is state-of-the-art high-pressure alkaline, 9 kiloamps per square meter. So really a next step in process intensification, delivering that hydrogen in a large scale. Well, the 20 megawatt scale, it's, we strive for more, but this is starting to get into interesting volumes also from a demonstration perspective of renewable methanol, because that's ultimately what we want to achieve, is building sustainable business cases and value chains. So that's our primary goal. We are using the flexibility of the electrolyzer to optimize on the power market as well. While we don't have, of course, the operational data, we have run several simulations, and indeed, I think basically to mirror what Guillaume was presenting, we do see that 25% to 30% reduction actually of a power cost. Now, at industrial scale, those savings add up and are important to drive green hydrogen development. We need to show these kind of technologies in an industrial setting, because that's really needed when we scale up electrolyzers. So it is important that we get the operational data, that we get safety data, which is important to drive further growth of electrolyzers. So that's what we're aiming to do. Currently, our O&M plan is finalized. We can benefit from the operational experience available at the Chemical Park Delfzijl, operating a chlor-alkali electrolyzer for decades. So highly experienced staff that will able to support the operations of Joulz, while at the same time Joulz will be set up as a remotely operated plant. So minimum human interface. Next slide, please. So key lessons up to now, I would say. A lot of efforts been done into the design of a safe system, really incorporating inherently safe design features as much as possible, and we're not adding mitigating measures. Obviously, we want to get the technology to the high industrial safety standards of the chemical industry, and that is has not been that easy. There is not a lot of safety data available of certain scenarios occurring. So that drove us to some design challenges, which we have overcome. And where also the learnings from that we have shared in the safety program, also facilitated by the FCH-JU. So I think from this, it's very important that we continue to share these learnings, because when we scale up, inherently safe design will further increase in priority. Establishing a sustainable business case, a sustainable value chain, obviously is driven by a regulatory framework which enables premium for renewable methanol. I think for all people, it is known that RED2 implementation, has its ways, and unfortunately, that is also affecting our project, obviously. But we look forward to implementation of RED2 in the Dutch legislation. Early next year, which will strongly reduce the regulatory risks on this business case. And as mentioned, we've done a lot of analysis already on how to couple the intermittent electricity with hydrogen production. On the technical side, we've also worked a lot with BioMC and how to integrate this fluctuating hydrogen supply into their methanol synthesis. And also there have found, I think, good ways how to further optimize, but also set up the control systems that enable that coupling. And obviously, while the volumes of hydrogen of joules into the total hydrogen consumption of BioMCN are limited, 1.5% of their use. Still, fluctuating feed will have an impact on their process. So that is something to consider also when supplementing into other industries, that even those volumes, really look carefully at the control systems because they will influence the synthesis loop. Next slide, please. Now, quite a busy slide, unfortunately. Sorry for that. On the explanation, exploitation and expected impact. I think the key message here is really for all parties involved. This is a key strategic project where a lot of lessons are being learned, but also are already being implemented. If we look to Nobian and Gazini, we're already taking a next step in the supply of green hydrogen into envisioned sustainable aviation fuel refinery in Delfzijl. So that's an important next step derived from joules. For BioMC and OCI on a global level, renewable methanol is really part of their corporate strategy, and a lot of the lessons from this project are taking into their broader global strategy. De Nora is able to demonstrate the use of their high current density electrodes into the system of McPhee. Already demonstrations of 1 megawatt units have been done. So that is located in Les Grenadiers in France, part of our project, but really demonstrating that use on a 20 megawatt scale, obviously very important for a scale up of their products. So I think all parties clearly benefiting from the project Jules. Thank you very much.
Thank you, Joost, for the presentation. Yeah, maybe participants noted that for this project, the FCAJU support covers only a quarter of the total budget. So there are important financial issues involved in realizing this project. There is a financial investment decision milestone coming up. It's a very real world project, which one would expect with such big sizes of projects. We have 2 questions for you. Is the electrolyzer directly connected to the wind turbines or to the grid? And is a compressor needed for feeding the hydrogen to the methanol plant?
Thank you. Starting with the second note, pressurized air process delivering at 30 bars, actually feeding into BioMCN at 22 bars. It still needs to be compressed because the synthesis is around 80 to 100 bars. I think it's methanol synthesis. So, but we're able to tap in their existing compressor, which currently feeds the output of their SMR into the synthesis. So it's a I would say on a pressure level, it's very well connected. The power feed, we actually get power from 66 kilovolts, which is the local grid at the industrial park, where there is, and that industrial park is connected to the public grid. So the feed of renewable power will be through the grid.
Right, and you might be purchasing green electricity certificates, I guess.
No, it will be through power purchase agreement. So both the electrons as the guarantees of origin to make sure that indeed we don't double count renewable power with our consumption. No.
Right. Okay. Thank you for this clarification. Excellent. Thank you for this round of presentations. There have been various questions on the energy to compress the hydrogen, but in most of these cases, these are pressurized electrolyzers delivering at 30 bar, so hydrogen can readily be stored and used. We don't have, let's say, an HRS, a hydrogen refueling station, where you would need compressors to go up to higher pressures. There were also some questions on ramp-up times for electrolyzers. I think this was mentioned, and we have only experience from the High Balance project on this. I think it's around 2 seconds when the electrolyzer is in hot standby, and around 30 seconds when in cold standby. But Guillaume, maybe you want to confirm?
No, that's correct. And as I mentioned, so this is the performance of the electrolyzer itself. But actually, in operation, we probably don't need that that's fast to ramp up that fast. So we can have a more smooth ramp up.
Okay.
Because if I might add, I think what we've seen in our analyses and design is that definitely if you connect to industrial customers as we do, the limitations will be much more in the remainder of the system than in how fast the electrolyzer is able to react on the power side.
You're right, very important. How downstream will be able to absorb these waves of hydrogen production, correct? Now we have just a few minutes, and I would like to ask you if within 1 minute each, you could describe what was the biggest challenge that you faced in each of your projects. Guillaume, what was the case for High Balance?
So I would say the main issue, at least it was not one challenge. It was to have, as it was a first of its kind project, we had to design and several. We wanted to test also to demonstrate several features for this kind of plant. So we had quite a complex process. So it's not only on the electrolyzer side, it's about the full process in the plant, because we wanted to we have first the connection to the grid, and then you have also the customer you want to deliver, so by pipeline and by trucked in solution. So you have to define the process to be able to refuel these trailers, and in the middle you have the compression and storage of hydrogen that you need to balance. In fact, depending the customer demands. So this was quite complex to put all these elements together and also to operate them. So to have a global control of the plant.
Right. Thank you, Guillaume. Ewald, what was the most important challenge that you faced?
Yes, the most important challenge, most difficult challenge. It's hard to choose, but the actual final location was very difficult to find. Here in Tyrol, we have a lot of mountains and accordingly little flatland space. And in our case, because we wanted to have this harmony with the production facility, we wanted to be close by in order to exchange media. And so it was extremely difficult and challenging to find a location, a spot to put it on. And that was certainly the most important challenge and the most difficult one. And then, very similar to Guillaume, ex aequo, so to say, was also the challenge of implementing the entire value chain down to the HRS. As I've stated in my outgoing statement, the lack of standardization, different technology readiness levels, they were extremely challenging. So we had to fit that together and to balance out the readiness levels on the different technology levels.
Right. Thanks very much. Elodie, you're not one of the technical people in this consortium, but maybe from the discussions you can refer to some of the challenges, besides being at the northern tip of Norway.
Yes. So I think at the beginning of the project, the challenge we imagine is remote access with the different cybersecurity and so on. But finally, for now, I think the most important challenge is linked to the locations and the weather. So for now, we have some snow. You have also the night durations. So it's night all the time. So it is difficult for outside operations. And I think it is some important constraints. And also we have to schedule the different tasks for the transport from Belgium to Norway of the electrolyzer systems, the integration and the testing. So we have to schedule all the different tasks and aspects during summer months. So I think the agenda and the location are
right. Yeah, indeed. In your case, you had plenty of space, but it was so remote, unlike the case of Austria, where space is an issue. Right. And Joost, maybe you would like to conclude with your comment on still many challenges to face, I guess.
Indeed. Oh, thanks very much. I think I'll take the chance to mention too. I think what we've overcome is really the challenge of. I think part of it is due to Nobion itself. Installing this installation on a chemical park with the high standards of safety that we have really took time to thoroughly explain and include in the design. I think the design and the technology has proven to be robust for quite a lot of challenges, but so we have overcome it, but it was a challenge that we all faced. And I think the other one really is an outlook on regulatory framework and the income, and that's still when we get to larger scales that will continue to play a role, and that's a key challenge ahead, making sure that we're able to market this renewable methanol at a price which will pay for a green hydrogen premium.
Right. Thank you, Joost. Thank you all. There are still some interesting questions in the chat, but I'm afraid we've run out of time. I'm very sorry not to have covered all of the questions. I'd like to thank our speakers, thank the people participating and following this session. We'll be off for our brief lunch break and back at 1 o'clock for the high temperature electrolyzer projects. Thank you all, and bye for now. Hello, everyone, and welcome to this session on electrolyzers for industrial applications, part 2. We have another 4 very interesting presentations. 2 will be on our largest high temperature electrolysis project, solid oxide electrolysis technologies. Then we have an interesting presentation from the JRC on the testing protocols for electrolyzers that they have developed. And we will wrap up with a presentation from a colleague from CINEA agency on scaling up of electrolyzers. It's the 300 megawatt projects. So let's start with Julie Mauguin, the coordinator of Project Multiply. Julie, the floor is yours.
Thank you, Nikos. Nice. Thank you for the introduction. So it's my pleasure indeed today to present Multiply projects. So I guess I need the screen somewhere. Yes. So next slide, please. So Multiply project has been proposed to the call 2019 under the topic multi-megawatt high temperature electrolyzer for valorization as energy vector in energy intensive industry. It started beginning 2020 for 60 months. We are consequently in the end of the second year of the project. The total budget is just below 10 million euro, with a maximum funding just below 7 million euro. We are 5 partners in the project, 4 industrial partners spread all around Europe: Neste in Finland and Netherlands, Sunfire in Germany, Polwurt in Luxembourg, Engie in France, and CA as the coordinator, also in France. Next slide. So the goal of the project is to manufacture, install, and integrate the world's first high temperature electrolyzer system at multi-megawatt scale, consequently reaching higher TRL up to 8, and it will be installed at a renewable product refinery located in Rotterdam in the Netherlands. So why did we select high temperature electrolysis technology for this application? It is because this technology allows to reach a very high efficiency thanks to the fact that we are splitting steam molecule instead of water molecule. On top of this, we can replace part of the electricity need by heat that we can find easily, mainly at some industrial places, and it is very efficient in order to increase the overall efficiency of the technology. Second, a high temperature electrolysis is a technology with no expensive noble catalyst, which allows to be very modular. The core technology is the cell, ceramic cell. Several of them are assembled into a stack to increase the power. Then several stacks are assembled into modules, and then several modules are put together in order to make the electrolysis system, which offers some versatility and flexibility in terms of size and piloting. Next slide. So as compared to the international state of the art, you could see from my brief introduction here that we intend to have the world's largest HTE unit by a factor more than 3 as compared to what currently exists. And as far as the refinery is concerned, it will be the first use case of high temperature electrolysis for this market area. Next. So the key figures that you can keep in mind is that the electrical rated nominal power is roughly 2.6 megawatt, including the high temperature electrolyzer, but also the hydrogen processing unit. It will allow to produce more than 60 kilograms of hydrogen per hour, and it will be operated on site roughly around 16,000 hours, consequently leading to substantial greenhouse gases emission reduction over the operating period. The technical objectives of the project is to prove at this scale the high efficiency, the high electrical efficiency, reaching 85% LHV, which correspond to an electricity consumption at nominal capacity of 39 kilowatt-hour per kilogram of hydrogen. We also intend to prove a very high level of availability above 98% and to reach good durability with a production loss rate below 1.2% per 1,000 hours. On top of those technical objectives, we have economic objectives targeting what is set in the multi-annual work plan. Capital cost decreased below to 2,400 euros per kilogram per day, and also decreasing the operating and maintenance cost below 120 euro per kilogram of hydrogen per day and per year. And we will perform an extensive technico-economic analysis of the use of high temperature electrolysis in refineries, and we will work in order to pave the way for further upscaling steps to the 100 megawatt scales. And finally, as far as social objectives are concerned, it will contribute to increase the awareness of this technology as a viable solution within electricity-intensive industry. It will also take care about the procurement strategy for renewable energy and also to the certification of the green hydrogen according to Certify. Next. Yes, and if we consider those objectives as compared to international state-of-the-art, so you could see here again that it will be the world's largest unit, longest demonstration phase, best efficiency values in field, as well as for the degradation rates, and also CAPEX and OPEX in agreement with the MOP targets. And finally, for the Certify activity, it will be the first hydrogen certificate for this technology. Next. So now if we look at some progress, some project progress, let's start with the stack performance and durability, which is part of the project performed in the lab with two different technologies. So first we started to define a testing protocol, which is a public document, including initial performance map durability step with also on-off load cycles, thermal cycles. Two technologies are considered, Sunfire electrolyte supported cell stack and CEA cathode supported cell stacks. And you can see here the result obtained on the two technologies, more than 8,000 hours with the Sunfire stack, more than 500 hours with the CEA stack, which is still ongoing. You could see that there is no degradation of the production loss with the strategy which is considered in the project. And the results achieved are the longest test for both technologies with current density in a quite interesting range between 0.5 and 0.85 amperes per centimeter, jointly with a high steam conversion. So it really brings understanding and evidence of the potential of this technology with quite high current density and steam conversion. Next. Second important part of the project is the module development and validation. So far, generation 2, 230 kilowatts, 60 stack module has been put in operation by Sunfire. They started by the engineering and optimization and tested this first prototype. It was efficient in order to evaluate the manufacturing duration. And then they are in the phase of the release of the design for the Multiply project. So this first evidence was successful to freeze the design of the hot and cold hotbox. More than 60 normal cubic meter of hydrogen per hour was produced as planned, with a very homogeneous temperature and voltage in the stack. And now the manufacturing of the Multiply units is in progress. Next. So in parallel, there are some work in order to prepare the site and the demonstration. So engineering and site preparation is ongoing for the startup in the second half of 2022. Auxiliary units are on tracks as far as design, manufacturing and commissioning as concerned. It includes dryer, compressor and buffer tank. We also worked in order to define in detail the service and maintenance concept. Also, the sourcing of the renewable electricity is planned. And as I said before, the work on the guarantee of origin for hydrogen in relation with certified and local Dutch policy is in progress, especially with the analysis of the draft RED II implementation impact on the Netherlands guarantee of origin. And finally, there is a draft methodology for the greenhouse gas avoidance, which is under discussion within Certify Working Group number 2. Next. So what are the risks and the challenges for the project? The risks are, let's say, about the delay, which might be related to longer manufacturing duration or delivery time. A contingency plan has been put in place with different options, as you could see, including the start of the modules at half of the capacity to start. Then the other risk is related to the implementation of a new technology in a new scale. And we can say here that a detailed risk management is in place with planning the installation and commissioning phase to ensure a smooth startup. And we faced a challenge in the procurement of a third-party stack, which was targeted for benchmark in the lab test performance characterization. It was not successful to find a third-party stack, so we decided and we proposed to test a new Sunfire stack design in replacement. So all the risks and challenges are mitigated. Thanks. Next slide. So regarding the exploitation, we can say here that the project partners are on the whole value chain, each having its own stone. Neste is the end user where the installation will be placed. Sunfire is the developer of the high temperature electrolysis technology, Polvurt for the hydrogen processing units. NG is, let's say, in charge of renewable energy purchase and certified, and CA, on top of the coordination activities, is taking care of the laboratory stack testing and of the dissemination. Regarding the impact, a preliminary market analysis has been performed and sales forecast also for each individual component performed by Sunfire. Next. And the last slide is about dissemination and communication activities. So a website exists that you can see here. We had a quite high number of visitors. We also updated regularly the website with some newsletters and leaflets. And the project has been presented at different workshops and conferences as far as it was possible considering the COVID-19 situation. And we have a table, as you can see in the right, to check the actions realized as compared to our plans. I think it's the last slide, so thank you for your attention.
Thank you, Julie, for your presentation. This is going to be a very important project. There are some questions in the chat. Someone is asking, what is the envisaged maximum stack capacity or power? I did a bit of arithmetic. I think 133 kilowatt module with 36 stacks. That makes 3.7 kilowatt per stack. Is that right?
Yes, I think it was written on the slides. It's 3.3 kilowatt for the Sunfire and 2.7 kilowatt for CA stack as far as the laboratory phase test was performed. So let's say, to make it short, around 3 kilowatts.
Around 3 kilowatt per stack. Great, thank you.
The two calculation of 3.7 is correct if you make the calculation for the 230 kilowatts module.
Right, and there is another question. Does the electrolyzer equipment constitute a hazardous area or zone?
You mean for safety?
In terms of safety, yes, I guess this question has to do with safety. Placing an electrolysis in a building, are the electrolysis stacks placed in this area or zone?
of course, it is really part of the work which is carried out to prepare the site and the demonstration. There is some safety analysis performed, I wouldn't say every day, but most of it is every day indeed. There is some HAZOP and hazard analysis and some compliance with the local regulations in order to take care about the hydrogen use, storage, vent in case, and whatever. So,
right. Thanks very much. This is what we're seeing also in the low temperature electrolysis projects. Safety is paramount because we are also inside an industrial area.
Absolutely.
Thank you very much, Julie. Let's move on to the next presentation, which is the Green High project. We have the coordinator of this project, but also of the previous Green High project, Mr. Simon Kropp of Salzgitter, who is also accompanied by Mr. Konstantin Schwarze from Sunfire, in case there are technical questions on the electrolyzer. So, Simon, the floor is yours.
Thank you, Nikos. Yes, let's move on to the presentation, please. Okay. Yes, let's talk about the first high temperature electrolyzer of the megawatt class, operated at Salzgitter's Iron and Steel Works. Let's talk about GreenEye 2.0. In GreenEye 2.0, we've manufactured and are currently operating the world's biggest high temperature electrolyzer. For now, as we just heard from Julie, we are using directly steam from waste heat of the steel production. And by doing so, the electrolyzer produces most energy efficiently hydrogen by also using green electricity. The prototype at Salzgitter is fully integrated into the infrastructure of the steel production. And the hydrogen produced is injected into the existing pipeline to the processes of annealing and hot dip galvanizing. And last, with our long-term stack testing, we will set new standards in the validation of SOEC technology. Next slide, please. Let's have a quick look at the project overview. We started in January 2019. The project duration is 4 years, what leaves us with an implementation of more than 70%. The project budget is about 6 million euros, and we'll receive at the end of the project an EU contribution of 4 million euros. Next slide, please. The project consortium consists of 6 companies from 4 different EU member states. First, there is Sunfire, who manufactured and maintains the high temperature electrolyzer. Then Paul Wood engineered and assembled the hydrogen processing unit for compression and drying. Tinova implements a study for a hydrogen-based low CO2 steelmaking route in Europe. Then there is CEA, conducting intensive long-term stack tests. And last, there are the 2 companies of the Salzgitter Group. Salzgitter Flachscher is responsible for system integration, operation, and regular maintenance. And Salzgitter Management Forschung, we are responsible for coordination and lifecycle assessment. Next slide, please. Okay. In the next slides, I'll present to you the progress of our operational targets. The chart on the left side shows you for the last 3 months the hydrogen that has been produced and injected in the orange line, next to the electrical efficiencies of the high temperature electrolyzer. Since November, you can see the small gap in the chart. 7 out of 8 of the electrolyzer modules are now operational, which increased the production rate from 90 cubic meters per hour to a maximum right now of 180 cubic meters per hour. With an electrical efficiency of 84% based on the low heating value for 1 kilogram saturated hydrogen at atmospheric pressure, we also reached the electricity consumption target of the FCHJU for 2020. In the slide, you can just see a small peak showing that we reached the 84%, but I can assure you right now, the system is operating at 180 cubic meters per hour, and we are constantly reaching this efficiency target of 84%, bringing the electricity consumption to lower than 40 kilowatt hours per kilogram. For saturated hydrogen at 1 bar pressure. Yes, from the beginning of September to the beginning of November, we had also the longest period that complied with the threshold of 95% availability. That were about 1.5 thousand hours steady operation. Since May, we reached an impressive overall availability of 80% on system level. So at 80% of the time since May, we are producing and injecting hydrogen. Next slide, please. Okay, let's get to the next two objectives. Since the beginning of commissioning in the first quarter of 2021, we produced and injected more than 32 tons of green hydrogen in about 5,000 operational hours. To reach the objectives by the end of 2022 that you can see in the table, we need an average availability from now on of about 84%, with an average production rate at those times of 120 cubic meters per hour. So as we can see right now, we are absolutely in line with our goals, and most probably by next year this time we already have gotten those goals. Yeah, next slide, please. Last, there is our 20,000 hours stack testing objective. Unfortunately, an incident with the building infrastructure destroyed the first stack that was already operational for 4,500 hours. The new stack, as shown in the chart in the slide, was installed in March this year and is operated for 5,000 hours now. Due to the incident, we will reach a testing time of about 13,000 hours by end of the project. However, there are also some good news, and those are the low degradation rate from the second stack. They indicate a very low production loss rate of less than 0.5% per kilo hour, which is quite impressive. Okay, next slide, please. And now to close my presentation, I'd like to provide some more information about the project in a video that we created during the visit of Bad Bibuk in June this year. And with a big thank you to the FCH.JU for the support. Please start the video, and also I'm happy to answer your questions later on. Welcome to Salzgitter. Right now we are standing in front of the world's largest high temperature electrolyzer of the GreenHy 2.0 project. GreenHy stands for Green Industrial Hydrogen, and the electrolyzer is fully integrated into the existing infrastructure of the integrated iron and steel works of Salzgitter Flachstahl. Based on steam from waste heat of the steel production and based on green electricity, we are producing most energy efficiently green hydrogen. With us today is the Fuel Cells and Hydrogen Joint Undertaking, which is also the funding agency of the project.
The ambitious GreenHy 2.0 project demonstrates how with green hydrogen we can successfully decarbonize hard to electrify sectors such as the steel sector and use the waste heat of the high temperature industrial processes. We are very proud to see that European players are leading this technology, and also that the FCH.JU enabled to build the biggest demonstrator of high temperature electrolysis.
Our Sunfire high-temperature electrolyzer uses the innovative solid oxide electrolysis cell technology. The electrolyzer uses steam and renewable electricity from sun, or in this case wind, in order to produce green hydrogen. The electrolyzer is operated at 850 degrees Celsius, and the fact that we can use steam in the system allows us to reach record efficiencies of more than 80% on the full system scale. This allows us to reduce the amount of renewable electricity in order to produce the same amount of hydrogen as competing solutions use.
Green Greenheit 2.0 prototype consists of two parts. The first one is the Hylink HL200 prototype that produces up to 200 cubic meters per hour hydrogen, and the second one is the hydrogen processing unit. The HL200 unit consists of 8 modules. Each module produces between 20 and 37 cubic meters per hour hydrogen. It can be individually controlled to follow the load requirement of the customer. The modules receive steam from the Salzgitter iron and steel works and split it into hydrogen and oxygen at a temperature of about 850 degrees Celsius. After it is compressed and dried in the hydrogen processing unit. The electrolyzer prototype is intended to run for more than 13,000 hours by the end of 2022. It should produce more than 100 tons of renewable hydrogen. It's intended to achieve an electrical efficiency of more than 84%, what is a world record in electrolyzer efficiencies. The system is developed and operated in a close collaboration between Salzgitter, Sunfire, Paul Wurth, Tenova, and the research institution CEA.
Since March, the system was operational for more than 2,000 hours and produced more than 15 tons of green hydrogen. Today, the hydrogen is used for the processes of steel annealing and hot dip galvanizing. However, the future role of hydrogen is way more essential for the future of steelmaking itself.
As the steel industry will transform from a highly CO2 emitting industry today to something that is not emitting any CO2 tomorrow, we're going to need hydrogen, predominantly green hydrogen, as a starting point, because the hydrogen will replace the coal in the whole steel making process. So without green hydrogen, no green steel.
Right.
Right.
Thank you very much, Simon. I guess this wraps up your presentation. Nice video as well. We have 2 questions. One, I think it's for you, and another one is for Konstantin. The one for you is the $1 million question on your estimations on the cost of hydrogen per kilogram.
Okay, my estimation. Well, for now I can say that we have the target of €7 per kilogram in the project, and well, it's highly depending on electricity prices, which are quite high right now. Everyone can imagine. But at the very beginning, we were definitely matching this target. I think what's possible is around €5 right now, and with those, but as we speak, with those high electricity prices, it's definitely difficult to get to the €7.
Right. And I think this question is very much related to what would be the value of green steel, and whether a client would be willing to buy a car that is slightly more expensive because it is built with such green steel. So thank you for your estimation on the cost. And a question for Konstantin. What are the conditions that the solid oxide electrolyzer cells are operated at? Parameters as temperature, current density, etc. And what is the degradation rate?
Thanks. Yes, operating temperature for our cells is between 800 and 850 degrees C, roundabout, and at atmospheric pressure. So maximum like 50 millibar gauge, so almost atmospheric pressure. And the current density at nominal load is 0.52 amps per square centimeter. We can also go to overload to something like 0.65 amps per square centimeter, but that's only possible during the first, during beginning of life for the cells. And the degradation rates should be in the range of what we see in the lab tests. So at something about 12 milliohms per 1,000 hours. But up until now, we have no, let's say, significant or relevant degradation calculations for the system.
Excellent. Thank you very much for this. There are more questions which I think we might be discussing later on. It's time to move on to our third presentation. We have Dr. Alberto Pilenga from the Joint Research Center of the European Commission, who will be talking to us about an effort that he and George Tsotridis undertook over a period of 2 years with great patience and lots of expertise going into there in developing testing protocols for low temperature electrolyzers. Alberto, the floor is yours.
Okay, thanks Nikos for the invitation. Yeah, indeed, I'm not going to talk about one specific project in this case, but the activities done by JRC. Oh, thanks for the presentation. About the pre-standardization activities that is would not be possible without the result and deliverables that has been provided by the many projects funded by the FCA-JU. So please, next slide. So about the harmonization objectives, what we have, we talk about a creation of a common accepted set of testing protocol and procedures that are to assess the performance and durability of the water electrolysis devices. We are talking about low and high temperature. In this case, the work has been done for the low temperature. And this work is not intended to replace existing practice, but is to allow a comparison of results. Because historically, one of the main projects was to be able to compare the result and to give a proper judgment on the effectiveness of these results. And so the reason is now the idea is to make a set of common operating conditions. The presented sets of documents are proposed to be used whenever is possible by the different projects in order to be able to allow to compare the result. Next, please. So the methodology, as Nico said, was a long work and started with the identification of an expert panel that were experts working for the different FCA-JU project or also among OEM manufacturer or final producer. And so the main requirement has been identified for the terminology documents, because also terminology can be different, and then procedure for low temperature water electrolyzer and testing procedure for high temperature water electrolyzer. So then the work of GRC was to draft a documentation, gathering the information, as I said, coming from the different FCA project, from the expert feedback, and also taken from existing standards or other metrology institutions. So here there are a list of different projects that has been used to gather information and testing procedure. We said also about, in total, we were in contact with 150 experts for both low temperature and high temperature document. And yeah, the reference has been taken also by ISO document, IEC, and SOE. When the work was drafting this document, and after a series of revision submitted for the final public stakeholder consultation under the FCA-JU website, and then the final version published are available now in different websites that are, the link is given in the presentation here. So it's on the Europa library or GRC library, or also in the FCA-JU website. Next, please. So the documentation prepared till now, we have different things. So starting from a testing procedure, a specific testing procedure like the polarization curve, cyclic voltammetric test method, electrochemical impedance, and a first document about terminology related to the low temperature electrolysis. That was work done until 2019. And now the work for the low temperature harmonization, the scope and needs. Scope is to define testing protocol, as is said, for assessing performance and degradation, and related to material testing, single cell testing, stack testing, up to system testing. And yeah, as we said already, the objective is to compare results from a different experimental campaign and using real life conditions. So we follow a top-bottom approach because with a new electrolyzer, we are working not anymore like in the past in steady state condition, but following the electricity variable profile. So the conditions are more critical. So for the use selection of this transient profile, we took profit of the work done by Polygrids, so that we developed specific pre-qualification profile for the qualification of the electrolyzer application on the grid. Okay, for this work, we found some critical part in the definition of the accelerated stress test, because there are a variety of them, and it's not easy to find an accepted uniform solution. And also about the off-grid load profile, because okay, there are also in this case a variety of combination of how the electrolyzer is operating in an Icelandic configuration. Next, please. So the content, as I said, we have a definition for functional properties for materials and definition of for different parts, so membrane, electrocatalyst, and so on. And I forgot to mention that for low temperature electrolyzer, we talk about different three technologies. So PEM electrolyzer, alkaline electrolyzer, and anion exchange membrane electrolyzer. So then what we have, one of the important part of the work is define this reference operation condition where it is possible to make the test to compare the result. So for each technology, it has been identified a set of operating conditions. Starting from this operating condition, also we identified a series of stressors that is a change of this parameter of this condition to see how the electrolyzer is behaving at lower temperature or higher temperature compared to the one that are on the reference one. And finally, there are also the tests defined for the system. So based on conventional energy supply or renewable energy supply and mainly on grid connection, so to define the performance test. Next, please. Yeah, as said before, also the indicators, KPIs are important. So we define in this document a series of indicators for performance. So whether you can see here, and for degradation, and also how to express this result in the form of this spider or radar graphs. Next, please. As you said, also it's important to consider what is the real application of the electrolyzer in the field. So based on the Polygrid project, we developed a series of protocols and the load profile based on the frequency containment reserve profile or manual frequency restoration reserve or replacement reserve. Here we have just an example of the frequency containment and automated frequency restoration reserve. The idea is to use the same profile for the degradation. So to repeat this profile for a certain number of cycles of hours, and then to measure the degradation. For the accelerated stress test, as we said, it's not easy to find an accepted solution, so we just proposed two simple profile. One is for flexibility, so where we change the current instead of 25% with a time of 15 minutes, so going up and down from 25% to 100%. And one to measure the reactivity of the membrane or the system, that is again with steps of 25 up to 100%, but in a shorter time. So each period is of 60 seconds. Next, please. Yeah, so this work is contained. All this data are reported in this document, and it was published this year. And we have also prepared a new document with terminology that is also including the high temperature electrolyzer. And the follow-up for next year is to prepare a document also on high temperature water electrolyzer testing. And the idea is to, the GRC will prepare a preliminary proposal by the end of the year. And then beginning of next year, we should start the discussion with the panel of experts. Next, it's important for us to receive your feedback. So if you can use these protocols and provide the feedback, because nothing is written on stone, we can modify and improve our document. And then I would like to thank the FCA-JU for the financial support. Again, all the experts that they provided a huge contribution on voluntary basis. So, and then last but not least, but to George Sotridis, it was one of the starters of these activities and the mentor for this work. Darina Bulagoeva, Giancarlo De Marco, and Thomas Malkov, that are also author of the other document. And the last but not least, also Mark Stein for his huge work and support for the preparation of the final document.
Great. Thank you very much, Alberto, for this presentation. Yeah, I mean, it's very important in this era of new electrolyzers that can operate dynamically to have such a method of testing their dynamic performance capabilities, so that we know we're comparing, apples with apples. At steady state, we can measure things like the efficiency, pressure, and stuff like that. But in dynamic operation, this is very important. That is why we are making reference to these testing protocols in all the topics that we publish. I noticed that originally the plan was not to go into standalone renewable electrolysis systems. However, I see now that under the Clean Hydrogen Partnership, we will be supporting the development of such systems, and maybe we will need to revisit this point. I know that the plan for next year is doing the same thing for high temperature electrolyzers, but maybe indeed we need to start thinking of standalone systems again. Thanks very much. I think we should be moving to the next presentation. I would like to invite Ms. Dana Dutianu from the Climate Infrastructure and Environment Executive Agency, CINEA for short, to present to us the scaling up of electrolyzers under the Green Deal call. Dana, the floor is yours. We can't quite hear you.
Thank you so much for this opportunity. Is this fine?
Yes, this is fine. Yeah. Perfect.
And good afternoon. My name is Dana Dutianu. I'm a project manager in the Horizon Europe Energy Unit of the European Climate Infrastructure and Environment executive agency. My presentation will focus first on an introduction of SINEA, just to understand the context, and then on an overview of our new hydrogen projects addressing 100 megawatt electrolyzers supported under the Green Deal topic, which was opened last year. Next slide, please. Next slide, please. The SINEA, briefly, has been established by the European Commission and started its operations on 1st of April 2021. It is actually the successor of the former Innovation and Networks Executive Agency, and also integrated the Executive Agency for Small and Medium-Sized Enterprises on what concerned energy topics and environment topics. In this way, SINEA combines the legacy programs like the former CEF, the Horizon 2020 program, however, adding the new ones and making in this way SINEA as a focal point for green projects and infrastructure projects. The key role of SINEA is, of course, to implement a large portfolio of projects covering the Green Deal policy and all the strategies around, and in this way providing feedback on program implementation to different European Commission's Directorates General, in fact 7 such Directorates General, like DG Mobility and Transport, DG Energy, DG Research and Innovation, Climate, Environment, Maritime Affairs, and Regional and Urban Policy. Just a brief, let's say, overview of the current programs. Apart from the Horizon 2020 and CEF programs, which have been managed previously, we have currently the Connecting Europe facility, the Horizon Europe, those parts dedicated to climate, energy, and mobility actions. We have the Innovation Fund program, LIFE program, the Just Transition Mechanism, the Renewable Energy Financing Mechanism, and the European Maritime Fisheries and Aquaculture Fund. Next slide, please. To do this, the budget is quite consistent. Last year we had 34 billion and it will reach almost 60 billion by 2027. Of course, this is supported by an increasing of the staffing from 300 staff last year in 2020 is expected to have 500 by 2027. And the most important, of course, is if the level of portfolio, which will reach about 4,500 projects by 2027. Here on this slide, we have, in a nutshell, the key contributions to European Green Deal, which is also a key mission of our executive agency, and we can highlight policy feedback to the European Commission on the projects and the program implementation results. Then we can highlight the synergies which we intend and we have and we further intend to create across the world programs. And here it might be also synergies with the joint undertakings. And also everything is based on a strong expertise in managing the complete life cycle of projects, and I dare to say many of them very complex projects. Next slide, please. So we have here the key contributions to the European Green Deal. In a way, they have been covered in my presentation. I would like to ask for the next slide, please. Okay, I will start by giving an overview of the context of the hydrogen projects supporting 100 megawatt electrolyzers. A bit of history, if I can say so. Last year, the European Commission opened the topic on one of the Green Deal calls was related to the topic on development and demonstration of 100 megawatt electrolyzer, upscaling the link between renewables and the commercial and industrial application. This was, of course, a very strategic objective to demonstrate energy system integration through hydrogen, and especially this key aim, key objectives to produce hydrogen from using rests of green hydrogen. So the challenges were obviously linked to climate neutrality, and also considering that today the technology is only available at multi-megawatts, and to reach a gigawatt scale, as the strategic objectives are envisaging, the development and demonstration of 100 megawatt electrolyzer is a key activity. This will help to create economies of scale, leading to further cost reduction. In this way, we expected that the proposals addressing the electrolyzer, 100 megawatt electrolyzer, will develop larger modules, managing efficiently the input power, the output hydrogen and oxygen streams, and the heat flow, ensuring the reliability of the system and reducing the footprint. Then we expected project to assemble the modules into 100 megawatt electrolyzer system, and then testing and demonstrate this system in real life conditions with operating flexibility. The aim was to harvest maximum renewable power and provide grid balancing services and supplying renewable hydrogen to commercial and industrial applications. Of course, what is important for such big project is to demonstrate the future economic viability of such technology, depending on cost of electricity and hours of operation employed by electrolyzer, and also assess the performance and durability of the electrolyzer, and including potential safety issues. Last but not the least, the environmental performance was a key issue of the system, and also other ecological and societal benefits along the whole EU value chain. As you can see, this kind of activities and the supported projects, the expected at that time projects, aim to contribute, to create a direct contribution to the European Green Deal, and to confront the climate crisis, in the same time to address the challenges of Europe's recovery, and to contribute directly in this way to the recovery plan for Europe. The call for proposal ultimately aimed to get clear results in the short and medium term, embedding them in a long-term change or potential change. In this way, we aim to have not only very solid technological developments, also visible actions with a clear focus on rapid scalability and dissemination and uptake. Following this call, we received 16 proposals and 3 have been selected. Next slide, please. The 3 selected proposals are Green High Scale, Green H2 Atlantic, and RIFHYNE 2. If you can see, as you can see, the supported project have a very strong focus on industrial implementation. 2 of them are focused on alkaline electrolyzer, 1 on PEM electrolyzer. I say industrial because they are really connected to industrial or local sites. And one of them, RIFHYNE, actually continues the successful implementation of the project, which are currently still running within the joint undertaking portfolio. Next slide, please. Now, of course, the project just started, and there are no tangible, let's say, results yet. However, an overview of the project could be easily done, and especially to highlight the ambition of those projects. So Green High Scale is looking to develop a multi-megawatt alkaline electrolyzer platform with factory assembled and pre-tested modules, 6 megawatt modules, reaching a capex below 400 euro per kilowatt by the end of the project. The project is led by GreenLab Skive, and contains 11 participants from Denmark, France, Norway, and United Kingdom. It is a 5-year project which started quite recently on 1st of October 2021. And its ambition is to generate green hydrogen for 2 years from 80 megawatt directly connected renewables in combination with certified green electricity from a TSO grid connection. You have on the screen also the ambition of the project, which will be, I'm pretty sure will be reached, and also some indicators aiming to reduce the cost of hydrogen below 2.85 euro per kilogram, depending on an electricity cost of 40 euro per megawatt hour. Next slide, please. The second supported project is Green H2 Atlantic. This is a project coordinated by EDP Renewables and intends to demonstrate 100 megawatt alkaline electrolyzer in Sines, Portugal, leveraging scale-up standardization and manufacturing automation. This is very innovative concerning some interface system which are composed of advanced power electronics. They will allow for a direct coupling of the electrolyzers with local dedicated hybrid solar and wind renewable energy. This project, which has a duration of 72 months, will intend or aims to reduce the cost, levelized cost of hydrogen to 2.87 euro per kilogram and of green hydrogen, and also to overcome some challenges related to capex, and also to have input on regulations, European regulations, and harmonization of policies. The third one supported, it's, as I said, it's a continuation of the current RIFHYNE. However, they intend in this new project to install 100 megawatt PEM electrolyzer to be seated in Rheinland refinery in Köln, Germany, using modules 5 megawatts electrolyzer modules. This is also a 5-year project with 8 participants and coordinated by SINTEF. And also the electrolyzer will be powered from renewable energy, especially from onshore and offshore wind farms and solar electricity.
Maybe we can move to the next slide, Dana. We're still seeing the green high. Yeah, that's refine.
Yeah,
great.
So you have here refine all the data. The ambition of the project is to demonstrate the potential of 100 megawatt electrolyzer able to decarbonize the operations of industrial sites and refineries. Also, they are looking to provide viable business cases for large-scale electrolysis at refineries by using the hydrogen and oxygen streams in the refinery. And this project, of course, builds on an existing, ongoing project, which is towards the final stage. And the team has already installed a 10 megawatt PEM electrolyzer at the same site. So the upscaling is natural, and we are looking forward to see very solid results as soon as possible. And because I raised this issue, you have to be aware that this call had a specific point. All the projects were requested to propose a go-no-go decision, a go-no-go milestone, a point ahead of entering the deployment phase. And before this go-no-go decision point, the project has to deliver detailed engineering plans, a complete business and implementation plan, and all the required permits for the deployment of the project. And then the status at that moment, which for some project is set up, let's say, after 1 year, for other projects after 18 months. So at that point, the status will be assessed, and a decision on a go or a no-go decision will be issued by us and endorsed by the Commission. So this is a very interesting, let's say, mechanism in a way to ensure that the projects are properly implemented, and there are clear milestones which could ensure that the project is really implemented in a very effective way and has big chances to deliver the expected outcomes and impacts. And so we discussed about the 3 projects addressing 100 megawatt electrolyzers. I have to also to mention that apart from these new projects in SINEA portfolio, we already have other projects involving hydrogen. For example, the ones in ports and airports developed under Horizon Europe, the transport part. In addition, the Innovation Fund small-scale call and also the large-scale call resulted in several projects involving production or use of green hydrogen, which are also currently in the very incipient phase in the grant agreement preparation. And also regarding the Connecting Europe facility, there are a total of 10 new projects related to hydrogen, which have been selected under the CEF blending facility. So maybe if you are interested, there is already public information about this projects, of course, take into account that they are in a very incipient phase. So you can keep an eye on the developments. All the projects are obliged to have a website, and also let's keep in mind that we are also obliged to create synergy with other initiatives and to provide visibility to these projects. So this is from my side. Thank you so much.
Excellent.
In case of questions, let me know.
Yes, thank you very much, Dana. That was, these are really exciting projects. We find these 100 megawatt are really very interesting. CINEA has been very kind in inviting the FCJU to follow these projects. And I had the opportunity to already join the kickoff meetings of 2 of those projects. We'll be very happy to provide any support, create synergies between our frameworks. And indeed, hydrogen is out there. It's in the real energy economy. So indeed, there will be frameworks like the ones mentioned by Dana, also supporting hydrogen energy technologies development and demonstration. Now, there is a question on who are the electrolyzer suppliers for the Green High Scale and Green H2 Atlantic projects. I guess that the person asking already assumes that ITM Power is the one providing the REFHYNE II electrolyzer.
Yeah, we have to, the projects are just in a very early stage. So, but thank you for providing an answer. For the other one, I'm, let's say, not in the position to say at this moment. So let's be patient and wait a bit.
Right, thank you for this.
Thank you.
Yeah, but I could say that with the exception of one of those projects, the rest of the electrolyzer OEMs we are familiar with and we have supported in the past, but there is one which has never looked at our frameworks, and that makes it also very interesting. Okay, so thank you all for your presentations. We had there is a question on the levelized cost of hydrogen for the REFHYNE II. Is there such an estimation in the proposal, Dana? The other 2 projects were just below €3 per kilogram.
To be honest, for this presentation, I used only public information. So there is an estimation in the project. However, I'm not allowed to make it, to disclose it. However, maybe because REFHYNE II is represented in this event, they can also answer. I'm pretty sure they have this amount. Yeah.
Yes, they are not in this panel at the moment, REFHYNE consortium, but fine. Okay, we will move on maybe with a question to Simon and Konstantin. Why was the availability of the electrolyzer rather low? I think you showed the figure of 80%. So we received such a question.
Okay. Yeah, I actually don't see it as rather low. I think it's a quite high number for, if you think about it's the first year of operation. And if you also think about that, the system that we have on site are prototypes. For one, the electrolyzer, but also for the hydrogen processing unit. Both units have been manufactured and assembled at different sites. Same as the infrastructure that was provided by Salzgitter and brought together at the beginning of the year. And since then, we had several smaller optimization topics to do. What in the end resulted to, again, from my point of view, an impressive 80% availability, if you think about it.
Right, so you think this is an improved figure compared to the Green High project?
The first Green High project, definitely, by far. And I can also say that we expect the system, now that it's really running smoothly, that we're definitely going to hit the target of 95% availability from now on, most probably, yes.
Excellent. Konstantin, would you like to add something, perhaps?
No, that was perfectly fine. The point is that all partners still have to learn lots about industrial operation of such systems, and that provides some challenges still. But anyways, these 80% availability is already okay, let's say, and we are confident to reach the 95% in the rest of for the rest of the project.
Right, and maybe I can ask, once you have the system up and running in temperature, do you tend to keep it at constant production, or do you also vary its production like you did with the GreenHy project, where it was also reversible and you could go into fuel cell mode?
Right. For this project, we are not going for reversible mode. But yes, we definitely will ramp up, ramp down the system also as demand or depending on the demand. For the GreenHy 1 project, it was less a topic because there we had just a maximum production rate of 40 cubic meters per hour. Now, by beginning of next year, we're gonna hit the 200 normal cubic meters per hour. And by then, we also have to be aware of the actual demand coming from the production side. Another point of view is, that with very high electricity prices also, which are fluctuating due to the renewable electricity generation, we also gonna have some restrictions on that end.
Right. Thank you, Simon. A question maybe to Julie. More general question on what you think are the most suitable industrial applications for solid oxide electrolyzers.
Okay, so there are two aspects. The first one maybe is, as I mentioned in my brief introduction, the fact that it's best for solid oxide electrolysis technology to have a heat source available in order to reach the high electrical efficiency that both Simon and me mentioned in the presentations. So saying that, a good option, of course, is to consider industrial sites having this kind of waste heat. That can be steel, that can be cement, that can be glass, that can be refining, and so on. And then, of course, it's useful also to consider industries which need some hydrogen or some oxygen or both. And for that, again, refining, steel, glass, and so on are good options. And then we can have some hybrid solutions, I would say, producing hydrogen on site with waste heat, and then, let's say, shipping or sending the hydrogen to consumers, which doesn't have the waste heat, but that needs the hydrogen, provided, of course, they are maybe not so far. It could be best. So, say sites with waste heat and, if possible, need of hydrogen or oxygen on site.
All right, thank you for this. And maybe on top of this, I appreciate that in the US and maybe also for France, there could be applications in integrating solid oxide electrolyzers with nuclear facilities.
Yes, I was only replying to your point with industry, but you're perfectly right. We need some electricity, and in case we want to reach the targets of 40 gigawatts in Europe, then we need a huge amount of electricity. Of course, renewable is very important, but maybe it's also an advantage in Europe to consider countries where we have low carbon electricity, and nuclear is one of them. And on top of that, of course, nuclear energy also provides some heat at a level which is compatible with the need for solid oxide electrolysis. Because maybe just to make it clear for everyone, we doesn't need a heat source at 700 or 800 degrees C. We just need, I could say, a heat source around 150 in order to produce the steam. And then it's a kind of trick in order to overheat the steam to 700 or 800. So you're perfectly right, Nikos, coupling with renewable, with the nuclear electricity for both the electrical part and the heat part can also be a very good option.
Right. Yes, I've heard concepts of bulk hydrogen production from nuclear and injection into the natural gas grids. Maybe a question to Alberto. Alberto, this is all EU driven because we always think that the European Union and Europe in general still has a lead in the field of electrolyzers. Have you seen interest in the testing protocols that you compiled from other parts of the world?
Yeah, indeed. We got some interested feedback even from China. So some also US. So you know better than me that also this electrolysis activities is also taken very seriously in US. So it can be of important. And also, as I said, the standardization for electrolyzer is done now under ISO. And yeah, I think DLR with Regin Reiser is doing the work. So for sure, there is an interest at the worldwide level.
Great, indeed. And like you said, there is an effort already to standardize these through the ISO committees. Thank you. Now, maybe moving on back to Dana, there is a question on how realistic you think it is to reach the 4 gigawatt of electrolysis target set in the EU hydrogen strategy by 2024, when all the 300 megawatt projects will only be implemented after this.
Okay, so I'm a person who really likes the step-by-step approach. So you need ambitious targets, which we have had, and we need a step-by-step approach and upscaling. So, and I think we don't discuss only on the 3 flagship projects. There are also other initiatives around who can contribute to this target. So let's do it step by step and in a wise way. And so not, let's say, distrust the target just because it's not realistic in the time frame. Let's do it step by step and we'll see if we can reach it, or maybe we should do something else in the meantime to reach it.
Right, indeed. Yes, I mean, these frameworks are there, facilitating frameworks, and we all wish and hope that eventually the industry and the real world market will overtake us eventually, and will start establishing commercial projects of this kind. But indeed, we heard during this week, Hydrogen Week, that the orders need to start flowing now for all the gigawatt scale production facilities that are being established to start receiving these orders and start manufacturing. Otherwise, indeed, we'll never get to the target. And there is one more question. What would a constant offshore energy production be attractive for hydrogen green production? Well, yeah, I think that would be quite obvious, but you can't have constant production from a stochastic energy source like wind and solar. But this is where also the advantage of electrolyzers comes into play, in that they are can operate dynamically and they can become ways to store energy from renewables. So I think we are coming to the end of this session. I would like to thank once more all our speakers for their contributions. I really hope that next year we will be meeting each other in person and with the audience. Thank you very much for the interesting questions that we received. And yeah, like I said, I hope to see you all next year in person. Bye for now.
Bye.
Bye, Nikos.
Right.
Hello, everyone, and welcome to this parallel session on next generation electrolyzers. We're just in a parallel session on electrolyzers in industrial applications, moderated by my colleague Nikolaos Limperopoulos, and now we'll be going to a bit of a lower TRL, smaller sizes, back to our laboratories as we're trying to prepare for the next generation of products. And we have some wonderful speakers here with us today that will be presenting 4 projects, 3 of which are on anion exchange membrane technologies, and 1 which is on high temperature solid oxide electrolyzers. So without any further delay, I can pass the floor to the first speaker, who is going to be Dr. Antonino Arico from the Institute for Advanced Energy Technologies in CNR, and will be talking to us about the progress they have achieved in Project Anione. Antonino, the floor is yours.
Thank you, Dionysis, for your kind introduction. Good afternoon, ladies and gentlemen. I would like to start by thanking the organizers for the invitation to present the Anione activities in the framework of this important event. Next slide, please. Anione is dealing with anion exchange membrane electrolysis, and the project was presented, the proposal for the project was presented in the call 2019, dealing with AM technology, AM electrolysis technology, and we have already reached the 60% of implementation stage for the project, and the total budget for this project is 2 million euro. And the project is coordinated by CNR ITE, the Institute of Advanced Energy Technologies in Italy, and we are also dealing with catalyst manufacturing and electrochemical testing in the project. The partners of the project are CNRS in France and Hydrolite in Israel that are working on developing advanced AM membranes. TFT in UK that is dealing with scaling up of electrocatalysts, and RD in Denmark manufacturing large area MEAs. Hydrogenics is assessing a stack, an innovative stack based on these advanced materials and components, and Uni Research is assisting CNR in project management and dissemination activities. Next slide, please. So regarding the project summary, Anione aims at developing a high-performance, cost-effective and durable anion exchange membrane water electrolysis. We aim to combine the advantages of PEM electrolysis in terms of high current density, high performance with the advantages of alkaline electrolysis dealing with non-precious metal electrocatalysts and non-critical raw materials. Our focus is essentially regarding reinforced anion exchange membranes, and these are developed in the project in combination with non-critical raw materials based electrocatalysts, and all these components are assessed in large area MEAs, and especially in a proof of concept that is a 2 kilowatt AM electrolyzer based on a cost-effective technology. Regarding quantitative targets, we are dealing with low energy consumption, less than 50 kilowatt hour per kilogram hydrogen, and also low degradation rate, 5 microvolts per hour at 1 ampere square centimeter operating current density. So the final goal is, of course, to contribute to a scalable production of low-cost hydrogen from renewable power sources through the reduction of capital costs while assuring high conversion efficiency and proper lifetime. Can you move to the next slide? Next, please. So regarding the project summary, I would like to summarize in this slide the main aspects, the main research activities carried out in this project. As already mentioned, our focus is on reinforcing the membranes. However, we also deal with non-critical raw materials-based electrocatalysis and innovative backing layers as gas diffusion layers. And these are integrated into a cost-effective electrolysis stack based on a flow-field-free stack design technology and not using any critical raw materials. Next slide, please. So here I would like to introduce some project results achieved in the first reporting period. We have achieved something like 1.9, 1.8 volts, a cell voltage at an operating current density of 1 ampere square centimeter using non-critical raw materials-based electrocatalysts and hydrocarbon membranes. And we have also observed a Faraday efficiency beginning of test of 99% and very good hydrogen purity at the cathode for this technology. Next slide, please. So regarding the durability, we have carried out several long-term durability tests at low temperature of 50 degrees Celsius, and we have observed in a long-term test of 2,000 hours steady state during steady state operation at 1 ampere square centimeter that we have a decrease of cell voltage with time. That means an increase of voltage efficiency. And this is due to the improvement of catalyst characteristics during operation. However, by the end of the test, we have also observed an increase of reversible losses and also a slight decrease of Faraday efficiency. And these are aspects that we are addressing in this mouse. Regarding the dynamic behavior, we have also observed good cyclability, good capability to operation in cycled mode between 0.2 and 1 ampere square centimeter. However, in this case, there is some influence from reversible losses, so the voltage efficiency is a little bit lower. Next slide, please. Regarding the operation with the diluted KOH, we have already, in all these tests, we have operated with 0.5 1 molar KOH solution recirculated through the system. We have tried to address operation with 0.1 molar KOH and pure water. However, we have a lower performance, especially using non-critical raw materials based components. These results have been achieved with this, under these conditions. And I think it will be interesting to compare the actual performance of our AM electrolysis technology with the PEM electrolysis results that we have achieved in various EU projects. At the moment, at the same operating temperatures, and in the case of PEM electrolysis, a precious metal loading of 0.5 milligram per square centimeter is used. As you can see, we have at the moment at 2 amperes square centimeter, we have something like 300 millivolt performance gap. And this is mainly associated to the polarization resistance. At the moment, we have achieved a similar conductivity in comparison to PEM, but still we have some issues to address a decrease of impolarization resistance, at least using non-critical raw materials. As you know, in PEM, beside precious metals, also titanium and perfluorosulfonic membranes are used. Next slide, please. So regarding the risks and challenges and lessons learned in this project, in the first period of this project, we have tried to achieve high performance by using thin membranes. Of course, we have also a strategy to address gas permeation by reinforced membranes, by recombination catalyst. Another relevant aspect is that our aim was to operate in a wide temperature range. And at the moment, at least for our durability studies, we prefer not operating above 50 degrees Celsius in order to keep good stability. Next slide, please. Regarding the synergies with the other projects, we have strongly collaborated with other projects, other FCH-JU projects dealing with the same topic, Newly and Chanel, and we have all together prepared testing protocols for assessing these systems. Together with these two projects, we have built an AM hub that can be accessed through our project websites. Can you move to the next slide? Next, please. Okay, regarding our website, Anione website, we have until now achieved something like 14,000 unique visitors, and we have really a good number of returning visitors. That is an amazing number of visitors. At the moment, we have published only a few papers, but we expect to publish more in the next months. And instead, we have presented our results in several conferences and workshops. Next slide, please. Regarding the exploitation plan and expected impact, we think that this project is a good opportunity for small, medium enterprises to develop and test their materials for this electrolysis technology in a proof of concept, in a, let's say, in a stack device. And of course, there is an aim to file new patents and also to progress on developing these materials. At the moment, we are addressing a 2 kilowatt stack, but we think that is a proof of concept of this technology, and of course is an opportunity for scaling up in the next years. Regarding the impact, as already mentioned, this technology is addressing a reduction of the capex, of the cost of the electrolysis technology, and also through achieving a high efficiency, also the OPEX cost. So in order to achieve the final goal of producing producing green hydrogen at competitive cost. And of course, this is the base for increasing EU competitiveness in the production of green hydrogen from renewable power sources at a large scale. I think this was my last slide, and I would like to conclude by acknowledging the FCH-JU for the financial support, all the partners of the project, and all of you for your kind attention. And I'm happy to answer your questions, if any. Thank you.
Thank you very much, Antonino, for the excellent presentation. While I wait for the Mentimeter to refresh so that I can have access to the audience's questions, I will ask you a few of my own. For the general audience, could you put in very simple terms the clear advantages that you see from your perspective of the anion exchange membrane technology compared to PEM and alkaline?
Yeah, this is an important question because, of course, the key advantage compared to PEM electrolysis is that in this technology, we don't have any precious metal electrocatalyst. We use a nickel-based electrocatalysts, and we don't have perfluorosulfonic membranes, so we do not need to deal with the fluorine chemistry. This is another important advantage. And the third advantage is that, of course, we don't use any titanium bipolar plates. We use nickel and steel in this technology. That means titanium was included in the critical raw material list of the European Union 2020. So this is now part of the critical raw material list. And of course, in this case, we use a cheap bipolar plates. So this is a clear advantage compared to PEM. Of course, at the moment, we have not yet achieved the current density that can be achieved with PEM at the same operating current density. And this is, our research efforts are addressing this aspect. Regarding alkaline electrolysis, of course, we think that this technology can operate with diluted KOH. And this means that we can really save, let's say, complexity in terms of balance of plant, in terms of managing this concentrated KOH. In principle, we can operate with extremely diluted KOH. And furthermore, since this is a zero gap cell with a thin membrane, we can achieve high pressure and operation at high current density. I hope I have answered the question.
I think you have been very clear. Thank you very much, Antonino. Now we have some questions from the audience as well. I would like to get to those. They're asking, what is the difference between the anionic concept compared to the concept of one OEM which is already in the market, and Apter?
The technology should be essentially the same. I don't have specific information about the Enapter technology. I know they are developing something like a few kilowatts systems that with modular technology, and of course this is a nice approach. And I don't have specifications in terms of operating current densities, efficiency, and so on. And also materials involved and costs. So at the moment, it is not easy to make a comparison.
Mm-hmm. Thank you very much. I have another question from the audience. Is there an interest from electrolyzer OEMs to consider manufacturing anion exchange membrane technologies? At what size and for which applications? And we have seen already in your presentation that you have one OEM already in your consortium, but maybe you could give us a bit more information.
Yeah, in our consortium, we have Hydrogenics involved as an OEM that is dealing with AM stack production. I think this is a good opportunity for Hydrogenics to develop another class, another type of electrolyzers that are similar to alkaline electrolyzers. So they have a good business activity in the field of alkaline electrolyzers. So I think they are really interested to progress also with AM. The advantages of AM have been already discussed. So I think this is the reason why we have Hydrogenics inside this consortium. But I know, I don't want to mention other, but I know several interests from several OEMs in this field. And I think this is a new technology. It is a technology for the future. I don't think there is a unique solution to address the goal of let's say 40 gigawatt per electrolysis installation in Europe at 2030. We need a set of different electrolysis technologies with specific advantages for different applications. I think if we can produce a cheap hydrogen from using this technology, the first market application is industry, the chemical industry. Hydrogen, gray hydrogen is used at the moment, widely used in the chemical industry, synthesis of ammonia, synthesis of methanol, and I think this is a nice application. Thank you.
Okay, thank you very much for the comprehensive response. And I would like to thank you also for your presentations. And now we can move on to the next speaker, which is Luis Colmenares Rauseo. I don't know if I pronounced it correctly. Apologies for any mistakes. Research scientist from SINTEF, who will be presenting Project Chanel. Very fancy name. Luis, the floor is yours.
Thank you for your introduction, Dionysis. Yes, thank you to the organizer for the opportunity to also to present a channel in the frame of the AEM technologies. I will today represent our consortium on behalf of our coordinator Tulil, which was not possible to do it today. Next slide, please. Yeah, similar to our colleagues Antonino explained before, channels. Could you move please to the next slide? Channel project is in the same topic that Anion is in the frame of the Anion HM membrane technologies. This is a project that will last for 3 years, starting the January of last 2020 until December of the 2022, with an overall budget of 2 million. I have this comment in the beginning, but the introduction of the Dionysus is under developed technology. We are basically develop new materials, taking advantage of knowledge from the more mature electrolysis technology. That's why we are moving material low between 2 and 3. The project, as I say, is coordinated by Synthes, but we had a partnership with Evonik, dealing with the development of the membrane polymers, membranes, ionomers, and Octave as the technology driver designing the electrolyzers prototype, the Forschung Zentrum Jülich, with the development of the electrocatalysis material for the oxygen evolution reaction, and the Norwegian University of Science and Technologies, NTNU, also dealing with the development of the electrocatalysis for the hydrogen evolution reaction. As you can see here, our main target is basically to prove the concept of the AEM technology in a cost-effective 2 kilowatt small stack AEM water electrolysis device, able to be operated at differential pressure. This prototype will be the configuration of the prototypes will be based in no PGM electrocatalyst. We are targeted to have performance the current density to 1 about or less than 1.85 volts, with an estimated cost of less than 600 euro for kilowatt. Next slide, please. In order to achieve that ultimate target, we had divided our work in the, I would say before, in the material development. Starting from the best in class from Evonik membranes, which are some kind of a membrane which had already some characteristic achieving the KPI determined the fortune for the fuel cell on hydrogen or the ticket and KPIs. And they will deal also with the development of the proper ionomer and optimizing the different characteristics and properties of such membrane to be implemented on the environmental conditions that required for the IEM technologies. In parallel, we also developed electrocatalyst material based in nickel based electrocatalyst in order to achieve higher activity and durability for the hydrogen evolution, oxygen evolution. And the process of the development of those materials will end up with the optimization of processing those materials and integrating those in single cells in order to learn about the process of the manufacturing process, in order also to achieve our technical target of less than 1.85 volts and apply current density of 1. As soon we optimize the integration, processing, stability of materials, membrane, electrocatalyst, integrations, and single cell. In parallel, we are also designing the stack where we will integrate those single cell in order to prove the concept with, how I say before, with a 2 kilowatt stacked platform. In the end, we try to achieve low-cost electrolysis and reduce capacity to the use of the no PGM materials, which are basically low-cost compared with the PGM ones. Next slide, please. So to give you a brief overview about our progress related to the material development, here I can present you the membrane ionomer development. As you can see here, we had some kind of workflow where we had a learning loop process during the different generations that have been developed in front of the channel by the Evonik regarding to the membrane utilizations. As you can see in the time frame, currently the project are in the month 24, where we had somehow already identified the optimal characteristics of the membrane that allow us to move to the next level. The basis of this membrane was, as I said before, as already achieving some key performance indicators, as you can see here in some table, just as preliminary a proof of the suitability to be used. We basically compare with the performance on PEM, as you can see here, where we can optimize or basically reduce the CapEx related to the PEM on these conditions is presented in this slide. So being sure that we were somehow develop robust membrane, we tried them to integrate the electrocatalysis having developed in parallel to that. Next slide, please. So we have during the development of this nickel-based electrocatalyst, our main target is besides the activity, durability, is also the scalability of those materials. I mean, the synthesis process that we investigate in the Forschung Zentrum Jülich on the NTNU is with the idea behind of be a process that can be cost-effective, scalable. Yeah. The characterization or determination of the best batches of these materials was done ex situ in RD configuration. At this characteristic, we basically look at 10 milliamps per square centimeter that the material had to achieve. In the case for the hydrogen evolution reaction, less than 150 millivolt over potential. And in the case the oxygen evolution reaction, less than 250 millivolt over voltage, as I can present here. As soon we assure that the synthesis process of this material is robust enough, we have reproducibilities of those synthesis process, currently we identify the optimal configuration from the hydrogen evolution material and oxygen evolution material. Currently, our project is in the process of producing a large, I will not say large scale because industrial level, but at least proving the production of the more than hundreds, I will say in general, more than 100 grams per batches. With keeping the characteristics of those electrocatalysts. Next slide, please. So identifying the best configuration or the best material related to the electrocatalyst or membrane, then we integrate those in a single cell. That is fully no PGN electrocatalyst, AEM electrolyzer from channel. As you can see here in the picture, we achieve our initial technical target at single cell level, the 1.85 volt current density of 1. At the same time, we investigate the durability of the single cell. In this case, is about 150 hours. But anyhow, this provides us very good information about the integration of those materials in a single cell. Next slide, please. Moving on in this process of the development, resource development, we also developed a modeling platform, a 1D transition AEM electrolysis model. Also to learn about, in parallel to the development of those materials, we try also to understand what kind of the process may happen in the operation with those materials regarding to the stability and durability. We was able during with our model to identify some local changes like local change of the pH, water concentration gradient that may induce some kind of the degradation mechanism during the long-term stabilities of the electrolyzer. The initiative of channel with this kind of the platform is to assume we come with some kind of the baseline knowledge that will be released. How you can see, the code will be released in GitHub in order to be able with the scientific community to make this kind of the model robust, learning from the different group worldwide related to the development of this technology. Next slide, please. Also, during this modeling, also we learning how we may operate the stack, which in parallel to the material development, our colleagues from Ignata have been designing the stack. We also identified another components of those, like the bipolar plate materials or the porous transport layer, in order to achieve some kind of the criteria, as you can see here, before and after some kind of the corrosion test that we have in channel project. In this way, we identified low-cost, durable materials to be used in our stack configuration. Next slide, please. Regarding to dissemination communication, similar to our colleague from Anione pointed out, we also have a different channel to disseminate, to communicate our results. Of course, in the first period of the project, having a lot of process of the development, not too much to bring outside. We expected during this last years of the project to publish more dedicated materials related to the development of the electrocatalyst, also related to a manuscript dedicated to the models. As in parallel, with another two AM projects, Ionic Newly, we create also with the support of the booster result, horizon results booster from the European Commission, we create an AM cluster with the idea to intensify the knowledge, make the community aware about this technology and the advantage, the potential disadvantage that they may have. In this way, the three projects, we join effort to communicate our progress, to make available our challenge, our next steps, also to disseminate properly the learning phase of what is behind of this technology. Next slide, please. So as summary, I hope that I showed you that during this period of the couple of years that the project have been already running, we was able to achieve statewide our key the development of our key components related to the electrocatalyst for the oxygen evolution or hydrogen evolution reaction, also the development of the AM membranes, ionomer, and also the integrations and manufacturing process of the single cells as a learning phase to be now integrated in our stack prototype. We will be now the last phase of the project. Parallel to that, we have been building a model to, as a learning mechanism, where we can simulate and learn about the different mechanisms that may affect the long-term stabilities of the AEM technology. Next slide, please. And the next slide basically is just to, what I already commented. The idea is through simulation or assessment of feasibility to try to see is under the channel configuration, we are able to achieve this less than 600 euro per kilowatt. Also to determine, the feasibility of the technology, and also to assure that all the value chain related to this technology is 100% EU supply. I think with this one, next slide, please. I want to thank all of you for your attention. Also, I want to thank you, the Fuel Cell and Hydrogen Joint Undertaking for the grant. Also, I want to thank all our partners in channel for the effort and very good proactive collaborations. And thank you, everyone.
Great. Thank you, Luis, for the presentation on the progress on Chanel. And we have a very engaging audience. So I would like to ask you a few questions from them. Yeah, the first question is about the temperatures that the hydrogen evolution reaction and the oxygen evolution reactions over potentials are measured. And then what temperature are you going to be measuring the 1.85 volt and 1 amp?
Yes, exactly. Thank you for this question. Also to remind me that I didn't forget about that. Yes, the actual single cell validation test was performing a 60-degree. Yeah,
Okay.
the screening of the electrocatalyst during the development of those, which was done ex situ in RDE configuration, was basically done at room temperature. But the actual validation single cell was done at 60-degree. Even so, we also have a temperature about 50 and 45 degree, which I didn't show here, but the currently one was in 60-degree. Yes.
Okay. Thank you very much for the reply. Going back a bit, let's say forward a bit to the cost projections that you have shown. How do you intend to calculate these this capex calculations, given that we are still at a TRL, low TRL, and what are your assumptions that you're taking into account here when you're going to be calculating this target?
Yeah, well, honestly speaking, it's quite a tough question for me, for myself. That is a target now that we will concentrate with the enactor concerning to, we need to design beside of the stack in our activity is just also to design the balance of the plant. Well, of course, with all this learning phase, we identifying the operation conditions that we want to implement in the stack. We need to take about also about the efficiency that they have, also the temperature that we apply. Also very relevant, I didn't comment to here, that now is a period that we will investigate the effect of the applied pressure of that. So all these kind of the parameters that have to be taken in account in order to make these estimations of projection of the cost. How you say, we are in very low TRL, but at least we need to start to establish some kind of the tool simulation mechanism that allow us to guide in the way what had to be optimized regarding to the operation condition, regarding to the materials itself implemented. Even so, as for example, Antonino already commented, we are using cheap materials, electrocatalyst materials, also bipolar plates, PTLs are a cheaper material, but beyond of that is also the balance of the plant. That's something study phase that we will now in this 2022 we'll try to identify the key parameters to try to assess in the proper way this cost target that we have.
Thank you very much. Thank you, Luis, for the reply. I have another question that will also be quite difficult for you to answer. It's from the audience, so I do want to take it. They're asking about whether Enapter and Chanel will be going into larger stacks in the future. And I know on the part of what Enapter is planning to do, it's a difficult question from your side. So let us know what you can reply to this.
Yeah, it's a difficult question because I cannot go in detail on behalf of the Enapter. Of course, as a startup company to push this technology, the ultimate target for those for this company, of course, will be go to this kind of level. There is some learning phase in order to identify the roadmap to go to this kind of the target. I will say I cannot go really deeper in that direction. I apologize for that. Most likely by the next year, when we more go deeper in the business development of this technology with the help of Enapter, I think once our deliverable will be public deliverable in order to provide a general overview about what could be the business case for this technology from the point of view of channel, of course, with the cooperation of the Enapter in aboard. Yeah. But yeah, I apologize that I cannot go so deeper in that
We understand. No problem. Thank you very much. And thanks again for the excellent presentation. With this, we can move to the next project, sticking into the three projects of anion exchange membranes. And I would like to welcome the next speaker, Dr. Aldo Gago, who is from DLR and will be showing us the results of project Newelly. Aldo, the floor is yours.
Thank you, Dionysius, and thank you for inviting me to present Newelly. So next generation of alkaline water electrolyzers with improved components and materials. I'm Aldo Gago, and I'm the coordinator of this project. Next slide, please. Yeah, here's some figures about the project. So it was submitted in the proposal and the call in 2019 in the call new anion exchange membrane electrolyzers. So the project started in January 2020 and will end in December 2022. Up to now, we could say that we are about 64% of implementation in the project. The total budget is it's about 2.5 million with a contribution of 2.2 million from the FCGU. And we have as well a partner from Korea, which is coming with their own funding of about almost 400,000 euro. The partners, you can see the logo there. Well, I'm not going to name all of them. Well, I'm going to explain later the roles of them. Next slide, please. Here you can see in a schematic the well-known polarization curves of the three low-temperature electrolyzer technologies, namely alkaline water electrolysis, anion exchange membrane water electrolysis, and PEM water electrolyzers. You can see, the FCGU funded recently some projects which aim the PEM electrolyzers to reach very high current densities. You can see the difference compared to alkaline that barely can reach 1 amp per square centimeter. So anion exchange membrane electrolyzers should be in terms of performance in the middle, more or less, as this technology aims to combine the benefits of both technologies, PEM and alkaline. So the low cost from anion exchange membrane by removing platinum group metals, catalysts, and coatings, and with the high performance of PEM electrolyzers. So ideally, and we hope one day can reach even higher current densities. But in NewELI project, our aim is to reach up to 1 amp per square centimeter and keep a cell voltage of 2 volts. So this is in our project, we aim to redefine the AEM electrolyzer concept and components, going higher in performance than alkaline alkaline electrolyzers, and bringing closer to PEM electrolyzers the performance. For this purpose, we are investigating, we're developing stable membranes, highly active electrodes and electrocatalysts for oxygen evolution reaction and hydrogen evolution reaction, and also membrane electrolyte assemblies. And we are going to go up to an area of 200 square centimeter active area in a stack, in a short stack up to 2 kilowatt. So as I mentioned, our aim is this 2 volts at 1 amp per square centimeter with pure water or 0.1 molar KOH electrolyte, which is much more lower than alkaline, which usually is up to 6 molar KOH. And we will aim to keep this performance in an endurance test of 2,000 hours in the stack. And at the end, we will have only 50 millivolts lost in cell voltage. Next slide, please. So here is how the NewELI consortium is organized. So we have more or less 3 teams investigating the 3 main aspects of this AEM technology. So that's the membrane and the ionomer development, the electrodes, and lastly the stack, which is a step closer to commercial status. And you can see the logos of three partners are a bit larger, and that's the membrane, the company Membrasense, in the electrode, the company Senmat, and in the stack, the company ProPulse. And then outside of these three teams, where we have a large company, which is Air Liquide. In our project, so we aim, this team the lead is these companies. They are all spin-offs of universities and research institutes. And that's why they are collaborating quite closely with the research and with academia partners to develop something that has a clear commercial perspective. Starting with the membranes, is the company Membrasense is overseeing this development. And then we have several partners. I mentioned Keys, some partners from Prague, from Czech Republic. And in the electrodes, we have CEA, TLR involved, as well as UCTP. And the stack is the spin-off company ProPulse, collaborating close with the FPK and WHS in Germany. So that's how we are progressing the project, going from TR level 2 up to TR level 4. And then on the left corner on top, you have a scheme of a cell. So the company ProPulse, they sell as a single cell test cell, and this is distributed to several partners. And this is the purpose, to harmonize the testing protocols as well as the testing hardware among them, so that they can achieve similar performance and we can have sort of a Robin test. And Air Liquide is there to oversee that all these developments have really commercial perspective, and they are in charge of doing cost analysis and life cycle analysis in the project. Next slide, please. So I show here some of the progress of the project. First, on the membrane. So the partners have developed a membrane type 1 based on hydrocarbon backbone with DAPCO functional group. And this membrane has a high OH minus conductivity, good mechanical stability. Well, this is basically the requirements that the membrane should have in the project. And the stability of the functional group in KOH, as is well known in AEM electrolysis. The KOH is mainly one reason of degradation of the membranes, as well as the partners need to develop an active binder based on the same chemistry. Up to now in the project, so there's been some achievements in this regard. So, for example, the tensile stress break, well, the Newelly target has been achieved, as well as tensile straight at break, the ionic conductivity, but still the area-specific resistance that they will not yet achieve the target. There has to be increased the degree of chloromethylations and also reducing the thickness. It's interesting that with even with thicker membranes, we can achieve the ionic conductivity target of the project. Next slide, please. And here I show some polarization curves from the measurements from the partners. So one of them, the Senmat, who is in charge of producing the electrodes with all the other partners, they have achieved already the target cell voltage, but not at 1 ampere square centimeter, but at 2 amps per square centimeter. And that's really quite close to PEM electrolysis, at least the commercial standard of PEM electrolysis, having non-PGM catalyst, both on the anode and cathode, and really with the low cost component and cell design. These electrodes are now, well, rather the catalysts are now commercial, so they're being already sold by Senmat to several partners. and they've been provided even for some of the two other AEM electrolysis projects. But the idea, well, is combine all the developments in the project, and on the right side you can see a polarization curve by the partner CEA with all the materials combined. So that is the membranes developed by the partners, as well ionomers and the catalyst from CERMAT. And in this regard, we are at 1.3 almost milliamps amps per centimeters at 2 volts, and this is ahead the project target. So in this regard, we are progressing, and there's been some durability tests already carried out, but I'm not showing this here. Next slide, please. Yeah, and on the other aspect, as I mentioned, is the stack. So the company proposed with other partners at adapting the stack that was developed in another FCGO project, Pretzel, and this stack has a patented novel technology, which is hydraulic compression technology, which allows to reach high pressures theoretically without any limit, but in the project will be at 40 bar, while maintaining a uniform compression along all the surface area of the electrode, as well as homogeneous temperature, and without putting stress on the components. You can see some schematic here of this stack that, well, in the case of the other project, had to reach 500 square centimeter. Here in the project is only up to 200 square centimeter and only 40 bar. And on the left side, you can see as well this single cell test device that they already commercialized. So all this is for PEM electrolysis, but in Newelly they are adapting their products for AEM electrolysis. Next slide, please. In terms of dissemination, it was mentioned in the previous projects, we are as well collaborating with them in this AEM hub. But one remarkable thing in our project is how productive have been in the publications. There are already 3 publications in peer-reviewed journals. And one of them was it's a review paper on commercial membranes. That's the number 2, and this is already the most read and downloaded paper of the journal. And this was a deliverable which has so high quality that the partners decided to submit it for a journal. Now it's a review paper. Next slide, please. Of course, major risk in the project has been, it's been affected all projects, is the COVID pandemic. So this has really decreased how we would like to progress and develop and put more energy in development, of course, because there must be more work in the laboratory, and as well the interactions with the partners, well, is not the same online. So yeah, we have some delays in our deliverables, milestones, and this we can attribute mainly to the pandemic. However, we have some difference, right? Compared how it's in Europe, in Korea, for example, there was no really lockdown, but we keep working even along the pandemic. And that was good because there was still progress in our project. Next slide, please. As I mentioned, having 3 spin-off companies sitting in the middle and taking care of the main developments in the AEM electrolysis technology is really very healthy and is working very well in our project, because they understand the need of the academia for publishing, for doing basic research. That's the TR level 2, but they really put in a direction and having a very clear lead role in that all this development, they don't stay only in scientific publications, but that they become patents, and then they are interested in licensing this patent. For example, Keith developed a membrane and then made a patent, and now Membret says he's very interested in licensing this patent. So that's really having a very positive aspect in the project. But then you have Air Liquide, which they are really demanding something that is a product that start giving a solution to the green hydrogen, and they are also calculating this cost for megawatt size electrolyzers, having the input from the spin-off companies regarding the cost of the materials they are using. So we really believe that at the end this concept is going to give very positive outcome. The impact of project, of course, this is an entirely almost new technology that is aimed to really will be better than the normal alkaline electrolyzers and getting closer to PEM electrolysis. No PGM materials, so there's no supply constraints. Aims to be low cost and ultimately will increase the EU competitiveness in the production of green hydrogen. Next slide, please. And with this, I would like to acknowledge the FCGU for the funding of this project and the partners for the remarkable work they're doing in the NewELI project. Thank you.
Thank you, Aldo, for the very good presentation and impressive technical progress, but also in terms of dissemination with a very good quality paper that you published. Also very nice to see the exploitation, the pool that you mentioned from the having high quality industrial, say, partners. And I have one question from the audience. I would like to, unfortunately, you were the last to present, so you are the one who gets this question. It's how complementary is NewELI compared to the two previous projects that presented? Could you outline us a few of the things that you believe are complementary to NewELI?
Yeah, so well, with this, actually, I have to thank the CGU, our project officer, Nikos, because, well, they are encourages to collaborate with the other two projects. So first, this AEM hub. So in this case, it makes us stronger disseminating the three AEM projects, and this combined the effort in Europe. We also have a workshop with the other two projects for setting common harmonized testing protocols for AEM electrolysis, and there was a lot of exchange of information with them, how they're doing the test, and at the end there was a sort of a document on that. There will be a second workshop, internal workshop on January. There was also a webinar on AEM electrolysis. So we are very complementary in that sense, in how we are disseminating our activity. And as I mentioned, we even started to exchange some of the results. One of our partners, Senmat, I know they send some, or they sold rather some of the catalysts to the other projects. So yeah, this rather than a competition seems to be really collaborating way with the other two projects.
Okay, thanks a lot. Seems like it was a good idea to proceed with all three instead of having separate lines of work. Thanks a lot, Aldo, for your presentation. And now we can move on to the next speaker. We will ramp up the temperature a bit now. We'll be going into high temperature operation, solid oxide cells with their promising versatility, and which is explored by Project Switch. The coordinator is Luigi Crema, who's the director of the Sustainable Energy Center at FBK, and will be walking us through the progress that they have achieved so far. Luigi, the floor is yours.
Many thanks, Dionis, for the kind introduction. Good afternoon to all the attendees. I'm thankful to the organizer for the kind invitation, and I'm glad to present today's Switch project. Next slide, please. Switch project started on January 1st, 2020, and it will conclude on December 31st, 2022, so at the end of the next year. At the present, the project is in a good progress with about and even more than 50% implemented without major delays. The total budget is around 3.7 million euros with a fuel cell hydrogen joint undertaking contribution of about 3 million euros. The consortium is composed of 7 partners from 5 countries. Fondazione Bruno Kessler from Italy as coordinating party, Solid Power and EPFL from Switzerland, Aigear and Shell from the Netherlands, DLR from Germany, and Sweco from Poland. FBK, EPFL, and DLR are supporting Solid Power and Aigear in modeling, engineering, and the lab validation of the single technology modules. Solid Power is involved on the engineering of the hot part, specifically the large stack module and the hot balance of plant. Aigear is therefore involved in the cold part of the system, as well as in the system integration and full technology validation. Shell is the end user involved in the final pilot testing, as Sweco is supporting on exploitation, while FBK on communication, dissemination, and management. Next slide. Switch is developing a novel technology using reversible solid oxide cells in a polygeneration mode that could guarantee mostly green hydrogen produced using renewables in electrolysis mode, but always secured using methane-rich mixtures and generating in a flexible way hydrogen, power, and heat. This is an important requirement, particularly for long-term hydrogen purchasing contracts, like in the rail sector, that must secure hydrogen supply on a daily basis to grant the service. Switch will be tested at the Shell Technology Center in Amsterdam. Next slide, please. By being always secured and by the specific key technology assets, Switch is aiming at becoming a key technology for the transition to a zero carbon mobility in Europe. The project has several goals, just to mention some: the security of supply by the flexibility of supplying green or low carbon hydrogen in several demand conditions, on the efficiency, having multi-source hydrogen generation that can maximize the green hydrogen production while minimizing the electricity cost. Sustainability, so targeting 65% CO2 emission reduction compared to the standard SMR technology, steam methane reforming. Then cost reduction, so targeting a final hydrogen price of 5 euros per kilogram hydrogen for about 40 tons hydrogen produced per day, as a total capacity of the deployed technology in the market. Flexibility, relying on multiple input sources and switching between the 2 operating modes during the daily operation. Next slide, please. So the Switch system uses alternatively renewable energy sources and methane-rich mixtures, including biomethane, to produce hydrogen in all conditions. The system, to make a short description, is composed of a fuel processing unit with a steamer and a reformer properly adapted in size and functions to the reversible process operation, of a hot part composed by the solid oxide fuel cell electrolyzer in form of a large stack module, and the hot balance of plant, including heat exchangers and the burner, among the other parts. The system is completed then with a cold part, including a compressor, water gas shield reactor, a PSA as a purification unit. The PSA has specifically been designed and developed to manage variable flow rates of hydrogen generated in both modes of electrolysis and fuel cell. All of these modules enabling cogeneration then of hydrogen, heat, and power, as already said. The system is innovative in the way it is integrated the several modular components and enabling a flexible operation with a proper mass and energy balance. Next slide, please. A first target of the project is to scale up the system capacity up to 150 kilowatt, 100 kilogram hydrogen day for reversible systems. This would comprise 2 solid oxide large stack modules involved in the pilot testing, each one with a capacity of 20 kilogram hydrogen day in solid oxide fuel cell mode and 50 kilogram hydrogen day in solid oxide electrolysis mode. The system will have then a total capacity of 100 kilogram hydrogen day and equivalent to 150 kilowatt in SOI mode. The prototype will be operated in a relevant industrial environment for at least 5,000 hours until the full validation of the foreseen performances. At the present, more than 300 hours of testing was performed at the DLR in reverse mode operation together for the larger stack module, together with additional 2,300 hours of hot rig operation at solid power and more than 2,000 hours in FBK on the single stack testing. The test at DLR confirmed a successful generation of 53 kilogram hydrogen per day, which is beyond the expected results. And it is visible here on the right, the thermoneutral performance matrix obtained. Next slide. The switch through thermal integration is aiming at a high conversion efficiency. The integrated gas treatment unit upstream of the solid oxide fuel cell electrolyzer recovers heat, generates steam, and pre-reforms the fuel. In the electrolysis mode, the efficiency based on the lower heating value is expecting to be 70% of the LHV, including electrical steam generation in the prototypal level. And this can increase at the second stage, including heat recovery from the steamer, for the steamer. The large stack module has been demonstrated at 90% efficiency based on the LHV, here not accounting the electrical steam generation, just the LSM efficiency. And in the fuel cell mode, it is expected to have more than 75% efficiency, accounting hydrogen, lower heating value, electricity, and useful heat co-generated. It is visible here, the picture with the efficiency map for the SOI mode for constant and variable steam utilization. Next slide, please. The call was asking for a partial load operation up to 30% of the nominal capacity. Switch in this can be fully dynamic in the range from 30 to 100% of hydrogen power production. The LSM can operate individually in 5 different modes, and the overall operating envelope include the SOI full load, the SOI partial load up to 30%, the SOFC full load generating at the same time 100% hydrogen and power, the SOFC 50% load, and the SOFC 100% power and 40% hydrogen. This support in different use cases were identified by the end user, applied to the business case developed. Next slide, please. Switch modules will be integrated in 2 40-feet containers, separating the hot part from the cold part and the power block. The system is integrating in an innovative way a complex technology, so starting from single module development to the final full technology integrated and validated. So there are indeed several sequential steps that could undermine the project in terms of schedule and results. This was evaluated among the risk and challenges, and to mitigate such, the consortium will move on a double way. First, taking all the previous experience and results from CH2P project that was working only on the solid oxide fuel cell mode. And secondly, anticipating as much as possible the final testing in lab validating the single key components and parts, including LSM, hot BOP, cold BOP, and the hydrogen purification unit. So arriving at the system integration with most of the risk at the component level resolved. Next slide, please. The project has prepared an exploitation plan finding the more relevant key exploitable results. And this was supported by the Horizon Result Booster service by the European Commission. In that workshop, 4 key exploitable results were identified and analyzed. They are the switch system as a whole in form of a multimodal reversible hydrogen production technology as a new product. They identified the exploitation route is direct commercialization by a year of the specific technology. The second is the large stack module as a new reversible solid oxide technology. This with the direct commercialization by Solid Power. The third was the flexible PSA as a customized technology for hydrogen purification with direct commercialization by a year. And finally, the flexible hot BOP customized for all fuel cell and electrolysis modes of operation with the foreseen licensing or direct commercialization by Solid Power. We collaborated in the HRB together with the other 2 projects supported by the FCHAU, so Prometeo and Multiply. Next slide, please. Switch is aiming to have a considerable impact on several end uses, in particular tools requiring a maximized utilization of renewables, but H24 operation needed. The project target application is directly that of the hydrogen refueling stations. Switch will target several use cases, considering the different demand profiles to supply hydrogen and the power to fuel cell and battery electric vehicles in a multimodal approach. This will address the mobility sector with the priority to rail, heavy-duty road, and ship transport, as well as involving potentially even multiple industrial sectors that would need at the same time decarbonization and continuous operation. For example, chemical industry, steel making, refineries on that. Next slide, please. Large attention has been given to the communication of the project and the dissemination to the potential several stakeholders interested. We have prepared in the project a visual identity, the website, brochure, video, all has been developed coherently with this strategy and included in a dissemination and communication plan. All the project materials are available at our website. Today in the website we add up to about 3,000 visitors. Next slide. At the end, I would like to acknowledge the Fuel Cell Hydrogen Joint Undertaking for the support granted and the partners for the dedicated efforts in the project progress. And I'm thankful for the attention and available to answer eventual questions. Many thanks.
Thank you very much, Luigi. Now I will briefly go over to our online friend, and I will ask you a question from the audience. We see that the application that you have targeted with Switch is hydrogen refueling stations. Do you see the lower power density of solid oxide electrolyzers as compared to PEM being a potential problem in this aspect? Do you see that there will be any lack of space or any of these sort of issues? Or is it already discussed with the industrial customer and you don't foresee any problems at all with this?
Yeah, we are trying to step into this issue in a double approach. The first is to have designed into the initial containers a really integrated modular technology. So trying to save space and volume for delivering the 100 kilogram hydrogen day in the two 40 feet containers. Of course, the density is an issue, and particularly when leveraging on hydrogen generation capacities of 1,000 or multi-thousand kilogram of hydrogen per day. This will be part of an engineering design optimizing further the integration layout. So the potential integration layout for the 1,000 and more hydrogen production, kilogram of hydrogen production capacity per day will be different from these initial modules. For the rest, considering the high efficiency, the flexibility in generating hydrogen power, the heat recovery that could be useful for particularly some applications. At the moment, even in the exchange with the end user, we are not foreseeing any major limitation on this.
Thank you, Luigi. As you mentioned, the several operation modes that the system can have, how quickly can you switch from one to the other? And what kind of advantages does this speed offer to the system? Would you be able also to provide, and with respect to the ability to operate part load, do you think that you would also be able to provide grid services on that, or is it not fast enough?
Yeah, this is quite a relevant, important question. If the system will be maintained on the hot standby in between the reverse mode from renewables to the utilization of the natural gas or methane-rich mixtures, the time for reversing at the nominal power will be lower than 30 minutes. Considering a high temperature system, this is quite a good result. We should be able then to reverse in 15 minutes from hot standby from electrolysis to fuel cell mode. Then the different modes identified by Shell are related to the potential use case by a hydrogen refueling station. So there are several business cases developed for the optimization of power generation when needed by the station itself, so avoiding import of electricity. This is evolving in an interesting business case and business model that is the reverse of the standard electrolysis mode. In this way, when the external electricity cost is high to take power from the grid, we can generate at the station locally or by the end use power from the system from natural gas at a high efficiency. And so the higher the cost of electricity from the grid, the lower the projected cost on hydrogen power generated locally. Then, of course, the grid services, not the frequency modulation, but maybe the voltage modulation or the consumption, one monodirectional consumption of excess of energy from power energy from electric energy from the grid. Of course, it could be supported by this technology, particularly in the SOE mode, and so this could grant additional revenue to the utilization of this module.
Okay, thank you very much for the reply, Luigi, and for the very good presentation. I think this brings us to the end of the time slot that we had. I would like to thank all the speakers for their excellent presentations, the good discussions. Also, a big thank you to the audience for being for engaging through Mentimeter. And yeah, the next session will be on hydrogen distribution and storage. So if you're looking, if you're interested in this topic, please stay with us and join us there as well. Thanks again to all the speakers, and yeah, see you soon.
Thank you. Have a good day.
Thank you very much. Have a good day.
Thank you.
Thank you. Bye.
Hello, everyone, and welcome back to another parallel session, this time on hydrogen distribution, storage, and hydrogen carriers. So my name is Dionysios Timis. I'm a project officer of the FCHGU, and I'll be moderating this session. And I have with me today four very experienced speakers that will be showing us results from a very diversified set of portfolio. So running across very different applications, but we will look at all the necessary tools that we need to enable the scale up of the logistical infrastructure for the hydrogen economy. And I would like to start right away by introducing the first speaker, Professor Marcelo Barrico from the University of Turin, who will be walking us through the progress made within Project HyCare, looking at hydrogen storage in metal hydrates. Professor Barrico, the floor is yours.
Yes, thank you very much indeed, Dionysius, for the kind presentation, and happy to be here to present the results of HyCare, and thank you to the organizer to allow me to be here. Maybe in the next slide, we have just a very short video. Okay, thank you. We can move to the next slide. Thank you. So this is just an overview of the project that is dealing with different partners from all around Europe. We started in 2019, and we were planning to end of this year, but because of COVID, we extended the project for we applied for the extension of the project of about 1 year. But let me go to the concept of this project. So in the next slide, we basically have an idea of what is the idea to the main goals of the project. So the idea is to demonstrate that with metal hydrides it's possible to store at enough quantity of hydrogen, so around 50 kilos. That is a quite huge quantity for hydrogen storage by metal hydrides. And to do that, a low pressure less than 50 bar and a low temperature less than 100 degrees C. Of course, the goal, because we are dealing with metal hydride, is to stay with a low footprint. And in order to reach these goals, the idea is to develop an innovative design. But the main point is to couple the hydrogen storage with a thermal storage, and that will be the main concept of the project. Of course, the goal is to improve the efficiency and then to demonstrate that that can be integrated with the electrolyzer and the fuel cell, and of course, to have a demonstration in the real applications. Of course, as usual, we have to take care of safety, to make some evaluation from the technical point of view, to take care about the environment impact with LCA analysis, and of course to try to exploit the results and then to follow suitable dissemination and engagement. But let me run with the next slide to the main concept of our project. So when the hydrogen is getting into the metal hydride, you have an exothermal reaction. And the idea, if you see on the bottom left of the slide, the idea is that the heat released by the metal hydride is stored by a phase change material. So that the heat released is stored in another material, and then eventually you could provide further store from the electrolyzer or from an external source. When you need hydrogen back from the metal hydride, you need to provide heat, but in this case, the heat is coming again from the heat storage. So the phase change material is moving from the liquid to the solid state, is releasing heat, and this is provided to the metal hydride. So at the end of the day, you have absorption and desorption of hydrogen, but the heat that is involved in the reaction is stay inside of the system. This has been a concept that has been, suggested from the literature, but it has never been applied in a real system. So this basically started from this idea, from this concept, we moved in the different stages of the project. So in the next slide is just to say that we already selected the material. That is basically a system on the iron titanium alloys that is able to store hydrogen at around 50 degrees C and at a pressure that can be used close to the electrolyzer, so close to 25 bar for charging, and to be released at about 2 bar, that is the needs for the fuel cell. You can see in the bottom left the typical behavior of the metal hydride. This is what we call PCT curve. But of course, because of the range in pressure that we are dealing with the system, we have a limited amount of hydrogen that can be stored into the alloy. So the weight percent that is available is about 1 weight percent. But the good point is that we are able to stay below 30 bar and below 70 degrees C. So the system, the alloy has been fully selected. And in the next slide, we can show that we already started in the upscaling. So our partner GKN provided to produce more than 4 tons of such a kind of powder with a suitable compositions. And all this powder has been compressed in specific pellets in order to optimize the thermal management of the whole system. This amount of alloys, about 4 tons, is able to reach nearly 50 kilos of hydrogen. That, as I said, is a rather huge quantity for metal hydride. What you can see in the bottom left of this slide is the very early prototype. This is based on about 60 kilos of powder, so it's a small fraction of the whole system, but it has been demonstrated that the system is really working. So thanks to this, demonstration with a small prototype, we started to build up the real system. In the next slide, there are some preliminary indication on how the real system will work. You can see on the bottom left, the tank for the phase change material. Of course, in this case, we will need a lot of thermal management, thermal conductivity. And on the right, you can see the full assembly where you have the PCM in the bottom and the metal hydride tank in the top. Of course, this exchange of heat from metal hydride and PCM will reduce significantly the needs of heat from the external sources, and this will provide an increased efficiency. So our goal is to reach an efficiency that is higher than 70%. Okay, so now the system, when we will build, have to be integrated. So let's go to the next slide, where we have some hints on the whole system to be integrated. So all the system will be inside of a container, and at the ENGIE site in Paris, that will be linked with an electrolyzer that will be providing hydrogen during the absorption. And then the system will be linked to a fuel cell to use the hydrogen when it will be delivered. The location for the system is already been established, and we are now finalizing the building of the system that is planned to be delivered in ENGIE sites early next year. I think we could move to the next slide, where basically we like just to remind that along the project, we have been supported by this support service for exploitation of research results. this is a rather good exercise that we are running for this project in order to understand how much results can be exploited. And on the other hand, I like to stress that the exercise made by Trust is very useful for us in order to compare the results of our system with the other possible options for hydrogen storage. Next slide, please. I think we quickly summarize that, of course, the system is very much engaged in communications and disseminations activities that, of course, are linked to the websites, are linked to the different meetings, papers, and all other activities that are typical for European projects. Okay, I think I basically went to the conclusion. Maybe in the next slide, we can have the very final conclusion. Simply to say, in the next slide, please. Okay, simply to say that we started with the HyCare. During our running, we went into the COVID, so the logo slightly changed it to Take Care. And this is basically the message that I like to send to everyone. Thank you very much indeed for hearing to me.
Thank you, Marcelo, for the great presentation and the even better message at the end. A few questions from my side. I will also try to see what we have from the audience. With respect to the targeted applications, we've seen in your project right now, where how the system is going to be installed at NDNG, and we're looking at basically a power-to-power application. Do you see this as the main targeted application for this type of storage system, or do you see this a possibility for mobility? Do you see for big industry where you also have heat available? What kind of applications are you targeting?
Yes, thank you for the question. Definitely, the idea is to think about stationary applications, mainly because of the weight of the metal hydride.
Sorry,
basically
for mobility, I meant refueling stations.
Refueling
stations. Sorry for
okay.
the clarification.
No, sorry for that. So that's clear. Of course, one of the big issue is to try to reduce the footprint of the hydrogen storage system. So let me say that volumetric footprint is one of the main points that we are dealing with. So in principle, this can be applied in all the system where actually you have such a kind of needs. Let me say that at the beginning, we mainly are thinking to the storage or renewable energies, mainly thinking to the place where you have to develop a self-standing system, you know, and that is the main region for storing heat that is able to go back and forth. This, in some sense, is the main point. Of course, this, in principle, can be also thought for hydrogen refueling stations, you know, mainly in places where you have a localized production, so that can be quickly be joined with the electrolyzer in one side and with the eventually with the delivering of the hydrogen on the other side. Of course, even in the remote application where you basically have no so many connection with the grid or whatever, that again can be possible case studies for such a kind of options.
Clear. Thank you. Thank you for your reply. And just to make it clear to the audience, what kind of volumetric density are you targeting within HyCare?
Well, actually, when we are dealing with the volumetric density, all the time we have to move from the carrier to the system. So we know that hydrogen metal hydride are very high volumetric dense material because they are able to collect much more hydrogen per volume than liquid hydrogen or, let's say, compressed gas. But of course, this is a matter of the material itself. Then as soon as you move to the powder and then to the pellets, of course, you are changing, you know, the volumetric density itself. As long as you move from the pellets into the system, of course, you have to improve the volume, and then the volumetric density is reducing. Let me say that at the moment, the main goal of the project is to demonstrate a concept, to demonstrate that metal hydride and its storage can talk together. Of course, as you have seen in the slides, there is a lot of room for optimizing the volume of the whole system. And then in the next steps, we really hope to improve such a kind of volumetric density. I don't know if I get my point, but the main matter is to move from the carrier to the system.
Clear. Thank you for your reply. And just to touch a bit on the cost issues, understanding that you're still at an early stage, but do you have any projections at this moment about, let's say, the cost of storage per kilogram, when assuming a lifetime of 20 years for the overall system?
Yes, thank you for the question. Of course, in this specific case, you have to add a cost of the powder itself. That, of course, is an issue. But let's say this, at the end of the day, is just a component of the whole system. And of course, that strongly depends on the market. So in principle, we are talking about iron and titanium, basically. So it's a material that itself is not so expensive. So the matter, of course, is how much you need devices around. And we strongly believe that dealing with system at less, let's say, than 700 degrees C and less than 50 bar, actually you could save a bit of the, the equipment around the system itself. So difficult right now to make an estimation of the cost per kilo, because of course it's too early. But the idea is, at the end of the day, to plan, or at least to forecast for the development of the market, so that the cost of the alloy itself can be something affordable, and then to save a bit of money for the other devices around because of the low temperature and low pressure.
Excellent, thank you for the reply. And we have one, let's say, last question from the audience. With respect to the lifetime of the tanks, how long do you expect that the system will last?
Yeah, that of course is an issue. At the moment, we simply played in cycling the powder itself, and the issue related to how much cycle you could play with the metal hydride has been already quite widely explored in the literature. We just run in a lab scale, let's say, equipment, and we already have cycling for more than 300 times, and we are planning to start with further cycles. How much this cycling time will be really explored in the real system is something that, of course, we have to be managed. The project plans to run for about 6 months just for testing. Of course, in 6 months, you don't have too much time for making several cycles, but the idea is to already start on doing that. Of course, you have to take care of all the equipments around the metal hydride itself. But let me say that from the preliminary results, it seems that the bottleneck is not the powder itself.
Okay, thank you very much once again for the discussion and the presentation. And I think it's time that we move to the next speaker.
Thank you, Dennis.
Thanks. And we can move to the next speaker, Ralph Oates, who's from Hydrogenious, and will be showing us the results of Project HyStock, moving on to the distribution of hydrogen with liquid organic hydrogen carriers. Ralph, the floor is yours.
Thank you very much, and good afternoon to everybody. Thank you for having the opportunity to present our Project HyStock. So I will present to you today some of the results of the project, and I'm the head of policy of regulation at Hydrogenious, but I also want to thank my colleague Vincent, who is the project manager for this project, and we have very good success. And also thank you to our partners in this project. And let's go on to the next slide, and I'll tell you a little bit about the project itself. So first of all, it derives from the year 2017, and it started in 2018. Actually, it is a little bit prolonged thanks to the situation with Corona, COVID, and so on. So we are very thankful for the flexibility of the European Commission and the FCH-JU program. And I think with the last month, we will also get very interesting results for our future projects. So perhaps last but not least, our partners in this project, this is of course Hydrogenious, LOHC Technologies, this is us, then the University of Erlangen-Nuremberg, Hygear, VTT and Wojkowski. You see that on the next slide. If you go to the next slide, where we are located actually. So in Erlangen, Germany, Hydrogenious and FAU. In the Netherlands, Hygear, which brings the hydrogen purification unit. Then we have VTT, which researches also is very much on the gas quality. And we have Wojkowski, who have the tank system and helps us with the LOHC logistics. And if you go to the next slide, we have a short project summary here. So hydrogen production and hydrogenation we will do in Kokkola in Finland. We store hydrogen in a liquid organic hydrogen carrier, shortly LOHC. And with this LOHC, we can transport the very complex hydrogen molecule to VTT and can dehydrogenate again the hydrogen. So we bring it, first we bind it to an oil. This oil is called dibenzyltoluene, DBT. And then with some thermal heat, or thermal energy, we bring or drive the hydrogen out of the oil. And here for this project, we are actually looking very much into the quality of the hydrogen, which we can get out of the oil, and the gas analysis, which is done by our partner VTT. And this is actually one of our main objectives. So first of all, we want to develop a cost-efficient, fully automated LOHC hydrogen storage and release system. We want to demonstrate the suitability for a commercial rollout, and also with regards to the hydrogen purification unit. And of course, for the future, as we will need a lot of hydrogen for the decarbonization of our industries, we want to reduce CAPEX and OPEX to store and transport hydrogen. If you go to the next slide, please. Just very, very briefly, some technical insights. So what do we do actually with this dibenzyltoluene, or the LOHC in general? First of all, if we get the hydrogen from any source, could be, for example, in the future from a wind or PV power plant, and then having an electrolyzer, getting the hydrogen molecule. And then with the hydrogen molecule, we bind it to an oil, to the DBT in this project. There, when you bind it, you have an exothermal reaction, which is that you get heat out. Then you have stored the hydrogen in this oil, and you can transport it like you are used with the oil industry, for example, in a trailer, in a ship, or on a train. Bring it to the point of use, so where it shall be used, for example, in a harbor where you put the hydrogen molecule into a pipeline, or bring it directly to the industry, which is in need of green energy, and hydrogen, the perfect carrier for this energy. At the dehydrogenation, we have to use or put heat in. More or less, it's the same amount of heat we get out at the hydrogenation unit, what we have to put in at the dehydrogenation unit. And then, of course, like a cycle economy, we bring the dehydrogenated DBT, the LOHC, back to the hydrogenation plant and have a sort of cycle, and can do this several hundred cycles with the DBT. And why do we use, or why do we do all this with the LOHC, the carrier? Several advantages from our point of view. The dibenzyltoluene is non-explosive. It's very much like diesel. Of course, it has some other advantages like toxicity and so on, but it's quite comparable to diesel. It's hardly flammable. It has a very good liquid state condition until minus 39 degrees Celsius, which is very important also for Finland. It can be stored at ambient conditions, and the DBT is already available. It's a commercial heat transfer oil, and of course, for the future, we want to make it a huge material, which a commodity which is used all over the world to transport hydrogen. If you go to the next slide. So what is the status of the storage system? The storage box, it's nearly completed. So the storage box is already under operation. It has already hydrated around 1 ton of hydrogen, which means for each ton of hydrogen, we need about 17.5 tons of LOHC. It's operated by our partner Wojtkowski. It has about 1 year, a little bit more, started its regular operation, and the logistics between the storage box and the release box is done by the project partner Wojtkowski as well. If you go to the next slide, we see the release system, the release box. So this started in January 2021, the commissioning, despite very heavy winter conditions, not the one here in Germany, but especially those in Finland. And it gets its hydrogen from the storage box system. It started in March 2021, the regular operation. And actually, we are very much testing, especially because we know already what our systems can do. We have them operating since 2016 and in several locations. But now with this project, we really want to see what the purification unit can do. So what purity the hydrogen has and how can it used for example, for fuel cells. And according to the first results, actually the hydrogen meets the requirements of the ISO. So we are quite optimistic, and actually, as it's the end of the project, but we have some months more, we said, okay, we want to test the next thing with this project. And also thanks to the flexibility of our very good coordination office, FCHTU, we can do some more testing. And if you go to the next slide, let me very briefly introduce to you just the general status, but that's just about the reports, though they are going to be finalized. But there is something standing there. We want to have an extended test program at VTT instead of the HRS at Wojtkowski. Now, this is quite interesting because in Finland, there aren't that many hydrogen-fueled cars. So we said, instead of using this as a hydrogen refueling system, which was first planned for, we want to test a little bit more on the system and actually for the later use cases. So the use cases will be first, store green hydrogen from, for example, intermittent renewable energies. And intermittent renewable energies means that you also have intermittent hydrogen coming to the system. And we think our technology works quite good with that and is very flexible with regards to green hydrogen. And actually also, what can we do with a release system? How can we play a little bit around with the purity of the hydrogen? For what use case do we need the hydrogen? And to what purity can we get there? And if you go to the next slide, you see just the reality. These are real systems in operation. The storage box on the right, you see the release box, and in the middle, the nice LOHC logistics, not a trailer, but a small box where the oil is in there. So very easily transportable now, the hydrogen. If you go to the next slide, some risks and challenges and lessons learned. First of all of us know the COVID situation, quite difficult, but actually some other challenges and lessons learned. We've seen the availability of hydrogen cars and hydrogen refueling stations in Finland makes it quite difficult to have a use case. And therefore the lessons learned is thanks, what I've already said, thanks to the coordination office, we could change a little bit our project plan and extended our test program for the LOHC release box. And this was thankful. We are quite thankful to all our partners that achieved this. And if you go to the next slide, just some brief comments on the exploitation plan and expected impact. So it helps us very much to have this project because we can update on our project research, on our research actually, and especially look at the gas quality, which is measured by VTT. And this is really important for our projects, but also for our partners. And we will further exploit other LOHCs in next research projects. So not just DBT, the next projects will look at BT, and we will use a lot of the information and also equipment from this project for the next project. And the impact, there's a lot of impact there, of course, but one thing with this project, it actually gives us the first start of storing hydrogen from intermittent renewable energy sources, which is very important for green hydrogen as the energy carrier of the future. And I think with our LOHC technology, we can achieve this. And this HyStock project was the first start of it. And if you go to the next slide, you see a little bit of our next plans, very much also in the European Union context. So we have several IPCEI projects planned, like Green Crane, like green hydrogen at Blue Danube, but also Aquaventus in with the offshore industry. And with all these results from the HyStock project, they are the basis for our future upscaling projects with different LOHCs, for example, benzyltoluene. And that was very briefly a short overview over our project HyStock. And thank you. And I'm ready to answer you some questions. Thank you very much.
Right. I'm mute. Thank you very much, Ralph, for the great presentation. Very nice overview indeed. And I will, while we wait for the audience's questions, I'll just start with a few of my own. You mentioned several times that VTT will be investigating the purity of the hydrogen following the dehydrogenation. And do you have any results you could share with us about, what kind of quality of hydrogen we're dealing with?
So the most important and most significant one is that we meet the ISO standards, the 99.97% of hydrogen purity. But it's perhaps also to give you a certain overview of the use cases for hydrogen in the future. You have different purities and for different use cases. So we want also to see, do we need this system, or what purity can we achieve for example, hydrogen-fueled cars? But on the same, at the same time, we also want to see which industry needs which purity, and what, how can we achieve that purity with which system? And that helps us a lot, not just getting the maximum of the purity, but also what pressures, what different filters or units, PSAs, do we need to fulfill the purity or purification process for which industry use case. And that's quite important for us, and therefore we plan to test a little bit more on this purification, not just for the fuel cells, but also for other use cases. And what we also see with our technology, to actually use this technology on ships, for example. So a direct combination with a fuel cell, where you also need another purification unit perhaps, or another purity. And this is also one step to get to the next step, not just stationary, but also on a mobility scale. So for example, for the maritime industry.
Okay, thank you. Thank you very much. And yeah, in my presentation earlier this morning, I mentioned about the JRC policy brief that they released on hydrogen storage and on distribution, comparing various methods. And they showed that for liquid organic hydrogen carriers, they are very well positioned when it comes to very large distances. They really are showing themselves as the most, let's say, economic method of distributing hydrogen. Is this the end game for you, or do you see yourselves fitting in other segments as well?
I've quite a difficult and very good question, because first of all, there are so many TCO studies around, and some showing only this carrier will make the race, some are showing a completely different carrier will make the race. I think we have to look at the use cases, and I think, yes, for very large value chains, LOHC is very well suited. But also, for example, a use case where we have a very complex value chain, LOHC can be used quite good, because we are in oil in the end. We can be used in the existing infrastructure, which we already know, and there we have also several advantages. So I think in the future, it really depends on the use case And of course, as all the TCO studies show, we are quite good in the game, I would say, with our technology.
Okay, thank you very much, Ralph, for the good discussion. And I think now we can move on to the next speaker. We'll be going now to the gas grid, and we will have Vanessa Aguil, who's the head of R&D in Fundación Hidrógeno Aragón, who will guide us through the achievements of Project Higgs, which is looking at hydrogen injection in the natural gas grid. Vanessa, the floor is yours.
Thank you so much. And yeah, so I will start. Yeah, so please, the next slide. Yeah. So the project, in fact, is about systematic validation of the ability to inject hydrogen at various admixture level into high pressure gas networks in operational conditions. The project started just a few months, a couple of months before the pandemic. So it was beginning of January 2020. And we are almost at the midterm of the project, a bit more. So we are six, yeah, please, next slide. We are 6 partners. Araugen Foundation, we are the coordinators of the project. Then also we have DBGW. They are focused on the regulations, codes and standards. OST from Switzerland, they are focused on the techno-economic studies on the field of the project. And then we have Tecnalia and Rodexis, both from Spain. Rodexis as the TSO and Tecnalia, they are contributing to the project in the characterization of the materials and also providing a membrane prototype for separation as a separation technology of the blend. And then we have Eric as a partner or as the manager of the project focused on communication and dissemination activities. So please, next slide. Yeah, so what is about Higgs? What is about this project? Higgs it aims to pave the way to decarbonize the gas grid and its use. How? Well, by covering the gaps of knowledge of the impact that different levels of hydrogen could have on the high pressure gas grid. Not only on the existing infrastructure, but also its components and also its management. So we have specific objectives in the project. We have 3 main topics or areas. The first one is try to map all the technical, legal, and regulatory barriers and enablers. Also, of course, testing and validate systems and innovation. So in the frame of the project, we have commissioned, we'll come later with another slides, but we have commissioned a testing loop that is able to test some components and some instrumentation of the high pressure gas grid. Also, we have another or the third main objective or goal, specific goal of the project is try to develop operation strategies by techno-economic modeling studies. And in conclusion, in summary, is try to define a set of conclusions as a pathway towards enabling the injection of hydrogen in high pressure gas grids. So please, next slide. Yeah, so if we compare the positioning of Higgs project versus the state of the art, how our project contribute to the Green Deal and this specific topic. The first point is that we try to provide a descriptive picture of the European natural gas transmission grid, so meaning high pressure gas grid. Also, we will construct, or we have constructed an R&D testing platform to work at 80 bar. That is the current maximum operation pressure for this kind of grids with hydrogen atmosphere at several concentrations. So this will allow, allow the replication of operating conditions of the European transmission gas grid. And of course, a methodology is developed to build and simulate a model of a network as efficiently as possible to perform techno-economic simulations of gas networks. The application of all this knowledge and know-how and market area could be, of course, components manufacturers, membranes producers, TSOs, operators in Europe, but also abroad, of course, software developers and RSC bodies. So please, next slide. Yeah, so we try to compare which is the status of the project right now for specific items, we could say, since it's quite difficult to provide KPIs for this kind of project, but we try to provide you the overall overview of the project. So one of these is try to see, okay, how is this kind of this picture that we want to gather in this project, this picture of the European natural gas transmission grid. So I can tell you that is quite advanced. It's true that we could make two differences, since we cover not only the instrumentation, or not only the infrastructure of at European level, but also all the regulations, codes, and standards. There are some differences. So we could say that we almost compile, or we have compiled almost the 100%. We are in the 75 regarding infrastructure. So meaning, for example, which are the most frequent pipeline materials or steel types that are present in the European gas network, depending on the countries or on the clusters that we have considered. So we have done this. Also, we gather all the information that it was until the date of the submission of the report, looking into these algorithm codes and standards. We can see that the picture is quite broad across Europe, so it's not homogenized. So the picture is a bit complex to handle, but finally we managed to gather all this information. And I can tell you that this is compiled in a dribble, that it was approved and will be, it's a public dribble that would be to be accessed by all of us quite soon. Please, next slide. Yeah, so this is the testing platform that I told you before. This is the experimental testing campaign. Is already commissioned, so the commissioning is done. This is at our facilities, as our facility at Goncanen Foundation. So right now we are in the time of running the first testing campaign with the first blend. I didn't say that, but the idea is to cover from low to high blend or percentage of hydrogen in the blend. And we will test several conditions. So here is just a picture about the loop. We have two sections, one dynamic section, static section also for different purposes. And the idea how we have commissioned this loop is that from the information that we got across Europe, we selected those materials, those steel that were the more representative across Europe. Those steels will be tested at 80 bars and with hydrogen methane blend. Also, we will consider at some point impurities, and we will characterize what is happening, not only in the steels, but also in some specific components, critical components of the high pressure gas grid. So please, the next slide. Yeah, so about risk, challenges, and lessons learned, of course, a lot of them, especially handling with this pandemic. But we could say that, of course, one of the key or critical points in the project on the side of this trying to handle this pandemic, it was really difficult sometimes to get information of the European high pressure gas grid. And since we wanted to have, or we must have this data that would be representative across Europe, sometimes it was critical to the project. We handled with this issue, and I would say that at the end, we could manage this, but it was a key point to be considered in the project. Also, at some point, for some countries, it was difficult to get current strategies because it was incomplete. Of course, also we consider that we were in a timing where it was really high, or it was really a high dynamic process across Europe about hydrogen and even this kind of consideration of the blends and so on. So sometimes it was difficult also to get so many data, so many information in a short time of period. Yeah. Regarding the assembly of the campaign, also, of course, we had a slight delay in the assembly of the platform that will modify the testing campaign. And finally, the acquisition of network data for simulations. We have decided that the simplification of the model is necessary to get information of this, or with the final results. And also a critical point is that there is no any standardized method for such task that also is difficult to handle. So please, next slide. Yeah, about dissemination and activities, what happened so far? Besides the pandemic, we were able to organize 3 conferences on the frame of the project and 2 workshops. Also, Higgs was presented at 12 external events, conferences, and fairs, of course, the most of them online, virtual, digital ones. Also, we have prepared some digital materials, presentations, fact sheets, press kits that are available on the project website. The first public deliverables will be published at the end of this year. As I said, they are almost done to be launched. And of course, what is planned for coming years or the next year, of course, is a showcase event at the demo site, possible. Also a project video to promote the results, and of course, more workshops. So if you want to be informed of this project, please just go to this with the WhatsApp of the project, his project, or even we are in LinkedIn and Twitter. Please, next slide. And I think just we only have two more slides. Yeah, this is about the exploitation plan and expected impact. We have applied for the Horizon results booster. So we already were in contact with these services that they will help us to exploit the results of the project and also maximize the impact. So far, we have identified several key exploitable results. For example, the testing platform could be one of those, since it's a platform that, as I said, is a good platform or a good tool to test new components at high pressure and with different blends and even with impurities. So this is quite relevant. And of course, there are more key exploitable results that will come with the project. So please, next slide. Yeah, and this is just the final picture. So you can just have here an insight or a taste of what is about the testing platform. So just you have on the right the facility, the main building. On the left, sorry, on the right, you have the solar panels, and just in the center, at the end of the picture, you have the testing platform. Yeah. So thank you so much. I think with the next slide, yes, it's done. So thank you so much for the attention. And if there is any question, I will be happy to answer.
Thank you for the presentation, Vanessa. I will move straight to the questions from the audience. So do you have any idea already, based on the first assessment that you've made, about the percentage of readiness of European grids with respect to the first point of 20% admixture, and then if we go to 100% H2, what percentage of those would be, let's say, H2 ready?
Well, it's difficult, right? Because right now we just started with the testing campaign. So we have right now the first plant, and we are waiting for the results. Of course, also we should think about the end user, right? A part of what will happen to, of course, with the specific materials, because we should keep in mind that we are considering the existing gas grid. Of course, fresh materials, but materials that are in the existing gas grid. So, of course, even though we should take into account what will happen with the different blends and even with the pure hydrogen, but we cannot forget the end users. In this regard, we are quite close also to our sister project. What we like to call it is the Giga project, that they are focused on the end user, let's say. So it's quite complex, and hopefully we will see with the time of the project, we can provide the answer.
Thank you. And with respect to the, let's say, the negative effect of hydrogen, where do you expect to see the most problems? Is it the pipelines themselves, or are you also going to be investigating effects on network components, valves, compressors, etc.?
Yes, we have, yeah, of course, we have different steel grades from X42 up to X70, I think, if I remember right. And then, well, those materials are in a different way prepared. So we have like a base and also welded pipes, but also we have equipment. So for example, or components. Of course, we have valves, different types of valves, the most representative ones from the existing infrastructure. So we have different valves. Also, we have pseudo pressure regulation and measurement station, I think it's called. So it's we have like a filter regulator and pressure regulator, and also gas meter. And with all these components, and after each testing campaign, we will see if there is, of course, if there is any leakage, or permeation, how will affect also to some materials of these components. So after each testing campaign, not only the steels will be characterized by mechanical properties, for example, but also we will look into some specific, into some specific components. Yeah, so for example, in the regulators could be like the spring or specific parts of these components.
Thank you. And at some point you mentioned the reluctance of the TSOs to provide you with data. Do you have a strategy in the coming months on how to resolve this barrier, to somehow tempt them with your R&D platform maybe, and offer it in exchange?
Yeah, I would say that there was a critical point, let's say at the beginning of the project or since the beginning of the project. It's true that at the time when was understood why they should provide this information or why it was important to provide this information, it was better and better, let's say. Of course, we should consider that we have considering a lot of countries across Europe, and we wanted to get a representative information. So far, I would say that we are quite positioned. So you will see in the public dribble, but we have gathered all the information in clusters, and you could see that it are quite representative. So even though still we have some let's say gaps that we could not be able so far to get information, we could say that our project will provide representative information across Europe. What is, I would say, the final message. But yes, we try to define different ways to get this information. Yes.
Okay, thank you for your reply. And one last question from the audience. They would like to know what will be the minimum duration of steel pipe testing to be sure that no hydrogen embrittlement has occurred?
Very good question, I would say, because since will be the first time, right? Yes, it's difficult. And also we should keep in mind that this is a 3 years project, and that the half of the project is just to have ready the testing platform. So we keep this in mind. We only have 1.5 more year project just to test different blends. So you can just make your conclusions. Of course, it's difficult to say how long should we keep one blend right to get final conclusions. But at least we could have the first assessment. If something is wrong, we know that it's a challenge. If everything is okay, of course, to make final conclusions will be difficult. But at least we have a first way to go, right? So, of course, more and more projects, I would say, are necessary in this field. This is the first FCH project focused on trying to develop these experiments at high pressure with different blends. So I would say that more and more projects are needed, and of course feed it with information from previous projects. So we will see what is. We are all of us. We are expecting what is coming from the first testing campaign. We will see how it goes.
Okay, thank you very much, Vanessa. With that, I'd like to close on Higgs and move on to the next project, HyGrid, which assumes that we have already managed to inject without any problems, and we now have to extract. So Fausto will guide us through the results of HyGrid. Fausto is a professor from Eindhoven University of Technology and is the coordinator of HyGrid, and will let us know of their achievements. Fausto, the floor is yours.
Thank you very much for the introduction and for giving me the possibility to give this presentation of HyGrid, and probably will be the last presentation of HyGrid. In fact, if you go to the next slide, you will see that the HyGrid project is finished and was a very long project. In reality, we had two main drawbacks through the project. One is shared by all the projects, I would say, is the pandemic. And we got the pandemic exactly when we had to put together all the prototypes and test them. And the other drawback was how we built the project, because you see the partners. We have very experienced partners, but also possible end users. And one was SAES. You see in brackets is a partner that was terminated. They had a very good market possibility for this technology, and especially in Europe, but especially in US. So they participated to the project with a lot of in-kind contribution, but unfortunately the market was so good that the company was sold to a US company, and they had to leave the project. So we had to stop with their design, make a new design of the system, and this took quite a lot of time also to regulate with the budget. Now, if you go to the next slide, basically, indeed, when we wrote the project, there were already some studies in Europe, but also in Canada and in US, showing that up to 10% of injection was no problem for the grids, and also no problem from a safety point of view. So we decided to do a project to extract hydrogen when it's a very low concentration, below 10%. And the idea is that with that concentration, the standard technology, in particular PSA, is too expensive to get pure hydrogen out of the grid. So we designed the project to have an hybrid technology that integrates membranes, hydrogen separators, and TSA. And the idea was to test the technology up to 25 kilo per day of hydrogen, so relatively small system. But with the SAES leaving the project, then we had to shrink a little bit this target. The rest of the target was to test the prototype at TRL5, so in real condition, and with a cost of below 1.5 euro per kilogram of hydrogen. Now, if you go to the next slide, you will see that basically, as I said before, we have a membrane module or more membrane modules, an electrochemical separator, and TSA. We use this very simplified schematic at the beginning of the project because we were making a patent out of the system to separate the hydrogen. But after, during the project, we also realized that this way to show the project is still valid, because depending on the amount of hydrogen that you have in the natural gas grid, and depending also on the number of steps that you can allow, so the cost and the purity of the hydrogen, indeed you can have so many combinations. And at the end, I will also show you that we calculated so many combinations. Now, if you go to the next slide, you see the partners. We have several partners from the Netherlands, with iGear and IET as industrial partners. And then we have Technalia and Nortegas. So we have also the gas grid included in the project. We have Quantis to do the LCA, and we had SAES that did the first part of the testing of the materials with hydrogen and the first design, but then we had to change the design, as I said before. Now, if you go to the next slide, I will show you a little bit of pictures. Of course, the project is finished and we were successful. So all the achievements are at TRL5, what we expected. And here you see the membranes that we use for the prototype. We tested several membranes, but at the end of the day, we used a single step palladium-based membranes. You see a few of these palladium membranes, a bundle of palladium membranes, and the real prototype, as it was in our laboratory in Eindhoven, and then as implemented also in the prototype at IGEA. If you go to the next slide, you will see also the perhaps click another time, because there should be another picture indeed. You see that we had also the electrochemical separator, the design of the control and the implementation of the electrochemical separator. What we want to do with the separator is to extract the last few percent of hydrogen in the natural gas grid, and then re-inject the natural gas inside the grid. So the challenge here was the scale up, of course, but especially having a very low pressure drop, because otherwise you need an additional compressor to put the natural gas in the grid. Anyway, we took some time. IET took some time, but was very successful also in this. And the test also showed that the scaled up prototype had a much better efficiency compared to what they tested in the lab. So it was also a nice achievement. And if you go to the next slide, you will see also the few picture of the prototype. The prototype, of course, has the membrane separation, has the TSA and the electrochemical separation, but also the conditioning of the gas, the cleaning of the gas before injecting in the prototype, and then the recycle of the gas in the natural gas grid. And if you go to the next slide, you also see the membrane prototype installed close to the heat exchangers, because this is a palladium membrane, so works at higher temperature. And in the back of the container, you see also the electrochemical separator connected downstream the membrane separator. Now, if you go to the next slide, of course, this was tested, and we reached the targets of the project. If you make another click, we did also quite a lot of tests on different membranes, because I told you that you can integrate different membranes. And here you see membranes tested at up to 40 bar, because compared to the previous project, we tested the membranes up to the grid of 40 bar. And you see that even cheaper membrane can be used, and still the purity is more than 93%. So this is still not yet good enough for the target of the project, but allows us to do a lot of different designs. For example, using first a cheap membrane and then a more expensive membrane, and then the electrochemical separator. If you go to the next slide, you see also the LCA analysis. Of course, we have a more extensive report that is also available. Here we compare our small scale iGrid with a PSA for separating the same concentration of hydrogen, and you see that the iGrid prototype is better in all the terms. Also considering that the PSA is optimized, while the iGrid prototype, you saw that is a small prototype in a big container. So if you scale up this system even to 200 kilo per day or even higher, then the difference between the iGrid and the PSA becomes even larger. And if you go to the next slide, as I said, we optimize the separation using a lot of different combinations. Here you see the configuration called in different ways. Each configuration has, for example, more membrane area or different membranes and different amount of hydrogen separated from the electrochemical separator. But all of them reach the target, of course, with different consumption. And for some of them, of course, we are below the target of the iGrid project. And if you go to the next slide, as conclusion of the talk, of course, the numbers are very interesting. We got 2 patent applications, one on the membrane and one on the system. What is very interesting is that one patent application was transferred to a spin-off company, H2 site that is using the design to commercialize this system for hydrogen separation. And the other patent is used as to be licensed in another spin-off company that we are creating together with Tecnalia. The project also, at the end of the project, we also got data for a third patent, but it's not yet submitted. We had 7 scientific publications in very good journals. What is important is that out of this publication, we got also a PhD student defending already, and the PhD student is working in a company dealing with hydrogen. So it's also a nice product of the project. We got 14 presentations in live conferences. Of course, as all the other projects in the last 2 years, we had many more online, but are not accounted here in this calculation. And we had 2 workshops and last June also a webinar for showing the first results of the prototype. And if you go to the next slide, then is the end of my presentation. As I said, thank you very much for the possibility, but also thank you for the FCH, because thanks to the support, we were able to bring the technology to TRL 5, test the technology, and transfer to spin-off companies, which is very good also for the economy. Thank you very much.
Thank you, Fausto, for the great presentation, the good results as well. When we are talking about the future, you said that the good results were transferred to the companies and they're now exploiting them. Do you see this done only in this specific application of extracting hydrogen from the natural gas grid, or do you see other possibilities as well?
No, actually, the extraction of the hydrogen from natural gas grid was a good test for the technology. You can imagine that you can separate from different mixtures, and actually we are still working together with the spin-off company on testing the system for different mixtures. So it's not just for natural gas grid. And the second spin-off company is not just about hydrogen separation, it's about gas separation.
Mm-hmm. Okay. Thank you very much. I see that the audience is rather tired and we don't have a great amount of questions incoming anymore. So I think this is a good signal to close the session and to close the day. I would like to thank you very much for joining us. Thank you for your good presentations and the engaging talks. To the audience, please join us tomorrow at 9:30 as we are starting immediately with parallel sessions, one on PNR for standards and safety, and another for stationary applications. So thanks again, everyone, and see you tomorrow.
Bye.
Bye.
Bye. Thank you very much.